Dark matter is an elusive substance that does not emit, absorb, or reflect light, making it invisible to traditional astronomical instruments. Unlike normal matter, which is composed of atoms with protons, neutrons, and electrons, dark matter interacts primarily through gravity and possibly weak forces, but not through electromagnetism, which is why it does not shine or block light. This key difference means that even though dark matter constitutes about 27% of the total mass energy content of the universe, it cannot be observed directly with telescopes that rely on electromagnetic radiation. The term dark matter originated in the early 20th century when astronomers first noticed discrepancies in the mass of galaxies and galaxy clusters. By studying galactic rotation curves, scientists such as Fritz Zwicky found that visible matter alone could not account for the gravitational effects observed. Galaxies were spinning too fast for the gravity exerted by their stars and gas. This observation implied the existence of an unseen form of matter, dark matter, that exerts gravitational influence but remains invisible, fundamentally differing from the ordinary matter making up stars, planets, and living things. Dark matter must be distinguished from dark energy, although their names are similar. While dark matter contributes to the gravitational pull that holds galaxies and clusters together, dark energy is a mysterious form of energy causing the accelerated expansion of the universe. Observations of distant supernovae and the cosmic microwave background radiation support the existence of dark energy, which constitutes about 68% of the universe's mass energy budget, compared to 27% for dark matter and only around 5% for normal matter. These fundamentally different roles highlight the separate phenomena of dark matter and dark energy in cosmology. The existence of dark matter is supported not only by galactic rotation measurements, but also by gravitational lensing, the bending of light from background sources such as distant galaxies and quasars by massive foreground structures. These lensing effects can be mapped to reveal the presence of mass that does not correspond to visible matter, providing a robust method for tracing dark matter distributions. Observations like those from the Hubble Space Telescope and ground-based observatories have shown that clusters of galaxies possess dark matter halos influencing the light of background objects, confirming the pervasive presence of dark matter. In addition to gravitational lensing and galaxy rotation curves, measurements of the cosmic microwave background, CMB, provide independent evidence of dark matter. The CMB is the relic radiation from the Big Bang, and its detailed temperature fluctuations correspond to density variations in the early universe. Analyzing these patterns with instruments like the Planck satellite reveals that the observed anisotropies require a significant dark matter component to explain the structure formation we see today. Without dark matter, the universe's early density fluctuations would not have grown fast enough to form the galaxies observed in the current epoch. Dark matter does not interact with electromagnetic forces, which accounts for its dark designation, but it responds to gravity, meaning it shapes the large-scale structure of the universe by acting as a scaffold for galaxy formation. Through the gravitational influence of dark matter, ordinary matter aggregates into filaments and clusters across the cosmic web. Numerical simulations combining dark matter with baryonic matter successfully reproduce the cosmic web patterns observed in large-scale galaxy surveys, further emphasizing the crucial role of dark matter in cosmic architecture. Unlike normal matter, dark matter has not been directly detected in laboratory experiments. Particle physics searches, including those involving underground detectors looking for weakly interacting massive particles, WIMPs, have so far produced null results. This non-detection challenges theorists to consider alternative particle candidates, such as axions or sterile neutrinos, but all remain speculative. The inability to identify dark matter particles within the standard model of particle physics underscores its fundamental difference from known matter constituents. The standard model, which elegantly describes all known elementary particles and 3 of the 4 fundamental forces, does not currently incorporate any particle that could serve as dark matter. This absence points to physics beyond the standard model, motivating experimental and theoretical efforts in particle physics and cosmology. Extensions such as supersymmetry predict new particles that could be dark matter candidates. But until evidence for these particles emerges, dark matter remains an entity outside the well-tested framework describing normal matter and its interactions. Dark matter clusters on scales much larger than ordinary matter, creating expansive halos that envelop galaxies and galaxy groups. These halos extend well beyond the visible edges of galaxies, typically by a factor of 10 or more, influencing the orbital speeds of stars and gas clouds at distances where visible matter alone would produce weaker gravitational forces. The presence of such extended halos is inferred from detailed rotation curves and the dynamical behavior of satellite galaxies, reaffirming the existence and influence of an unseen mass component within galactic structures. Further insights into dark matter come from the study of galaxy cluster collisions, such as the famous Bullet cluster. In such collisions, the normal matter, mostly hot gas emitting X-rays, is slowed and displaced by friction, while dark matter appears to pass through unimpeded. Observations combining X-ray imagery and gravitational lensing maps reveal a spatial separation between visible matter and gravitational mass, strongly supporting the idea that dark matter interacts weakly with itself and ordinary matter, primarily through gravity. Studies of structure formation also show that dark matter must be cold or non-relativistic during the epoch when galaxies formed. This designation means dark matter particles moved relatively slowly compared to the speed of light, allowing small density perturbations to collapse into larger structures over time. Simulations assuming hot, dark matter, consisting of fast-moving particles like neutrinos, fail to reproduce the observed abundance of galaxies and the sharpness of cosmic structures, thus reinforcing the cold dark matter model as the standard cosmological paradigm. Dark matter's gravitational influence helps maintain the stability of galaxies over billions of years. Without the additional mass from dark matter, galaxies would not have sufficient gravitational binding to prevent stars from escaping given their observed velocities. This necessity is observed not only in spiral galaxies, but also in elliptical and dwarf galaxies, where mass-to-light ratios often indicate a dominance of dark matter compared to visible matter. These measurements strengthen the conclusion that normal matter is only a minor fraction of total galactic mass content. Some efforts to explain dark matter phenomena attempt modifications to gravity itself, such as the MOND, modified Newtonian dynamics, hypothesis. While these alternative theories can explain certain galactic rotation curves without invoking dark matter, they often struggle to consistently explain other observations like galaxy cluster dynamics and gravitational lensing patterns. Thus, the prevailing consensus remains that dark matter is a distinct form of matter rather than a modification of gravitational theory. The diffuse distribution of dark matter in the universe means it plays a key role in cosmic evolution from the earliest epochs. During the recombination era, when photons decoupled from matter about 380,000 years after the Big Bang, dark matter had already begun to clump under gravity, providing the gravitational wells into which ordinary matter could fall. This interplay between dark and normal matter laid the foundation for subsequent star and galaxy formation, showing that dark matter is central to understanding how the observable universe came to be structured. Current astronomical surveys, including the Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey, DES, provide maps of dark matter distribution on large scales by analyzing gravitational lensing and galaxy clustering. These extensive data sets confirm that dark matter traces the cosmic web's filamentary network, along which galaxies and clusters are aligned. Such surveys assist in measuring cosmological parameters and refining dark matter models, but still leave open questions about the microphysical nature of the dark matter particles themselves. Dark matter's non-interaction with electromagnetic radiation also means it does not radiate heat or light, which sets strict constraints on its temperature and composition. Unlike baryonic matter, it cannot cool by radiating energy, so dark matter remains dynamically hot, in a sense of being gravitationally bound but thermally dark. This property prevents dark matter from collapsing into compact astrophysical objects like stars or planets, meaning it typically forms extended halos rather than dense cores seen in luminous matter. Although the exact particle nature of dark matter remains unknown, many theoretical candidates fit within extensions of particle physics rather than the standard model as it stands. Weakly interacting massive particles, WIMPs, have been popular candidates due to their ability to interact via weak nuclear forces and produce the correct relic abundance through thermal freeze-out in the early universe. However, extensive searches for WIMPs in direct detection experiments such as LUX and Xenon 1T have not confirmed their existence, pushing the field toward broader candidate searches. In summary, dark matter refers to non-luminous matter that interacts gravitationally but not electromagnetically, differing fundamentally from ordinary matter composed of atoms, and is distinct from dark energy, which drives cosmic expansion. Observational evidence from galaxy rotation curves, gravitational lensing, cosmic microwave background fluctuations, and galaxy cluster dynamics consistently supports its existence. However, it remains beyond the reach of the standard model of particle physics, representing a frontier where cosmology, astrophysics, and particle physics intersect to unravel one of the greatest mysteries of modern science. Dark matter constitutes the majority of mass within galaxy clusters, far surpassing the amount of visible matter present. Detailed measurements of the velocity dispersions of galaxies within these clusters reveal gravitational effects that cannot be accounted for by luminous matter alone. These observations date back to Fritz Zwicky's 1930s measurements of the Coma cluster and have been reinforced by more recent studies using advanced telescopes, confirming that dark matter dominates cluster mass budgets by factors of 5 or more compared to stars and hot gas. The inferred distribution of dark matter within galaxies shows a characteristic density profile, often described by models such as the Navarro-Frank-White (NFW) profile. This empirical model, derived from cosmological simulations, describes dark matter density decreasing steadily from a dense core toward the outer regions of galactic halos. Such profiles help explain why the orbital velocity of stars remains roughly constant at large radii, known as flat rotation curves, whereas, under only visible matter, velocities would be expected to fall off. In addition to large-scale dynamics, dark matter's gravitational signature is observed in dwarf spheroidal galaxies, small, faint galaxies that orbit larger galaxies like the Milky Way. Despite their low luminosity, these dwarf galaxies exhibit unexpectedly high mass-to-light ratios, sometimes exceeding 100 times the visible mass. This suggests an overwhelming dominance of dark matter, making such galaxies key laboratories for studying the nature and properties of dark matter due to their relative simplicity and proximity. Dark matter also affects the propagation of sound waves in the early universe's plasma, leaving discernible imprints in the cosmic microwave background, known as baryon acoustic oscillations, BAO. These are periodic fluctuations in the density of visible baryonic matter, caused by acoustic waves oscillating in the photon-baryon fluid before recombination. The exact scale and amplitude of BAO measured by satellites like Planck and experiments like BOSS rely on the gravitational backdrop provided by dark matter, which influences how these waves evolve over time. Observations of strong gravitational lensing, where the light from a distant object is bent into multiple images or arcs by a foreground mass, allow astronomers to map dark matter on subgalactic scales. By examining how lensing distortions occur around individual galaxies, researchers can infer the presence of dark matter clumps or subhalos that do not contain stars or gas. These dark substructures are predicted by the cold dark matter paradigm and have been detected, giving insight into the granularity and distribution of dark matter beyond smooth halos. Large-scale cosmological simulations, such as the Millennium Simulation and Illustris, have successfully incorporated dark matter to reproduce the observed universe's structure from the smallest dwarf galaxies to the largest galaxy clusters. These simulations start from initial conditions based on the cosmic microwave background data and evolve dark matter and baryonic matter forward in time, replicating filamentary cosmic web structures. The close agreement between simulated and observed galaxy distributions strengthens the theoretical framework that places dark matter at the heart of structure formation. Cosmological surveys detecting weak gravitational lensing, which causes subtle distortions in the shapes of millions of distant galaxies, provide statistical measures of dark matter distribution. Weak lensing studies have revealed that dark matter halos not only exist around individual galaxies, but also form an interconnected web extending throughout the universe. By comparing these observations with predictions from different dark matter models, scientists can constrain characteristics such as dark matter particle mass and its degree of clustering. High-energy astrophysical observations provide further indirect constraints on dark matter properties. For example, gamma-ray telescopes like Fermi-Lat search for potential signals from dark matter particle annihilations or decays, particularly in regions of high dark matter density such as the galactic center. While no definitive detection has been made, these observations place upper limits on interaction cross-sections and decay lifetimes, helping narrow down the plausible parameter space for dark matter candidates. The study of primordial black holes as a potential component of dark matter explores whether black holes formed in the early universe could account for some or all dark matter. Observational limits based on gravitational lensing surveys, cosmic microwave background anisotropies, and gravitational wave detections from LIGO-Virgo collaborations restrict the abundance and mass ranges of such black holes. Current evidence suggests that primordial black holes are unlikely to comprise the majority of dark matter, though they might contribute in minor amounts. On galactic scales, the detailed kinematic studies of neutral hydrogen gas clouds using 21-centimeter radio observations provide precise rotation curves extending far beyond the visible stellar disk. These measurements consistently show that orbital velocities remain stable or even rise at large radii, contradicting expectations if only visible matter produced gravity. The availability of large HI surveys, like those from the Very Large Array (VLA) and the upcoming Square Kilometre Array (SKA), ensures that dark matter's gravitational effects can be studied in unprecedented detail across many types of galaxies. Dark matter halos are thought to be roughly spherical or elliptical, but do not exhibit the same complex substructures associated with baryonic matter, such as disks, arms, or bars. This difference arises because dark matter does not experience dissipative forces like friction or radiative cooling, preventing it from collapsing into thin structures. The result is that dark matter forms a smoother, more diffuse gravitational background that underpins the more irregular and dynamic shapes of visible galaxies. Tests of alternative dark matter particle models, such as warm dark matter, examine scenarios where dark matter particles have small but non-negligible thermal velocities. These models attempt to address challenges like the missing satellites problem, which notes that cold dark matter simulations predict more small-scale structures than are observed. Observations to date, along with the distribution and properties of dwarf satellite galaxies, impose constraints that favor cold over warm dark matter, but this remains an active area of research. The gravitational influence of dark matter extends even beyond individual galaxies to the scale of superclusters and the great cosmic voids between them. Mapping these regions through galaxy redshift surveys reveals that dark matter helps form the large-scale filamentary pattern of matter, while voids are underdense relative to the cosmic mean. This large-scale structure is consistent with the lambdictum model, which incorporates cold dark matter and a cosmological constant, and matches observations of galaxy clustering statistics. In studying the rotation curves of low surface brightness, LSB galaxies, which have fewer stars and lower densities, scientists find that dark matter dominates almost entirely over visible matter. These galaxies serve as clean probes of dark matter distribution because their baryonic content minimally affects their gravitational dynamics. Rotation curve data from LSB galaxies often reveal dark matter halos with core-like density profiles distinct from the cuspy profile predicted by some NFW fits, introducing important constraints on theoretical dark matter models. Since dark matter does not interact electromagnetically, it does not participate in known chemical reactions or form atoms and molecules. This lack of interaction limits its ability to clump on very small scales and rules out many mechanisms that shape ordinary matter, such as cooling via radiation or pressure forces. Thus, dark matter remains smoothly distributed on small scales, but can gravitationally aggregate into large clumps, underlying the peculiar dual role it plays in cosmological dynamics. The distribution of dark matter within the Milky Way itself has been studied extensively through star kinematics, stellar streams, and gas dynamics. Estimates indicate that the dark matter halo of our galaxy extends at least several 100,000 light-years and contains several 100 billion solar masses, approximately 5 to 10 times the mass of the visible stellar disk and bulge combined. Mapping this distribution is crucial for calibrating dark matter detection experiments on Earth and understanding the local dark matter density where the solar system resides. Gravitational microlensing, where the gravitational field of a dark object briefly magnifies a background star, provides another avenue to study dark matter. While initial expectations considered that massive compact halo objects, machos, like brown dwarfs or faint stars, might comprise significant dark matter, microlensing surveys towards the Large Magellanic Cloud and the galactic bulge showed insufficient event rates to account for all dark matter. These results helped exclude machos as a primary dark matter candidate, supporting the notion that it is non-baryonic. Certain dark matter models suggest interactions among dark matter particles themselves, termed self-interacting dark matter, SIDM, as a way to reconcile some observational discrepancies in galactic cores. SIDM could redistribute dark matter within halos, creating flatter density cores and alleviating tensions with observed rotation curves. Although this idea remains under investigation, current constraints from cluster collisions and weak lensing observations limit the strength and frequency of such dark matter self-interactions. The phenomenon of dark matter annihilation freezeout in the early universe helps explain why dark matter is still abundant today. In models involving WIMPs, particles and antiparticles annihilated each other at high temperatures until the universe cooled sufficiently for annihilation rates to drop below the expansion rate, leaving a residual abundance, a relic density. This mechanism ties predictions of dark matter particle properties to cosmological observations, such as the measured density of dark matter from the CMB. Efforts to detect dark matter through indirect methods include searching for neutrinos generated by dark matter annihilations within celestial bodies. Dark matter particles may accumulate in massive objects like the Sun or Earth by scattering off nuclei and becoming gravitationally trapped. Detectors such as IceCube monitor for high-energy neutrinos emerging from the Sun's core, with limits from these searches helping constrain the properties of dark matter particles. The widespread distribution of dark matter also shapes the process of galaxy mergers and interactions. During collisions, dark matter halos of merging galaxies can pass through each other with minimal interaction, in contrast to the behavior of interstellar gas clouds that collide and shock heat. This difference in interaction dynamics affects the morphological evolution of galaxies and is observable in systems like the Bullet Cluster, whose detailed observations offer empirical insight into dark matter's collisionless nature. Because dark matter does not emit light, its presence can influence the process of cosmic reionization indirectly. By assembling gravitational wells that attract baryonic gas, dark matter halos enable the formation of the first stars and galaxies, whose energetic radiation later reionizes hydrogen in the intergalactic medium. Measurements of the timing and progression of reionization from the CMB and quasar absorption spectra can thus be linked back to the growth of dark matter structures in the earliest epochs. In addition to the gravitational effects visible on large scales, dark matter is expected to have a velocity distribution function that shapes its behavior within halos. This velocity distribution influences the capture rate of dark matter particles in astrophysical objects and impacts direct and indirect detection strategies on Earth. Observations and simulations suggest a roughly Maxwellian velocity distribution in halos like the Milky Way, but localized variations and streams can also exist, informing the design of highly sensitive detectors. While laboratories on Earth have yet to detect dark matter particles, underground experiments continue to improve detection sensitivity by reducing radioactive background noise and enhancing target mass. These direct detection experiments aim to observe nuclear recoils caused by dark matter particles scattering off atomic nuclei. The ongoing aspirations of detectors like XENO, NNT, LZ, and Super-CDMS represent the forefront of probing weakly interacting particles hypothesized to constitute dark matter. Data from the cosmic microwave background provides key constraints on neutrino masses, which in turn relate to possible roles of neutrinos in dark matter composition. Neutrinos are known to exist with tiny masses, but their high velocities prevent them from clustering on small scales effectively, classifying them as hot dark matter. Precision measurements of CMB anisotropy and large-scale structure impose upper limits on the neutrino mass sum, confirming that neutrinos cannot account for the majority of dark matter. The early universe's conditions and phase transitions shaped the abundance and nature of dark matter candidates. Processes like symmetry breaking and freeze-in production mechanisms postulated in early cosmology can generate particles that behave as dark matter today. Research in this area bridges high-energy particle physics and cosmology, tying fundamental physics with the observed large-scale properties of dark matter. Finally, the growth history of supermassive black holes is influenced indirectly by dark matter halos. The gravitational potential, wells created by dark matter halos, funnel gas into galactic centers, fueling the growth of central black holes. Observations correlating black hole masses and host galaxy properties are consistent with models linking dark matter halo formation and baryonic processes, emphasizing the interconnected roles dark matter plays across vastly different cosmic scales. Dark matter plays a critical role in the hierarchical clustering process of cosmic structure formation, where small clumps of matter merge over time to form progressively larger systems such as galaxies, groups, and clusters. This bottom-up growth model is supported by observational evidence from galaxy surveys and cosmological simulations, demonstrating that dark matter halos initially formed at small scales and then merged to assemble the large structures we observe today. The gravitational domination of dark matter during this process is essential because it dictates how and when baryonic matter can cool and form stars within these gravitational wells. Further observational support for dark matter arises from precise measurements of the bullet cluster and other merging clusters using multiple wavelengths including optical, X-ray, and radio. These combined datasets reveal the offset between the centroid of luminous, baryonic gas and the gravitational potential mapped through lensing, providing one of the clearest empirical distinctions between dark matter and ordinary matter behavior. This spatial segregation constrains dark matter's self-interaction cross-section to be very low, reinforcing its collisionless character under typical astrophysical conditions. Dark matter also influences the shape and orientation of galaxies through its halos. Observations suggest a correlation between the alignment of galactic disks and the axes of their surrounding dark matter halos, indicating that angular momentum transfer occurred during the collapse and accretion phases. Studies of polar ring galaxies and warped disks provide indirect evidence about halo shapes and the role dark matter played in sculpting galactic morphology over cosmic timescales. High-resolution simulations indicate that dark matter subhalos, smaller concentrations of dark matter within larger halos, survive tidal disruption and form gravitationally bound structures that do not necessarily contain stars or gas. These subhalos influence the dynamics and evolution of satellite galaxies and globular clusters, and provide testable predictions for the small-scale distribution of dark matter. Observational programs searching for lensing signatures and stellar stream perturbations have begun to identify candidates for these dark substructures. Cosmological measurements of the matter power spectrum, which quantifies the distribution of density fluctuations across different scales, are sensitive to the properties of dark matter. In particular, variations in the slope and amplitude of the power spectrum derived from galaxy clustering and Lyman alpha forest observations constrain dark matter particle mass and velocity dispersion. This approach allows astronomers to exclude certain dark matter candidates while favoring others based on consistent replication of observed large and small-scale structures. The study of globular clusters near the centers of galaxies offers additional insights into dark matter presence and distribution. Although these clusters predominantly consist of stars, their orbital behavior within the overall galactic potential, shaped largely by dark matter, reflects the mass distribution in the innermost regions of galaxies. Contrary to early expectations, studies suggest dark matter density may decline or form cores in such central environments, initiating debates about the interplay between baryonic feedback and dark matter dynamics. In examining the cosmic infrared background alongside the cosmic microwave background, astronomers detect signatures indirectly related to dark matter through the formation history of early galaxies and quasars. This diffuse background radiation results from accumulated light emitted by distant, unresolved sources, whose assembly depends critically on dark matter halo mass functions and merger histories. Modeling these backgrounds provides constraints on the timing and efficiency of structure formation processes shaped by dark matter. Dark matter impacts galaxy evolution by shaping the potential wells into which gas accretes, influencing star formation rates and chemical enrichment over cosmic time. Halo mass and concentration affect gas cooling times and feedback mechanisms from supernovae and active galactic nuclei, linking dark matter properties to observable features such as galaxy color distributions, morphology, and stellar populations. Detailed studies combining simulations and observations highlight dark matter's indirect yet vital role in the complex baryonic processes governing galaxy formation. The search for primordial density fluctuations imprinted by inflation involves careful analysis of dark matter's gravitational effects on matter clustering. Measurements of the CMB by the Wilkinson Microwave Anisotropy Probe, WMAP, and Planck satellites have provided precise initial conditions for cosmic structure growth, with dark matter serving as the dominant component amplifying these primordial perturbations. These results align with the lambda-cold dark matter, lambdictum, model, which remains the most successful framework incorporating dark matter into cosmic evolution. Dark matter's influence extends to the dynamics of galaxy groups, where the combined mass of dark matter halos governs the virialization and long-term stability of these systems. Velocity dispersion and galaxy member counts within groups reveal mass-to-light ratios far exceeding those expected from visible matter alone, underlining dark matter's dominance at intermediate scales between single galaxies and massive clusters. These systems provide laboratories for studying dark matter interactions on scales smaller than clusters, but larger than isolated galaxies. Advanced gravitational lensing techniques, such as flexion mapping, enhance understanding of dark matter by detecting higher-order distortions in background galaxy images. Flexion provides sensitive probes of small-scale mass irregularities and gradients within dark matter halos, allowing for refined mass modeling. This method is improving constraints on substructure abundance and dark matter distribution within galaxy clusters and around individual galaxies. In satellite galaxy alignments, astronomers observe anisotropic distributions of dwarf satellites around larger galaxies, suggesting that dark matter filaments guide their accretion. This patterned infall accords with cosmological simulations, where dark matter's cosmic web dictates the preferred directions for satellite accretion and the anisotropic growth of halos. Satellite kinematics and spatial distributions thus serve as tracers for the unseen dark matter structures permeating the universe. The phenomenon of dark matter heating addresses how dark matter particles dynamically interact with stars and gas within galaxies, potentially exchanging energy through gravitational encounters. Over long timescales, this process may influence the structure and evolution of galactic disks and bulges. While dark matter is fundamentally collisionless, collective gravitational effects can impart subtle but measurable dynamical footprints on visible matter distributions. Theoretical exploration of sterile neutrinos, hypothetical particles extending the known neutrino family, provide alternative interpretations for certain astrophysical observations consistent with dark matter. These particles would interact gravitationally and via the weak force, but avoid electromagnetic interaction, fitting dark matter's defining characteristics. X-ray observations searching for characteristic decay lines, such as the claimed 3.5 keV line, provide tentative but controversial evidence that continues to motivate study of neutrino-like dark matter candidates. Dark matter's role in galaxy cluster cooling flows is subtle but significant. The gas in cluster centers tends to cool radiatively, yet observed cooling rates are lower than classical predictions, a situation known as the cooling flow problem. Dark matter's gravitational potential affects gas density and pressure profiles, while feedback mechanisms linked to dark matter halo dynamics modulate energy input, offering explanations consistent with multi-wavelength observations, including radio and X-ray data. Studies of velocity anisotropy within dark matter halos enhance understanding of their formation history and particle behavior. Simulated halos exhibit radial variations in velocity dispersion, reflecting the complex processes during collapse and merging events. Observational efforts to estimate velocity anisotropy through galaxy motions and lensing can test simulation predictions and constrain properties of dark matter particle interactions. The detection of the Sunyaev-Zeldovich (SZ) effect, a distortion of the cosmic microwave background caused by hot gas in galaxy clusters, indirectly probes the interplay between ionized baryons and dark matter gravitational potentials. Measurements from observatories like the Atacama Cosmology Telescope provide cluster mass estimates sensitive to dark matter distributions. Combined SZ, X-ray, and lensing data offer comprehensive insights into the mass balance and thermodynamic state of clusters shaped by dark matter. Ultra-faint dwarf galaxies recently discovered in the local group exhibit some of the highest known dark matter to baryonic matter ratios, sometimes exceeding several hundred or even 1,000. These galaxies, often containing just a few hundred to a few thousand stars, serve as crucial tests for dark matter models, particularly in assessing the presence of small-scale structures predicted by cold dark matter theories. Their extreme mass-to-light ratios also challenge understanding of star formation under the influence of dominant dark matter. Detailed investigations of dark matter annihilation signatures in cosmic ray data provide complementary indirect detection approaches. Instruments aboard satellites such as AM-2 analyze positrons, antiprotons, and other particles potentially produced by dark matter interactions. Although astrophysical sources contribute to observed signals, improved statistical analysis refines exclusion limits and guides theoretical modeling of dark matter annihilation cross-sections. Gravitational wave astronomy, emerging as a powerful new observational window, may eventually illuminate dark matter properties. Potential signals include mergers of primordial black holes, which could represent some dark matter fraction, or perturbations caused by dark matter clumps interacting with compact objects. Although current detections remain unrelated to dark matter, future enhanced sensitivity and event statistics might probe these exotic scenarios. Dark matter's influence is not limited to galactic and cosmological scales, but extends to the dynamics of the earliest molecular clouds where first-generation stars formed. By providing gravitational potential wells, dark matter halos influence the collapse timescales and fragmentation processes that shaped population III star formation. These earliest stars affected subsequent chemical evolution, reionization, and the initial phases of galaxy assembly. Astrophysicists employ novel machine learning techniques to analyze large datasets from sky surveys, aiming to identify subtle dark matter signals within complex observations. These methods enhance pattern recognition and model fitting capabilities, enabling more precise mapping of dark matter distributions and substructures. Such technological advances accelerate data-driven understanding of dark matter's astrophysical footprint. The feedback from active galactic nuclei, AGN, is thought to couple strongly to surrounding dark matter halos, influencing galaxy evolution by regulating gas inflow and star formation. Observations of AGN outflows and their spatial correlation with halo properties suggest a feedback loop where dark matter indirectly modulates baryonic processes. This link is a key component in semi-analytic models of galaxy and cluster formation within lambdictum cosmology. The timing argument applied to the local group, which consists primarily of the Milky Way and Andromeda galaxies, estimates combined mass through their relative motions. Results confirm that the total mass substantially exceeds the visible content, consistent with a large dark matter component. Continued measurements, refining the orbital parameters of satellite and member galaxies, enhance constraints on local dark matter distributions. Examinations of the intrinsic alignments of galaxies, correlations in orientation independent of gravitational lensing, provide insight into how dark matter shapes galaxy formation and angular momentum acquisition. These alignments must be carefully modeled in cosmological weak lensing analyses to reduce systematic errors, underscoring dark matter's role in affecting both intrinsic and lensing-induced distortions. Studies of low metallicity, stars in the galactic halo probe conditions influenced by early dark matter halos, and subsequent chemical enrichment. The distribution and dynamics of these ancient stellar populations trace the assembly history of the Milky Way's dark matter halo, offering fossil records of dark matter-driven accretion events and mergers. Upcoming observatories such as the Vera C. Rubin Observatory and the Euclid Space Telescope will vastly increase the depth and coverage of sky surveys sensitive to dark matter through lensing and galaxy clustering. These programs aim to produce high-precision three-dimensional maps of dark matter, enabling unprecedented tests of cosmological models and dark matter theories, potentially revealing new physics. In particle physics laboratories, collider experiments at the Large Hadron Collider, LHC, search for missing energy signatures that could indicate the production of dark matter candidates in high-energy collisions. While no definitive evidence has been found, continued data collection and analysis refine constraints on possible dark sector particles interacting weakly with standard model particles. Dark matter's presence influences the detailed shape of baryonic acoustic oscillation peaks in galaxy correlation functions. The position and amplitude of these peaks, measured by surveys such as BOSS, rely on the interplay between photon-baryon fluid dynamics and dark matter's gravitational influence. Accurate measurement of BAO contributes critical distance scales for cosmological parameter estimation in dark energy and dark matter studies. Studies of tidal streams formed by disrupted satellite galaxies or globular clusters provide high-resolution probes of the dark matter halo's granularity. Gaps and perturbations in these streams are consistent with encounters with dark matter subhalos, offering empirical evidence for the small-scale structure predicted by theoretical dark matter models. Such stellar streams thus become sensitive tools to map otherwise invisible dark matter clumps. The analysis of dark matter halo concentration parameters across different mass scales reveals correlations with formation time and environment. Early forming halos tend to be more concentrated, influencing galaxy formation efficiency. Observational constraints linking concentration to halo mass help refine semi-analytic and hydrodynamical models incorporating dark matter physics. The interaction of cosmic rays with the interstellar medium is influenced indirectly by dark matter through the regulation of star formation and magnetic fields. This impact affects the propagation and spectrum of cosmic rays detected on Earth, offering a subtle but meaningful connection between dark matter's gravitational framework and high-energy astrophysical phenomena. The abundance and spatial distribution of satellite galaxies around massive galaxies, such as the Milky Way and Andromeda, provide critical tests for small-scale dark matter predictions. Discrepancies like the too-big-to-fail problem highlight tensions between observed satellite galaxy properties and cold dark matter simulations, prompting refinements in baryonic physics modeling and alternative dark matter scenarios. Gravitational redshift measurements of galaxies in clusters may provide supplementary information on the depth of the gravitational potentials shaped by dark matter. By analyzing spectral line shifts induced by cluster gravity wells, researchers can independently verify mass distributions inferred from lensing and dynamics, enhancing our understanding of dark matter's role in cluster environments. The detection of exoplanets and their orbital dynamics around stars could one day inform indirect constraints on local dark matter density through subtle gravitational effects or dark matter capture within planetary interiors. While currently speculative, future advancements in exoplanet precision measurements might offer novel astrophysical laboratories linked to dark matter phenomena. Studies focusing on the environmental dependence of galaxy properties reveal that dark matter halos in denser regions tend to assemble earlier and have distinct merger histories compared to those in voids. This environmental effect modulates star formation history, morphology, and gas content, illustrating the complex connection between dark matter halo cosmology and visible galaxy properties. Finally, the concept of dark disks, hypothetical, dense planar dark matter structures aligned with galactic disks, has been explored as a potential feature in some simulations, including dissipative dark matter components. While current observational evidence for such disks is lacking, continued kinematic studies of stellar populations and dark matter distribution may detect or constrain these structures, further refining our understanding of dark matter's diversity. Advanced cosmological measurements leverage the anisotropies in the cosmic microwave background, CMB, polarization patterns to further elucidate dark matter properties. Instruments like the Atacama Cosmology Telescope and the South Pole Telescope have measured subtle polarization signals known as E modes and B modes, whose statistical distribution depends on the total matter content, including dark matter. These polarization anisotropies help break degeneracies in cosmological parameters and provide precise constraints on the dark matter density, complementing temperature-based CMB analyses. Dark matter's influence extends to gravitational redshift within galactic halos, where photons escaping a gravitational potential well lose energy, shifting their frequency toward the red. Observations of such redshifts for stars and gas at various radii from galactic centers enable indirect mapping of the underlying gravitational potential, shaped predominantly by dark matter. This approach supplements traditional mass estimations by offering direct insight into gravitational effects without relying solely on orbital kinematics. The Bullet Cluster represents a valuable natural laboratory for constraining the cross-section of dark matter self-interactions, setting upper limits on the strength and frequency of collisions between dark matter particles. Combined analyses from multiple merging galaxy clusters indicate that dark matter behaves approximately collisionlessly on astrophysical scales, with interaction cross-sections less than around 1 square centimeter per gram. Such constraints help rule out classes of self-interacting dark matter models that would otherwise significantly alter halo shapes and collision dynamics. Observations of ultra-diffuse galaxies, galaxies with the luminosity of dwarfs but the spatial extent of the Milky Way, have revealed that some of these systems are dominated by dark matter, while others have surprisingly low dark matter content. The diversity in dark matter fraction among ultra-diffuse galaxies challenges straightforward predictions from galaxy formation theories and suggests complex baryon-dark matter interplay during evolutionary processes. Studies employing both stellar dynamics and gravitational lensing aim to clarify this puzzling diversity and its implications for dark matter distribution models. The characterization of the cosmic neutrino background connects indirectly to dark matter studies, as massive neutrinos contribute a small but non-negligible fraction of the total matter density. While neutrinos remain relativistic particles during much of cosmic history, their transition to non-relativistic speeds affects the growth of cosmic structures subtly. Precision cosmology constrains neutrino masses and number densities, thus delimiting neutrino contributions to dark matter and refining the total dark matter budget. Dark matter's gravitational wells accelerate the infall of gas during the epoch of recombination, directly affecting the acoustic peaks observed in the cosmic microwave background power spectrum. The precise heights and positions of these peaks are sensitive to the baryon-to-dark matter ratio, allowing cosmologists to tightly constrain these quantities. Variations in peak features thus offer diagnostic tools for refining dark matter density estimates and testing theoretical models against observation. Laboratory tests of dark matter alternatives include experiments searching for axions, hypothetical low-mass bosons proposed as dark matter candidates. Detection strategies involve resonant cavities exposed to strong magnetic fields, aiming to convert axions into photons via the Primakov effect. Experiments such as ADMX, Axion Dark Matter E-experiment, have reached sensitivities capable of probing realistic axion parameter spaces, though discovery remains elusive. Dark matter substructures within galactic halos induce characteristic distortions in pulsar timing measurements. As compact dark matter clumps pass between Earth and pulsars, they can perturb the arrival times of radio pulses in a predictable manner. Monitoring these timing residuals across pulsar networks could one day provide a novel channel to detect or constrain dark matter clumpiness at small scales, complementary to electromagnetic observations. The discovery and analysis of high-velocity stars escaping the Milky Way contribute to understanding the gravitational potential shaped by dark matter. These hypervelocity stars, often ejected by interactions with the central supermassive black hole or dynamic encounters, trace trajectories influenced by the full mass distribution, including the extended dark matter halo. Modeling their orbits helps constrain the shape and extent of the galactic dark matter halo far from the luminous disk. Dark matter's contribution to cosmic shear measurements, the weak gravitational lensing distortion of distant galaxies, provides a statistical method to test the large-scale homogeneity and isotropy of dark matter distribution. Large survey projects like the Hyper-Suprime-Cam (HSC) survey analyze millions of galaxy shapes to map gravitational lensing signals over vast sky areas. These analyses help verify the consistency of dark matter clustering across scales and epochs, offering a direct cosmological probe independent of visible matter. The role of dark matter in the Sunyaev-Zeldovich (SZ) power spectrum emerges from its effect on the gas pressure distribution in galaxy clusters. Clusters with more concentrated dark matter halos compress intracluster gas to higher densities and temperatures, altering the amplitude and shape of the SZ spectrum, which is observable with millimeter-wave telescopes. Detailed modeling of these effects allows constraints on cluster mass functions, and by extension dark matter halo properties across cosmic time. Some models of dark matter predict the existence of dark photons, analogous messenger particles mediating forces within a hidden dark sector. These hypothetical particles could induce rare interactions between dark matter particles or weakly couple to ordinary matter, potentially detectable through precision atomic spectroscopy or missing energy signals in particle colliders. Experimental efforts exploring these weak portals aim to expand the search beyond traditional WIMP frameworks. Gravitational wave signals from neutron star mergers may eventually help probe dark matter effects indirectly. Dark matter concentrating within neutron stars could alter their mass-radius relationship and tidal deformability, influencing gravitational waveforms detected by LIGO and Virgo. Future high-precision gravitational wave observations could thus provide complementary constraints on dark matter accumulation and particle properties within compact objects. Galactic rotation curves from dwarf irregular galaxies extend our knowledge of dark matter's influence in low-mass environments. These galaxies, with irregular morphologies and active star formation, display flat or rising rotation curves inconsistent with baryonic-dominated mass distributions. Their dynamics highlight that dark matter is a crucial gravitational component even in turbulent, irregular systems, reinforcing the universality of dark matter halos across galaxy types. Cosmological parameters inferred from combined analyses of large-scale structure, supernovae, and CMB data place stringent limits on the amount and behavior of dark matter throughout cosmic history. Using Bayesian frameworks, cosmologists can jointly constrain dark matter properties such as mass density, clustering behavior, and interaction rates with normal matter or itself. These integrated constraints provide high-precision parameters that form inputs to simulations and theoretical models. Certain hypothetical dark matter candidates, such as fuzzy dark matter, propose ultralight bosons with masses around 10^2 eV that would suppress small-scale structure formation through quantum wave effects. This can potentially resolve discrepancies like the core-cusp problem in dwarf galaxies by inducing coherent dark matter density cores rather than cusps. Although still under active investigation, astrophysical surveys and Lyman alpha forest data currently provide stringent constraints limiting the fraction of such ultralight particles in the total dark matter population. Studies of galaxy cluster mass functions over time reveal how dark matter controls the abundance and growth of the most massive structures in the universe. X-ray and lensing observations chart how the number density of clusters varies with redshift, which in turn reflects the rate of dark matter halo formation and accretion. Comparisons with lambdictum models confirm the predicted hierarchical growth shaped by dark matter gravitational collapse. The lack of observed dark matter decay signatures in the X-ray and gamma-ray backgrounds limits possible decay channels for dark matter particles, constraining their lifetime to be much longer than the age of the universe. This stability is essential for dark matter to persist and influence cosmic structure formation over billions of years. Indirect detection experiments continuously monitor for faint excesses or spectral lines that would signal rare decay events. Recent deep observations of neutral hydrogen gas in galaxy outskirts using 21 cm mapping reveal complex velocity fields shaped not only by baryonic matter, but also by underlying dark matter halos. These detailed kinematic maps provide insight into halo shapes and can detect warps or asymmetries induced by interactions or substructure. Such studies expand understanding of the interplay between dark matter and gas on the scales where star formation may be triggered or suppressed. The modeling of tidal interactions between satellite galaxies and their hosts benefits from accurately characterizing the mass and density profile of the host's dark matter halo. Simulations incorporating realistic dark matter potentials show how satellites lose mass and structural integrity over time, contributing stellar streams and diffuse halos. Observational confirmation of these features informs both dark matter halo properties and satellite galaxy evolution. The cosmic web filaments traced by weak gravitational lensing and galaxy surveys act as corridors that channel matter into dark matter halos. These filaments, predominantly composed of dark matter, funnel gas and galaxies toward clusters along preferential directions, driving anisotropic growth. The study of filament properties and their evolution enables designers of surveys and simulations to probe dark matter connectivity on intermediate cosmic scales. Within the Milky Way, the presence of dark matter subhalos can create gaps and clumps in stellar streams formed by tidally disrupted satellites. Detailed mapping of streams such as the GD-1 and Palomar 5 streams using Gaia mission data reveals such perturbations consistent with encounters with dark matter clumps as predicted by lambdictum simulations. These observations provide a unique, direct probe into the granularity and distribution of dark matter on small scales. The Lyman alpha forest, the absorption features in the spectra of distant quasars caused by intervening intergalactic gas, serves as a probe of dark matter distribution on scales smaller than galaxies. The clustering and temperature of this diffuse gas are influenced by the gravitational potential dominated by dark matter. Measurements of the forest constrain the free-streaming length of dark matter particles, effectively limiting warm dark matter mass ranges and helping to refine particle models. Data from the Dark Energy Spectroscopic Instrument, DESI, survey will enhance the precision mapping of the three-dimensional distribution of galaxies, enabling detailed studies of dark matter clustering evolution. By extending redshift measurements to billions of light-years, DESI allows examination of the cosmic structure growth rate tied to dark matter halo formation over time. Such results aid in distinguishing between competing models of dark matter and dark energy. The combination of strong and weak gravitational lensing in galaxy clusters offers a multi-scale approach to modeling dark matter halos. Strong lensing captures the inner dense core regions by producing multiple images and arcs, while weak lensing delineates the more diffuse outskirts. Together, these analyses reveal density profiles and substructure abundances, providing increasingly accurate mass maps that underpin studies of dark matter physics. The phenomenon of dynamical friction, wherein moving objects lose momentum due to gravitational interactions with surrounding matter, is influenced by the presence of dark matter halos. For example, satellite galaxies spiraling toward a host galaxy experience drag predominantly through interactions with dark matter particles. Understanding this effect is essential for modeling galaxy mergers and satellite survival times in dark matter-dominated environments. Dark matter could influence early black hole seed formation via the accretion of dark matter particles, or through their gravitational role, enabling efficient gas collapse. Some scenarios suggest dark matter density peaks may act as sites for enhanced baryonic cooling and black hole seed formation, potentially explaining the existence of supermassive black holes at high redshifts. While such ideas remain under active research, the interplay between dark matter cusps and baryonic physics is a significant aspect of early structure theories. The search for dark matter-induced gamma-ray excesses near dwarf spheroidal galaxies, which are dark matter-rich but low in astrophysical backgrounds, remains an important strategy for indirect detection. Data from Fermi Gamma-Ray Space Telescope is analyzed to identify such signals arising from dark matter annihilation or decay. Though no confirmed detections exist, the stringent upper limits derived help rule out high annihilation cross-sections and inform particle physics models. Peculiar velocities of galaxies, deviations from the uniform Hubble flow, reflect gravitational pull caused by large-scale matter overdensities, including dark matter. Large surveys map these velocities to reconstruct the matter density field, providing independent validation of dark matter's role in structure growth. Comparing observed velocity fields with simulations constrains cosmological models and dark matter clustering. The presence of dark matter can be studied through the dynamics of thick stellar disks in spiral galaxies. These extended disk components interact gravitationally with the dark matter halo, and their vertical velocity dispersions and scale heights encode information about the background gravitational potential. Detailed modeling of thick disk kinematics assists in constraining dark matter halo shapes and densities in the inner regions of galaxies. The influence of dark matter on the intergalactic magnetic fields, though indirect, stems from its gravitational shaping of large-scale structures, where plasma processes generate and amplify magnetic fields. The filamentary dark matter scaffolding guides gas flows and shock fronts that contribute to magnetic field growth in cosmic environments. Understanding the role of dark matter in magnetic field evolution links gravitational and plasma astrophysics within the cosmic context. Finally, flat galaxy rotation curves, first noted nearly a century ago, remain one of the clearest empirical signatures necessitating dark matter in current astrophysics. The consistent observation that rotational velocities remain constant or increase at large radii, where visible matter declines, underpins the fundamental requirement for a dominant, non-luminous mass component shaping galactic dynamics. This empirical fact continues to guide theoretical and observational dark matter inquiries. In the early 1930s, Swiss astronomer Fritz Zwicky made the first compelling case for what would later be called dark matter while studying the Coma galaxy cluster. By measuring the velocities of individual galaxies moving within the cluster, Zwicky applied the virial theorem and found that the visible matter, stars and gas, could not account for the high speeds observed. He concluded that there must be a substantial amount of unseen mass exerting gravitational influence to prevent the cluster from dispersing. Zwicky coined this missing mass Dunkelmaterei, meaning dark matter, marking the first scientific proposal of its existence. Despite Zwicky's groundbreaking insight, his conclusions were initially met with skepticism, partly because observational techniques were still developing and alternative explanations, such as measurement errors, were considered. For several decades, astronomers largely focused on visible matter and considered normal baryonic matter sufficient to explain galaxy dynamics. However, in the 1970s, a new era of precision measurements reignited interest in hidden mass as Vera Rubin and Kent Ford conducted detailed studies of the rotation curves of spiral galaxies. Rubin and Ford observed that stars in the outer regions of galaxies were orbiting much faster than expected, if only the visible stars and gas contributed to the galaxy's gravitational pull. According to Newtonian dynamics, orbital velocities should decrease with distance from the galactic center, much like planets in the solar system. Instead, Rubin's rotation curves remained flat or even rose at large radii, implying the presence of an extended, invisible halo of mass encompassing the galaxies, now strongly supporting the dark matter hypothesis. Parallel to optical observations, radio telescopes provided valuable data by detecting the 21-centimeter emission line of neutral hydrogen gas in galaxies. Scaling of these measurements consistently confirmed that rotational velocities stayed anomalously high far beyond the luminous edges of galaxies. This convergence of optical and radio evidence from multiple independent datasets solidified the notion that dark matter is a pervasive feature of galaxies, not an observational artifact or a quirk of a single galaxy type. In the 1980s and 1990s, gravitational lensing emerged as a powerful, independent tool for probing dark matter. This phenomenon occurs when massive objects, such as galaxy clusters, bend and magnify the light from more distant background galaxies. By analyzing the distortions and multiple images produced, astronomers could map the distribution of mass, often revealing concentrations far exceeding the amount of visible matter. These lensing studies provided compelling proof that most of the mass in such clusters is unseen but detectable through its gravitational effects. Another key milestone in the historical development of dark matter was the detailed study of the cosmic microwave background, CMB, radiation. First detected in 1965 and later mapped in exquisite precision by satellites such as COBE, WMAP, and Planck. The tiny fluctuations in the CMB encode information about the early universe and its composition. The patterns and amplitudes of these fluctuations could only be explained by including a significant amount of non-baryonic dark matter in the cosmological models, further integrating dark matter into the framework of modern cosmology. In addition to astronomical observations, simulations of cosmic structure formation played a critical role in validating the dark matter paradigm. Computer models incorporating only ordinary matter failed to reproduce the observed large-scale structure of the universe, such as the web-like distribution of galaxies and clusters. Including dark matter allowed simulations to replicate these features remarkably well, providing strong indirect support for its existence and properties, such as being cold and collisionless on cosmic scales. The evolution of the dark matter concept also reflects advancements in particle physics, as scientists attempted to identify candidate particles that could make up the invisible mass. Early assumptions focused on ordinary matter in forms like faint stars, brown dwarfs, or gas clouds, collectively termed massive astrophysical compact halo objects, MACHOs. However, searches for MACHOs via gravitational microlensing yielded insufficient detections to account for the missing mass, steering the scientific consensus toward exotic, non-baryonic candidates such as weakly interacting massive particles, WIMPs, and axions. Historical debates throughout the 20th century included alternative explanations for the observed gravitational anomalies, notably modifications to Newtonian gravity or general relativity under low acceleration regimes. These modified Newtonian dynamics, MOND theories, aim to explain galaxy rotation curves without invoking dark matter. While MOND successfully models some galactic scales, it struggles to consistently account for cluster dynamics and cosmological observations, leaving dark matter the more broadly supported framework. The discovery of dark matter has had profound implications beyond understanding galaxy dynamics, influencing the development of the lambda-cold dark matter, lambdictum, model, which combines dark matter and dark energy to explain the expansion and structure of the universe. This concordance model is currently the leading cosmological framework, tightly fitting observational data ranging from supernova surveys and baryon acoustic oscillations to the detailed maps of the cosmic microwave background. Today, dark matter research continues to evolve with increasingly sophisticated observational techniques, such as weak gravitational lensing, surveys that map dark matter distribution over vast cosmic volumes. Deep sky surveys like the Dark Energy Survey and future missions like the Euclid satellite provide detailed three-dimensional reconstructions of dark matter on large scales. These measurements help trace the growth of cosmic structure over time, refining estimates of dark matter's properties and role in the universe's evolution. Furthermore, advances in astronomical instrumentation have allowed for the detection of subtle phenomena linked to dark matter, such as its gravitational influence on dwarf satellite galaxies and stellar streams orbiting the Milky Way. These local tests complement cosmic-scale observations and offer critical clues about the particle nature and interactions of dark matter in various environments. In summary, the discovery and historical development of dark matter is a tale of increasingly precise astronomical observations and theoretical innovation, beginning with Fritz Zwicky's early 20th century cluster studies and culminating in a multi-probe, interdisciplinary scientific effort that continues to transform our understanding of the cosmos. This journey not only revealed a dominant but invisible form of matter, but also reshaped fundamental physics and cosmology in profound and ongoing ways. Building upon early observational foundations, the study of galaxy clusters throughout the mid-20th century added further dimension to the dark matter story. In addition to the Coma cluster studied by Zwicky, astronomers observed discrepancies in velocity dispersions in other clusters, such as the Virgo and Perseus clusters. These studies consistently showed that the mass inferred from galaxy motions far exceeded what could be accounted for by luminous matter alone, reinforcing the need for an unseen mass component on larger scales beyond individual galaxies. The advent of X-ray astronomy in the 1970s provided an important new method for assessing cluster mass through observations of hot intracluster gas. This gas, emitting X-rays due to its high temperature, traces the gravitational potential of the cluster. Detailed measurements revealed that even when including this baryonic component, the total visible mass was insufficient to explain the cluster dynamics, implying an even greater discrepancy and lending further weight to the dark matter hypothesis. A landmark moment in solidifying dark matter's role as a universal phenomenon came with the realization that the mass-to-light ratios of galaxies and clusters varied dramatically from values predicted by standard astrophysics. Typical mass-to-light ratios in stars and gas range roughly between 1 and 10 solar masses per solar luminosity, but observations indicated ratios as high as hundreds for clusters, suggesting the presence of vast amounts of non-luminous matter permeating these cosmic structures. During the 1970s and 1980s, detailed mapping of galaxy rotation curves expanded beyond spiral galaxies to include low surface brightness and elliptical galaxies. These studies found similar evidence for dark matter, showing flat or rising rotation curves extending well beyond visible components. This ubiquity across different galaxy types underlined that dark matter was not restricted to specific morphological classes, but was a widespread cosmic constituent. The development of CCD, charge-coupled device, technology revolutionized optical astronomy from the late 1970s onward, enabling astronomers to obtain higher resolution and more sensitive measurements of galactic and extragalactic objects. This technological leap improved the precision of rotation curve data and mass distribution models, allowing for more robust confirmation of dark matter halos and detailed characterization of their spatial extent and density profiles. By the 1990s, the use of large-scale redshift surveys, such as the CFA redshift survey and the 2-degree field galaxy redshift survey, revealed the cosmic web-like pattern of galaxy clustering on scales of hundreds of millions of light-years. Comparing these observations with dark matter simulations showed that gravitational clustering, driven primarily by dark matter, provided a compelling explanation for the formation and distribution of large-scale structures, further solidifying the concept's cosmological significance. A critical confirmation of the dark matter framework came from precise measurements of the abundance of light elements formed during Big Bang nucleosynthesis, BBN. Observations of primordial helium, deuterium, and lithium abundances indicate limits on the density of ordinary baryonic matter, which falls far short of the total matter density required to explain gravitational phenomena. This disparity confirmed that dark matter cannot be composed principally of normal matter, pointing instead to an exotic, non-baryonic component. The 1998 discovery of the accelerating expansion of the universe introduced a new ingredient to cosmology, dark energy, but it also provided an indirect check on dark matter models. Combining supernova distance measurements with cosmic microwave background and large-scale structure data led to the lambda-cold dark matter, lambdictum, model, where dark matter accounts for roughly 27% of the universe's total energy density, consistent with multiple independent datasets spanning vastly different epochs. Experimental efforts to detect dark matter particles directly have their roots in the late 20th century, as theoretical predictions suggested particles, such as WIMPs, could interact weakly with ordinary matter. These experiments involve ultrasensitive detectors placed deep underground to shield from cosmic rays, aiming to observe rare interactions between dark matter particles and atomic nuclei. While no unambiguous detections have yet been reported, These searches have placed increasingly stringent constraints on possible dark matter properties, guiding theoretical developments and experimental design. During the 2000s, large collaborations utilizing gravitational lensing techniques began conducting weak lensing surveys, measuring subtle distortions in background galaxy shapes over vast swathes of sky. This statistical approach allowed the creation of detailed dark matter maps without relying on assumptions about luminous tracers. Results from the CFHT, LEN-S, and later, the Dark Energy Survey have demonstrated that dark matter structures trace the underlying distribution of galaxies and clusters in exquisite detail. In parallel, detailed studies of dwarf spheroidal galaxies orbiting the Milky Way provided critical local tests of dark matter properties. These faint galaxies exhibit high mass-to-light ratios, indicating they are highly dominated by dark matter. Their relatively simple structure and proximity make them ideal laboratories for constraining the dark matter density profile and testing competing models. The combination of multiple lines of evidence from rotation curves, lensing, CMB anisotropies, structure formation, and particle physics has raised the confidence level for dark matter's existence to a scientific consensus. This multifaceted approach exemplifies how progress in astrophysics relies on diverse observations and theory integration, transforming an early 20th century curiosity into a central pillar of modern cosmology. The elucidation of dark matter's role has also driven improvements in numerical simulations of galaxy formation. By including dark matter halos as initial conditions, simulations now capture key phenomena such as galaxy clustering, halo mergers, and feedback processes shaping the visible universe. These advances have allowed detailed predictions that can be tested via ongoing and future surveys, perpetuating the iterative cycle of observation and theory. In recent years, the Planck satellite's high-precision measurements of the cosmic microwave background have refined estimates of cosmological parameters with extraordinary accuracy. Planck's data confirmed that approximately 84% of total matter in the universe is dark matter, reinforcing earlier WMAP results while improving error margins. This refinement helps constrain both the nature of dark matter and its influence on the universe's earliest phases. The story of dark matter's discovery intertwines closely with the evolution of telescope technology over more than a century. Innovations ranging from photographic plates to space-based observatories have progressively unveiled the universe at all wavelengths, revealing the gravitational footprints of dark matter at scales spanning from individual galaxies to the cosmic web. Each technological milestone has contributed incremental but vital pieces to the overall puzzle. Throughout history, the recognition that dark matter is non-luminous required a conceptual shift in how mass is detected, pivoting from electromagnetic observations to gravitational influence. This paradigm shift broadened the scientific method in astronomy, emphasizing gravitational effects as a primary tool for studying cosmic matter distributions, and leading to new collaborations across disciplines including particle physics, astrophysics, and cosmology. Continued improvements in data quality, analysis techniques, and theoretical frameworks perpetuate the refinement of dark matter models. Researchers now explore properties such as dark matter's self-interactions, mass range, and potential decay signatures, while constantly cross-referencing with the rich observational heritage built over nearly a century of study. This ongoing work seeks to transform dark matter from a phenomenological construct into a well-understood fundamental component of physics. Historically, the interplay between competing theories and accumulating evidence showcases the self-correcting nature of scientific progress. Initial resistance to Zwicky's proposal eventually gave way to acceptance as diverse, independent observations converged on the same conclusion: that the universe harbors vast amounts of matter detectable only through gravity. This transformation exemplifies how scientific consensus develops through rigorous, evidence-based inquiry. In summary, The historical development of dark matter encapsulates a saga of continuous observational breakthroughs, theoretical refinement, and interdisciplinary collaboration. From Zwicky's first measurements in the 1930s to precision cosmology in the 21st century, this journey underscores the power of gravity as a cosmic probe and represents one of the most significant paradigm shifts in our understanding of the universe. The integration of data from X-ray astronomy and gravitational lensing in the late 20th century yielded crucial cross-validation of dark matter distributions in galaxy clusters. This combined approach showed that the hot gas visible in X-rays, which accounts for a significant fraction of cluster baryonic mass, follows gravitational potentials dominated by much larger dark matter halos. Such multi-wavelength studies confirmed that dark matter's presence is not an observational artifact tied to any single method, but a robust astrophysical reality shaping cluster dynamics. Advances in spectroscopic technology during the 1980s allowed for the precise measurement of velocity dispersions within galaxy groups, revealing that dark matter halos exist not just in massive clusters, but also in smaller, less dense environments. Velocity dispersion studies in groups like the Local Group, a collection of galaxies that includes the Milky Way, indicated dark matter's pervasive presence even at relatively low cosmic densities, suggesting its fundamental role across diverse cosmic scales. Observations of the Bullet cluster in the early 2000s provided a dramatic and clear case for separating the effects of ordinary matter and dark matter in a high-energy cosmic collision. In this system, the hot X-ray emitting gas from two colliding clusters was displaced from the bulk of the gravitational mass traced by weak lensing. This displacement conclusively demonstrated that most cluster mass is not in the form of ordinary baryonic matter, and strongly argued against modified gravity theories as the sole explanation. In the development of cosmological models, the introduction of cold dark matter, CDM, in the 1980s was pivotal, distinguishing it from earlier warm and hot dark matter variants. Cold dark matter particles are hypothesized to move slowly compared to the speed of light, allowing them to clump and form the seed structures observed in the universe. Numerical simulations incorporating CDM successfully reproduce hierarchical structure formation, where small objects merge to form larger cosmic structures, matching observations of galaxy clusters and filaments. The identification of the cosmological parameter omega-m, omega matter, representing the total matter density, was significantly refined through combined observations of supernovae, galaxy clustering, and the CMB during the 1990s and early 2000s. These efforts converged on a value near 0.3, implying that around 30% of the total energy density of the universe is matter, but only a fraction of this matter is baryonic. The rest, accounting for roughly 85% of the matter density, is identified as dark matter, highlighting its dominant role in cosmic mass balance. The discovery of so-called ultra-diffuse galaxies, UDGS, in the 21st century added complexity to the understanding of dark matter's role in galactic systems. These galaxies possess very low stellar densities, yet appear to reside in massive dark matter halos comparable to those of much brighter galaxies. Studies of UDGs provide important constraints on how dark matter halos can host vastly different visible structures, thereby testing models of galaxy formation and the interplay between baryons and dark matter. Further evidence for dark matter's distribution comes from observations of galaxy cluster mergers beyond the Bullet cluster, such as the Train Wreck cluster, Able 520, which present more nuanced configurations of dark matter and normal matter. These systems challenge simplified interpretations and encourage refinements in understanding dark matter's collisionless properties and its interactions, or lack thereof, with baryonic components during large-scale energetic events. The advent of the Sloan Digital Sky Survey, SDSS, markedly advanced the statistical characterization of dark matter halos through its comprehensive mapping of millions of galaxies. SDSS data enabled large-scale correlation studies of galaxies with their surrounding dark matter environments, revealing the relationship between galaxy properties, such as type, color, and mass, and the strength and shape of their associated dark matter halos. These findings helped integrate dark matter more firmly into the narrative of galaxy formation and evolution. In the pursuit of identifying dark matter particles, experiments like the Cryogenic Dark Matter Search, CDMS, and Xenon projects began producing stringent upper limits on WIMP interaction cross-sections starting in the early 2000s. Though no definitive signals emerged, these null results informed and constrained theoretical models, progressively narrowing the possible parameter space for viable dark matter candidates and guiding future experiments toward higher sensitivities. Astrophysical measurements of the Lyman alpha forest, absorption lines in the spectra of distant quasars caused by clouds of intergalactic hydrogen, provided another early cosmological probe connected to dark matter. Patterns in the Lyman alpha forest trace the filamentary structure of the intergalactic medium, shaped by underlying dark matter distributions. Careful analysis of this data helped constrain the thermal properties and free-streaming lengths of hypothesized dark matter particles, favoring cold over warm dark matter scenarios. Another historical breakthrough came from considering the role of dark matter in the formation and stability of galactic bars, the elongated central structures seen in many disk galaxies. Computational models showed that the presence of a substantial dark matter halo stabilizes disk galaxies against bar dissolution, providing a dynamical context for observed galactic features. Observations tracking bar frequencies across cosmic time hence indirectly inform the nature and distribution of dark matter in galaxies. In the broader context of galaxy evolution, the realization that dark matter halos capture and preserve baryons against energetic feedback was vital. For example, supernovae and active galactic nuclei, AGN, inject energy into gas at galactic centers, driving outflows that regulate star formation. The gravitational potential wells created by dark matter halos govern whether such feedback can expel gas or if it remains bound, meaning dark matter crucially influences observable galaxy properties and their developmental pathways. The 21st century has also seen the first large-scale all-sky gravitational lensing surveys from space, such as with the Hubble Space Telescope's Cosmos field, offering exceptional resolution for mapping dark matter distributions. These high-definition lensing maps provide unprecedented insights into smaller-scale substructures within halos, allowing astronomers to directly observe the clumpiness predicted by cold dark matter models. Such observations test whether dark matter is smoothly distributed or exhibits significant granular structure. The historical trajectory of dark matter research includes the formulation of the Navarro-Franquite (NFW) profile in the mid-1990s, a now standard mathematical description of how dark matter density varies within halos. This profile, derived from high-resolution N-body simulations, predicts a characteristic cusp-like increase in density toward the halo center. It has served as a crucial theoretical benchmark for comparing observational inferences of density profiles in galaxies and clusters, probing the consistency between simulations and reality. Early measurements of gravitational redshifts in galaxy clusters also contributed to mass determinations, complementing velocity-based methods. Gravitational redshift effects cause wavelengths of photons to be shifted when escaping deep gravitational wells, and their detection in cluster galaxies validated mass estimates consistent with large dark matter halos. While subtle and challenging to measure, these effects added another independent layer supporting dark matter's dominance in cluster mass. The discovery of large-scale voids, vast underdense regions millions of light-years across, emerged from galaxy surveys of the late 20th century and further contextualized dark matter's role in shaping cosmic web structure. The interplay of gravitational attraction by dark matter concentrations and repulsion from expanding voids underlies the observed filamentary and wall-like galaxy distributions. Understanding void dynamics has become an important facet in testing cosmological theories incorporating dark matter. The confirmation of the neutrino's small but finite mass, established in the late 1990s and early 2000s, introduced the concept of a minor hot dark matter component. While neutrinos contribute a small fraction to total dark matter density, their relativistic behavior impacts structure formation at the smallest scales. Accounting for neutrino masses sharpened cosmological models by limiting their influence and reinforcing cold dark matter as the dominant component required to explain observed structures. Research on dark matter subhalos, smaller dark matter clumps orbiting within larger halos, has progressed significantly thanks to both simulations and observations of stellar streams in the Milky Way. Gaps and perturbations detected in tidal streams, remnants of disrupted dwarf galaxies or globular clusters, provide indirect evidence of these invisible substructures predicted by cold dark matter theory. Such discoveries furnish a powerful testbed for dark matter models, especially regarding its interaction cross-sections and clustering behavior. A detailed historical analysis of satellite galaxy distributions around the Milky Way and Andromeda revealed intriguing anisotropies in their spatial arrangement, occasionally referred to as planes of satellites. These patterns challenge some expectations from dark matter simulations, prompting a re-examination of assembly histories and baryonic effects within the dark matter framework. Though not negating dark matter's presence, these findings highlight the complex interplay between halo properties and visible structures. In parallel with advances in astrophysical observations, early theoretical work on supersymmetric extensions of the standard model of particle physics predicted stable particles that could account for dark matter. These theoretical developments motivated experimental searches for particles like neutralinos, heavily influencing dark matter research trajectories from the 1980s onward. Such theoretical experimental synergy exemplifies the interdisciplinary nature of dark matter's historical development. Some of the most precise evidence for dark matter arose from analyses of baryon acoustic oscillations, BAO, imprinted in the large-scale distribution of galaxies. BAO periodic fluctuations in matter density resulting from sound waves in the early universe provide a standard ruler for cosmology. Their measured scale and amplitude, consistent with the presence of non-baryonic dark matter, reinforced conclusions drawn independently from the cosmic microwave background and supernova observations. The increasing sophistication of data analysis techniques, including machine learning algorithms and Bayesian statistical methods, has recently enhanced the capacity to extract dark matter signals from noisy data sets. These methodological improvements have facilitated sharper constraints on dark matter's spatial distribution and properties, ensuring the field continues to refine and update historical conclusions in light of ever-growing data volumes. Lastly, ongoing and planned multi-messenger astronomy campaigns, integrating electromagnetic, gravitational wave, and neutrino observations, are poised to provide novel avenues for investigating dark matter. Though still emerging, these efforts reflect the historical trajectory of dark matter research as continuously evolving, with new observational windows promising further insights into one of modern science's most enduring mysteries. In the 1950s and 1960s, astronomers began to systematically catalog galaxy groups and their velocity dispersions, providing early statistical confirmation that discrepancies in mass estimates were not limited to massive clusters, but also appeared in smaller cosmic structures. These studies indicated that even relatively modest galaxy associations exhibited dynamics that required additional, unseen mass to hold them together gravitationally. This broadened the scale at which dark matter effects were recognized, implying that the missing mass phenomenon was a universal property of cosmic systems and not an anomaly confined to a few exceptional cases. The introduction of radio interferometry techniques allowed astronomers to map the neutral hydrogen gas in galaxies, with unprecedented spatial resolution during the 1970s and 1980s. The high precision of these measurements permitted detailed rotation curves to be constructed out to very large galactic radii, far beyond the optical disk. These extensive rotation curves reinforced the presence of dark matter halos, revealing that mass profiles did not taper off as would be expected if only the luminous matter were present, but instead implied vast, diffuse halos extending several times beyond the visible stellar components. Theoretical advances surrounding the early universe's thermal history provided further context for dark matter's nature and origin. Calculations of freeze-out processes involving hypothetical particles showed how relic abundances of weakly interacting particles could persist from the Big Bang, offering a mechanism for a stable, non-luminous matter component. These insights were instrumental in shifting the dark matter hypothesis toward particle physics models, connecting cosmology with fundamental particle physics and inspiring searches for dark matter beyond gravitational effects alone. In addition to rotation curves and clusters, studies of elliptical galaxies during the late 20th century also contributed important evidence for dark matter. Unlike spirals, elliptical galaxies lack prominent rotating disks, so researchers relied on stellar velocity dispersions and X-ray emission from hot gas to assess mass distributions. These studies consistently suggested the presence of extended dark matter halos similar to those surrounding spirals, implying that dark matter halos are a general feature of galaxy formation independent of morphological type. The development of the excursion set theory in the 1980s provided a formal statistical framework for understanding how dark matter fluctuations collapse to form bound structures across cosmic time. This theoretical tool connected initial density perturbations in the early universe to the hierarchical clustering observed today and influenced the design and interpretation of large-scale numerical simulations. By predicting the abundance and distribution of halo masses, this approach was key to relating cosmological parameters inferred from observations to underlying dark matter properties. Observations of galaxy stellar populations and metallicities have also historically complemented dark matter studies by constraining baryonic mass fractions in galaxies. Since metals are produced by stars, their abundance serves as an indirect tracer of star formation efficiency and retained gas mass. Comparisons between these baryonic indicators and total gravitating mass estimates highlighted large discrepancies, particularly in low-mass galaxies, reinforcing the necessity of substantial unseen mass components in the overall mass budget. In the 1990s, the discovery and characterization of high redshift galaxies with the Hubble Space Telescope provided a window into early galaxy formation in the context of dark matter halos. These distant galaxies, observed less than a few billion years after the Big Bang, appeared consistent with theoretical models where dark matter halos served as gravitational cradles around which baryonic matter condensed. This evidence linked dark matter directly to the earliest observable structures, supporting the theory that dark matter underpins galaxy formation across cosmic epochs. The examination of the correlation function of galaxies, a statistical measure of galaxy clustering on different scales, was a significant development in understanding the large-scale distribution of dark matter. Observational measurements compared with theoretical predictions from numerical dark matter simulations demonstrated excellent agreement, particularly within the lambda-cold dark matter (lambdictum) framework. This correlation function provided a crucial quantitative tool to assess the correspondence between the luminous matter and the underlying dark matter scaffolding of the universe. Refinements in cosmic microwave background polarization measurements during the 2000s, particularly from the WMAP and Planck satellites, added layers of detail validating the dark matter paradigm. Polarization is sensitive to reionization history and the density of various matter components, and the resulting data further constrain the fractions of baryonic and non-baryonic matter. These measurements solidified dark matter's integral role in cosmic evolution, laying to rest alternative models that could not simultaneously explain the temperature and polarization anisotropies observed. During this period, the idea that dark matter could be composed of sterile neutrinos, hypothetical neutrino types not interacting via the weak nuclear force, gained interest as an alternative to WIMPs. Sterile neutrino models suggested a warm dark matter candidate with particle masses in the key V range, which might alleviate some small-scale structure problems observed in the lambdictum model. Though indirect and tentative, constraints on these particles emerged from X-ray observations searching for decay signatures, marking an intersection of astrophysical observation and particle theory in the ongoing quest for dark matter's identity. The role of globular clusters in probing dark matter distribution was explored historically by examining their dynamics and spatial distribution around host galaxies. Though globular clusters are luminous components bound tightly by gravity, their motions and concentrations provided insights into the gravitational potential dominated by dark matter halos at large radii. These studies contributed evidence on the extent and shape of dark matter distributions, particularly in massive elliptical galaxies and galaxy clusters. An important astronomical milestone came with the detection of gravitational microlensing events in the 1990s by collaborations such as MACHO, EROS, and OGLE. These surveys monitored millions of stars to detect transient brightness changes caused by compact objects passing in front of background stars. The low incidence of events found in our galaxy's halo indicated that MACHOs could not make up the majority of dark matter, a result that constrained baryonic dark matter candidates and strengthened the case for non-baryonic dark matter components. The late 20th century refinement of numerical techniques and supercomputing power enabled detailed n-body simulations following billions of dark matter particles through cosmic time. These simulations were groundbreaking in reproducing the rich observed hierarchy from small satellite halos to massive galaxy clusters. The fidelity and scale achieved in these models enabled a more precise comparison with observations, feeding back into the development of consistent dark matter models and deepening understanding of structure formation dynamics. Notably, the historical discovery of dark matter led to the formulation of halo occupation distribution (HOD) models that relate the observed galaxies to their host dark matter halos statistically. Developed in the early 21st century, HOD models bridged the gap between dark matter simulations and galaxy surveys, enabling quantitative predictions of galaxy clustering based on halo properties. These models have become essential tools in interpreting large-scale structure data and refining indirect measures of dark matter distribution. Data from the Hubble Deep Field surveys revolutionized the observational landscape, providing catalogs of thousands of faint galaxies spanning a range of redshifts, which help track evolution of both baryonic matter and dark matter across cosmic time. This compendium of distant galaxies allowed astronomers to statistically validate the timing and scale of hierarchical aggregation in dark matter halos predicted by cosmological simulations, cementing dark matter's role as a fundamental ingredient in cosmic history. Historically, the interplay between observations of the Lyman break galaxies, high redshift, star-forming galaxies identified by their ultraviolet dropout, and dark matter simulations played a significant role in understanding early structure growth. Lyman break galaxies traced dense regions believed to correspond to massive dark matter halos, thus connecting luminous tracers to the underlying dark matter web. This relationship enabled stronger constraints on halo mass functions at early epochs, shaping the timeline of cosmic evolution. Emerging in the 2010s, the technique of intensity mapping, measuring integrated radiation from unresolved sources over large volumes, became a novel method to probe dark matter clustering indirectly. For example, 21 cm intensity mapping of neutral hydrogen over vast cosmic regions provides information on large-scale mass distribution through gravitational influence of dark matter. This approach has added a new dimension to the historical suite of dark matter detection methods, broadening observational probes beyond traditional galaxy surveys. The historical development of alternative dark matter candidates expanded to include models involving self-interacting dark matter, posited to explain small-scale structure anomalies. These models hypothesized that dark matter particles could experience elastic collisions, affecting halo density profiles and satellite galaxy distributions. Though initially developed to address discrepancies in galactic cores, such theories have rooted their origins in accumulating observational puzzles encountered throughout dark matter's study history. In the context of galaxy clusters, the Sunyaev-Zeldovich (SZ) effect, distortions in the cosmic microwave background caused by hot cluster gas, became an important independent probe influencing dark matter research. The SZ effect combined with X-ray observations yields precise measurements of cluster masses and gas fractions, which when compared with lensing data, provide robust constraints on dark matter halo properties. This multifaceted approach has improved cluster mass calibration and sharpened cosmological parameter estimation linked to dark matter. Studies of cosmic shear, the weak gravitational lensing produced by large-scale structure on background galaxies, emerged as a powerful, direct measure of the projected dark matter distribution. Pioneered observationally in the early 2000s, cosmic shear surveys provided statistical maps of mass fluctuations across gigaparsec scales. These measurements confirmed the predictions of lambdictum and allowed ever finer tests of dark matter clustering and potential deviations from standard gravity. Thoughtful historical evaluation of quasar absorption line systems also contributed to understanding dark matter's role in shaping the intergalactic medium. Damped Lyman alpha systems, characterized by high neutral hydrogen column densities, act as reservoirs of baryons influenced by dark matter potential wells. The observed kinematics and spatial distribution of these systems agree with hierarchical structure models driven by dark matter halos, supporting the concordance cosmological picture. In summation, the historical discovery and analysis of dark matter reflect a multidisciplinary synthesis of observational astronomy, theoretical physics, and computational modeling, with key contributions emerging from diverse cosmic scales and methods. Each new technique, from velocity measurements to lensing, from X-ray to microwave background analyses, has progressively confirmed and refined our understanding of dark matter, highlighting its central role in the cosmic architecture and evolution observed today. Gravitational lensing provides direct evidence of dark matter's physical presence. When light from distant galaxies passes near massive objects, its path bends, creating warped or duplicated images. The degree of lensing often points to a total mass much greater than what we see, indicating a substantial amount of unseen matter influencing spacetime curvature, consistent with dark matter predictions. Unlike ordinary matter, dark matter does not appear to interact electromagnetically, meaning it neither emits nor absorbs radiation across the entire electromagnetic spectrum. This lack of interaction makes it undetectable by traditional telescopes, but allows scientists to study it through the gravitational effect it imposes on surrounding matter and light. Observations of the cosmic microwave background, CMB, provide further insight into the properties of dark matter. Precise measurements of the slight temperature fluctuations in the CMB, such as those made by the Planck satellite, show patterns consistent with a universe that contains approximately 27% dark matter, influencing the rate of structure formation after the Big Bang. Dark matter is believed to be cold or non-relativistic, meaning it moves slowly compared to the speed of light. This cold dark matter, CDM, model fits observations well by allowing the growth of cosmic structures, such as galaxies and clusters, over time. If dark matter were hot or relativistic, it would smear out density fluctuations, preventing the formation of small-scale structures observed in the universe. One hypothesized form of dark matter is weakly interacting massive particles, WIMPs, which are predicted by various extensions of the standard model of particle physics. WIMPs would have mass and interact via gravity and possibly the weak nuclear force, but rarely with ordinary matter, aligning with the observed invisible but massive nature of dark matter. Another class of candidate particles includes axions, very light particles arising from solutions to the strong CP problem in quantum chromodynamics. Unlike WIMPs, axions would be extremely light and could form a cold, dark matter condensate, potentially detectable through their slight interaction with electromagnetism under special laboratory conditions. Sterile neutrinos are a hypothetical type of neutrino that do not interact via the standard model forces except gravity and possibly a new force, making them a warm dark matter candidate. They could explain certain astrophysical observations, such as X-ray emissions from galaxy clusters, though no conclusive detections have been made. Self-interacting dark matter models propose that dark matter particles can interact with each other through forces analogous to, but weaker than, those known in the standard model. These interactions might alleviate some discrepancies between simulations of cold dark matter and the observed structure of galaxies, such as the density profiles near galactic centers. Dark matter's interaction with baryonic matter, ordinary matter made of protons and neutrons, is predominantly gravitational. Unlike ordinary matter, it does not form atoms, molecules, or complex structures because it does not cool by radiating energy. This property prevents dark matter from clumping at small scales and forming structures like stars or planets. In galaxy clusters, the separation of dark matter and ordinary matter is observed directly during collisions, such as the bullet cluster. After two clusters collide, the visible matter, mostly hot gas, slows down and emits X-rays, while dark matter passes through mostly unaffected, continuing along its trajectory as detected via gravitational lensing, highlighting its weak interaction with ordinary matter. The temperature of dark matter particles influences the formation of cosmic structure. Cold dark matter allows for hierarchical clustering, where small objects form first and merge into larger structures, consistent with observations. In contrast, hot dark matter, like neutrinos moving near light speed, would erase small-scale fluctuations, conflicting with the observed abundance of small galaxies. Direct detection experiments aim to observe rare interactions between dark matter particles and detectors on Earth. These experiments rely on the assumption that dark matter occasionally collides with nuclei, producing small energy signals. To date, no definitive detections have been made, placing stringent limits on the strength of possible dark matter interactions with normal matter. Dark matter must be non-baryonic, as evidenced by measurements of light elements formed in the first 3 minutes after the Big Bang, known as Big Bang nucleosynthesis. The abundance of hydrogen, helium, and lithium matches predictions assuming dark matter does not consist of baryons, which helped eliminate ordinary matter as the source of the missing mass. Astrophysical observations show that dark matter dominates the mass budget of galaxies and galaxy clusters, often exceeding visible mass by a factor of 5 or more. This dominant presence shapes galactic formation and dynamics, influencing everything from star orbits to the temperature distribution of interstellar gas. Cosmological simulations that include dark matter particles reproduce the large-scale structure of the universe remarkably well, predicting a cosmic web of filaments and voids where galaxies cluster along dense filaments. This outcome supports the idea that dark matter influences the gravitational scaffolding upon which ordinary matter accumulates. Although dark matter interacts weakly or not at all electromagnetically, it may still have subtle impact on the polarization patterns observed in the CMB. Scientists analyze these patterns to constrain properties like the mass and interaction rates of dark matter candidates, providing indirect but valuable information for understanding dark matter's physical nature. The distribution of dark matter around galaxies tends to form halos, extending well beyond the visible edge of galaxies. These halos are roughly spherical or elliptical and have density profiles characterized by simulations such as the Navarro-Franquite (NFW) profile, which helps astronomers model dark matter's gravitational influence. One challenge in understanding dark matter properties comes from dwarf galaxies, where the predicted dense central cusps of dark matter from simulations often appear less dense, a discrepancy termed the core cusp problem. This has led to alternative models considering dark matter self-interactions or feedback effects from star formation to reconcile models with observations. While dark matter does not interact electromagnetically, it can be mapped by its gravitational effect on nearby objects, such as causing shifts in the orbits of stars in the Milky Way or affecting the paths of satellite galaxies. These precise measurements help astronomers map the shape and density of dark matter halos surrounding our galaxy. The non-relativistic nature and weak scattering rates of cold dark matter imply that it had to decouple early enough in the universe's history to allow density perturbations to grow. This decoupling time and temperature are essential parameters in theoretical models that match the observed structure and cosmic microwave background. In summary, dark matter's physical characteristics, its invisibility to electromagnetic radiation, dominance of gravitational effects, and hypothesized particle properties, are essential to explaining a wide range of cosmic phenomena. These properties have been progressively refined through decades of astronomical observations, particle experiments, and cosmological modeling, forming the foundation of modern astrophysics and cosmology's understanding of the universe's composition. The gravitational influence of dark matter extends beyond individual galaxies, playing a crucial role in the formation and dynamics of galaxy clusters, the largest gravitationally bound structures in the universe. Clusters typically contain hundreds to thousands of galaxies, along with hot gas visible in X-rays. Intriguingly, the total mass inferred from gravitational lensing and the motion of galaxies within clusters exceeds the mass of luminous components by a factor of about 5 to 10, strongly supporting the presence of a dominant dark matter component that provides the primary gravitational scaffolding in these massive systems. Dark matter's inability to interact via electromagnetic forces distinguishes it sharply from ordinary matter, affecting how it distributes itself in space. Unlike gas and dust, which can cool and collapse to form dense structures like stars and planets, dark matter remains in diffuse halos because it cannot dissipate energy by radiating light. This fundamental characteristic causes dark matter to maintain more extended, smoother distributions around galaxies and clusters, influencing their gravitational potential wells and the dynamics of visible matter within them. One of the most useful observational tools for assessing the properties of dark matter halos is weak gravitational lensing, which measures subtle distortions in the shapes of distant galaxies caused by intervening dark matter. Statistical analysis of these distortions has enabled astronomers to map dark matter distribution on large scales and determine the typical density profiles surrounding galaxies and clusters. These lensing maps confirm that dark matter halos are extensive, often extending up to several times the radius of the visible galaxies they envelop and following density profiles predicted by cold dark matter cosmological models. Dark matter's influence on cosmic structure extends back to the early universe, where it contributed to the growth of primordial density fluctuations. The clumping of dark matter in the aftermath of recombination set the gravitational wells into which ordinary matter could fall, leading to the eventual formation of galaxies and larger structures. Detailed measurements of the anisotropies in the cosmic microwave background radiation, particularly from missions like the Wilkinson Microwave Anisotropy Probe, WMAP, and Planck, allow scientists to constrain the dark matter density and understand its role in shaping large-scale structures. Further evidence for the properties of dark matter comes from observations of satellite galaxies orbiting larger hosts like the Milky Way. These satellites, often dwarf galaxies with low luminosity, provide laboratories to study dark matter's distribution on small scales. Their internal dynamics frequently suggest large mass-to-light ratios, indicating dark matter dominance. Measurements of their velocity dispersions imply dark matter is cold and collisionless, supporting the prevailing theoretical framework while also presenting puzzles such as the too-big-to-fail problem, where the most massive predicted subhalos lack luminous counterparts. Dark matter's gravitational effects also influence the velocity dispersion of stars within elliptical galaxies and galaxy clusters. Stars in such systems move under the gravitational pull of both visible and dark matter. By measuring these stellar motions, astronomers can reconstruct the underlying gravitational potential and infer the radial distribution of dark matter. These studies typically support models in which dark matter density decreases gradually with radius, consistent with predictions from large cosmological N-body simulations. One particularly intriguing property of dark matter is its apparent lack of self-annihilation signals in indirect detection experiments. Many dark matter candidates, such as WIMPs, are expected to annihilate when they collide, producing high-energy photons or cosmic rays. Despite sensitive searches with gamma-ray telescopes like Fermi-LAT and ground-based detectors, no unambiguous excess consistent with dark matter annihilation has been detected in regions with dense dark matter concentrations, such as the galactic center or dwarf spheroidal galaxies. This absence places strong constraints on the interaction cross-section and mass of dark matter particles. The observed isotropy and homogeneity of the large-scale universe also inform us about the properties of dark matter. Its presence must be sufficiently smooth at very large scales to comply with the observed cosmic microwave background uniformity, while allowing small-scale clumping necessary for galaxy formation. This balance supports the cold dark matter model, where dark matter dominates gravitational interactions, but does not collapse into smaller-scale structures due to its non-collisional nature, thereby enabling the formation of the cosmic web, a vast network of filaments and voids traced by galaxies. Dark matter halos exhibit a phenomenon known as velocity anisotropy, where the velocities of dark matter particles are direction-dependent. Simulations have shown that particles in the outer regions of halos tend to have more radially elongated orbits, while those near the center move more isotropically. This behavior impacts the shape and density profile of halos, and is consistent with the predictions of collisionless dark matter particles evolving under gravity alone, providing another diagnostic tool for matching theoretical models with observations. In galaxy cluster collisions beyond the famous bullet cluster, observations continue to reinforce dark matter's collisionless nature. Subsequent merging clusters have demonstrated that the bulk of dark matter passes through collisional ordinary matter largely unaffected. These measurements not only confirm the weak interaction between dark matter and baryons, but also constrain possible self-interactions within the dark matter component itself, typically limiting the interaction cross-section per unit mass to less than about 1 cm2/g. Dark matter's non-baryonic nature is also supported by large-scale surveys of the Lyman alpha forest, collections of absorption lines in the spectra of distant quasars caused by intergalactic hydrogen gas clouds. The detailed statistics and distribution of these clouds reflect small-scale mass fluctuations governed by dark matter clustering. Modeling these data imposes constraints on dark matter particle properties, such as their free-streaming lengths, favoring cold or warm dark matter candidates with negligible pressure on small scales to prevent erasure of structure. Moreover, dark matter's gravitational influence can be detected through its effect on the orbital motion of stars in the Milky Way's disk and halo. Precise measurements using stellar kinematics from missions like Gaia allow astronomers to map the dark matter density profile locally. These studies confirm that dark matter density near our solar system is roughly 0.3 GeV/cm3, a crucial parameter for direct detection experiments aiming to observe dark matter scattering events on Earth. Despite the dominant gravitational influence of dark matter, it does not show evidence of dissipative processes, such as radiative cooling, that would enable it to collapse into disks or other flattened structures like baryonic matter. This absence of dissipation contributes to the roughly spherical shape of dark matter halos, in contrast to the thin disk morphology of spiral galaxies composed of ordinary matter. This fundamental difference impacts galaxy morphology and the interplay between dark and visible matter during galaxy formation. Detailed computer simulations of dark matter have revealed a hierarchical pattern of structure formation, where small halos form first and then merge to build larger ones. This bottom-up scenario is a direct consequence of dark matter particle properties, chiefly being cold and collisionless. Such simulations match observational data on galaxy clustering and halo mass function, reinforcing the idea that dark matter drives the growth of cosmic structure from tiny early fluctuations to the rich array of galaxies seen today. Finally, the effects of dark matter extend to cosmological parameters such as the expansion rate and total matter density of the universe. Dark matter contributes about 85% of the total matter content, profoundly influencing the dynamics of cosmic expansion and the growth rate of fluctuations. Its gravitational pull slows the expansion locally and accelerates the clumping of matter, shaping the universe's evolution on timescales of billions of years, as revealed through supernovae surveys and large-scale structure observations. Dark matter's stability over cosmological timescales is a crucial property inferred from observations. Unlike many unstable particles, dark matter must persist from shortly after the Big Bang until the present, surviving billions of years, without significant decay or transformation. This longevity is supported by the consistency in measurements of structure formation and cosmic microwave background anisotropies, which require a stable or very long-lived form of matter to provide the gravitational backbone that guides cosmic evolution. The particle nature of dark matter also strongly suggests it is electrically neutral. If dark matter had electric charge, it would interact electromagnetically and thus be directly observable through various electromagnetic signals, which has not been detected despite extensive searches. This neutrality allows dark matter to avoid coupling with photons, enabling it to remain invisible across the electromagnetic spectrum, yet still exert gravitational influence. Another important characteristic involves dark matter's isotropic distribution on very large scales, as observed through galaxy surveys and cosmic microwave background measurements. While dark matter clusters and forms halos at smaller scales, on scales of hundreds of millions of light-years, its distribution appears smooth and uniform, consistent with the cosmological principle. This isotropy supports the cold dark matter paradigm and aligns with predictions from inflationary cosmology. Dark matter is also characterized by having a non-zero mass, which is critical in producing gravitational effects observed in galaxies and clusters. While the exact mass of dark matter particles remains unknown, constraints from cosmology and particle physics experiments limit the mass range to broad intervals, from ultralight axions with masses less than 10⁻22 eV to heavier candidates in the GeV/TeV range. This mass endows dark matter with the gravitational pull needed to influence visible structures, yet because it seldom interacts otherwise, it remains elusive. The phase space density of dark matter halos provides insight into the properties of dark matter particles. Observations of dwarf galaxies indicate that halos have high phase space density, placing upper limits on the velocity dispersion and setting constraints on the nature and mass of dark matter. Such data indicate that dark matter is cold rather than warm, since warm dark matter candidates would produce lower phase space densities contradictory to measurements. Dark matter exhibits a specific pattern of gravitational clustering characterized by non-collisional behavior. That is, dark matter particles interact gravitationally, but not significantly via other forces with themselves or baryons. This collisionless nature allows dark matter particles to pass through each other during large-scale structure formation, creating the smooth halo profiles inferred from simulations and gravitational lensing studies, while simultaneously avoiding dissipative effects typical of ordinary matter. Studies of dark matter in the early universe have shown that it decoupled from the primordial plasma well before recombination, effectively free streaming as the universe expanded. This early decoupling is essential to allow dark matter to seed the gravitational potential wells that drive baryonic matter to collapse into galaxies later. The timing of decoupling influences the size and distribution of initial density fluctuations, as deduced from very precise measurements of the cosmic microwave background. Dark matter is also characterized by an extremely low scattering cross-section with ordinary matter. This means that when dark matter particles encounter normal atoms, the probability of interaction is minuscule. This property helped establish the difficulty experienced thus far in detecting dark matter directly in underground detectors, despite their extreme sensitivity. Experimental upper bounds on dark matter particle-nucleon scattering cross-sections have reached values as low as 10⁻47 cm2, implying exceptionally weak interactions beyond gravity. The spatial extent of dark matter halos around galaxies is vast compared to the visible components. Observations indicate that these halos can extend to several 100,000 light-years beyond the luminous parts of galaxies. The total mass enclosed within these halos dominates the galaxy's mass budget and plays a significant role in stabilizing galactic disks and forming the environmental context in which satellite galaxies orbit. Dark matter is considered to be pressureless in cosmological modeling. Unlike ordinary gases or radiation, which exert pressure counteracting gravitational collapse, dark matter's pressure is negligible at large scales. This absence of pressure simplifies the modeling of cosmic evolution and is a fundamental assumption in the cold dark matter paradigm, enabling the formation of structures over time in line with observational evidence. The role of dark matter in galaxy formation involves the collapse of dark matter overdensities into gravitationally bound halos first, followed by the collapse of baryonic matter into the gravitational potential wells created. This sequence is supported by hydrodynamical simulations combined with dark matter n-body calculations, which reproduce the timing and distribution of galaxy formation observed across cosmic history. Dark matter's properties ensure the initial scaffolding necessary for gas cooling and star formation processes. In the context of large-scale cosmic flows, dark matter contributes to the bulk motion of galaxies. Peculiar velocities, or deviations from the uniform expansion of the universe, are driven largely by dark matter's gravitational field. Measurements of redshift space distortions and galaxy motions provide methods to quantify dark matter clustering and to test cosmological models describing its distribution and behavior. Dark matter's distribution can also be constrained by tidal streams, remnants of smaller galaxies torn apart as they orbit larger ones. By modeling how these streams move and disperse, astronomers can infer the underlying gravitational potential shaped predominantly by dark matter. These stellar streams act as sensitive probes of the clumpiness and shape of the dark matter halo, revealing substructures and anisotropies that align with cold dark matter predictions. The velocity distribution of dark matter particles in the Milky Way's halo is expected to follow a Maxwellian or near-Maxwellian profile, based on simulations and theoretical models. This velocity distribution is important for interpreting the results of direct detection experiments on Earth that rely on dark matter particles scattering off atomic nuclei. Variations from this expected distribution, such as the presence of streams or caustics, are actively studied as they could affect detection rates. Dark matter's gravitational influence also extends to altering the gravitational potential wells in which baryonic matter resides, affecting star formation rates and the cooling of gas clouds in galaxies. By shaping the depth and shape of potential wells, dark matter indirectly governs the conditions for star and planet formation, underscoring its foundational role in the cosmological evolution of luminous matter. In the framework of the lambda-cold dark matter, lambdictum, model, the standard cosmological model, dark matter's lack of interaction with radiation defines its behavior during the radiation-dominated era of the early universe. While photons and baryons were tightly coupled and underwent oscillations, dark matter barely interacted, allowing density fluctuations in the dark matter to grow uninterrupted. This property leaves observable imprints on the matter power spectrum and the anisotropies recorded in the CMB. Observations of rotating low-surface brightness galaxies have further constrained the central density profiles of dark matter halos. Unlike high-surface brightness galaxies, where baryonic mass dominates, these galaxies provide clearer insight into dark matter distributions, often showing core-like central densities rather than cusps. This trend has prompted refinements in understanding dark matter particle interactions at small scales, suggesting that any self-interaction or feedback processes must be subtle. Dark matter also affects gravitational time delays in systems where multiple images of a background source are seen due to lensing. The path length and gravitational potential differences caused by dark matter concentrations modify the arrival time of photons, measurable in lensed quasars or fast radio bursts. These time delays serve as probes of dark matter distribution and substructure, testing theoretical models beyond simple smooth halo approximations. On cosmological timescales, the presence of dark matter affects the rate of gravitational clustering and, consequently, the rate of galaxy mergers. The interaction cross-sections and masses influence how small dark matter halos combine to form larger structures. Observational evidence from galaxy merger rates and the growth of cosmic structures provides indirect constraints on dark matter properties, such as the particle mass and interaction strength. Large astronomical surveys, such as those conducted by the Dark Energy Survey and the Sloan Digital Sky Survey, utilize statistical analyses of millions of galaxies to further refine dark matter's properties. The correlation functions derived from these datasets reveal clustering behavior consistent with cold dark matter predictions, and allow constraints on dark matter's role in shaping the universe's evolution over billions of years. Finally, emergent phenomena such as the shapes of dark matter halos show triaxiality rather than perfect sphericity, as deduced from simulations and gravitational lensing data. These shapes stem from the anisotropic accretion history of dark matter and the hierarchical nature of structure formation. Understanding the three-dimensional density distributions of dark matter halos is fundamental to bridging theory and observation in astrophysical contexts. Dark matter's gravitational influence is sufficiently strong that it alters the dynamics within individual galaxies and between galaxies in groups. For example, rotational velocities of stars in the outskirts of spiral galaxies remain unexpectedly high and nearly constant, with radius defying predictions based on visible mass alone. This flatness in rotation curves implies that dark matter forms extensive halos that encompass and extend well beyond the luminous components, compelling revisions in the mass distribution models of galaxies. Unlike baryonic matter, dark matter does not participate in chemical reactions or nuclear processes. It neither absorbs nor emits photons, making it immune to radiative cooling, which is essential for ordinary matter to collapse and form stars or planets. The absence of electromagnetic interaction means dark matter is mostly influenced by gravity alone, allowing it to remain diffuse and stable in large halos without fragmenting into smaller, dense structures. Experimental and observational studies have established stringent upper limits on the interaction cross-section between dark matter particles and ordinary matter. These findings imply that if dark matter particles scatter off nuclei, the frequency of such events is extraordinarily rare. For instance, experiments such as LUX, Xenon 1T, and PandaX have constrained the dark matter nucleon cross-section to less than approximately 10⁻46 cm2 for WIMP masses near 100 GeV. placing challenging limits on many theoretical models. Dark matter is expected to have a velocity dispersion much lower than relativistic speeds, consistent with its classification as cold or at most warm dark matter. This slow velocity is a key factor, enabling the formation of the observed clumpy cosmic structure by allowing gravitational collapse on small scales without excessive smearing out of density fluctuations. Measurements of galaxy clustering and the Lyman alpha forest set lower bounds on the particle mass consistent with this cold or warm dark matter behavior. The large-scale cosmic web, as mapped through galaxy redshift surveys, directly manifests the gravitational scaffolding shaped by dark matter distribution. Filamentary structures connecting clusters of galaxies trace concentrations of dark matter, whose gravitational wells collect baryonic matter to form galaxies within them. The dominant role of dark matter in forming these filaments underscores its non-collisional and non-dissipative nature, since ordinary matter distribution alone cannot account for these patterns. In gravitational lensing analyses, the substructure within dark matter halos can cause small perturbations in the lensed images of distant quasars or galaxies. Detection of such subhalos through anomalies in lensing flux ratios offers independent evidence that dark matter is clumpy at small scales, consistent with predictions from cold dark matter simulations. These findings help constrain the minimum mass of dark matter halos, as well as the smoothness or granularity of dark matter distributions. Dark matter's dynamical friction, or the drag force experienced due to gravitational interactions with surrounding matter, differs notably from that of ordinary matter because dark matter is collisionless. As massive objects move through dark matter halos, they experience dynamical friction that can slow their motions, influencing galaxy mergers and satellite decay timescales. This process shapes the evolution and structure of galactic environments while reinforcing dark matter's role as a passive gravitational medium. Indirect searches for dark matter annihilation or decay products rely on signals such as gamma rays, neutrinos, or antimatter fluxes. Despite extensive observations by instruments like Fermi-LAT, HESS, and AM-SMINUS-2, no unambiguous signal of dark matter self-annihilation or decay has been observed to date. These null results place upper limits on the velocity-averaged annihilation cross-section and particle lifetime, further informing particle physics models of dark matter. Dark matter may possess primordial velocity distributions that differ from Maxwell-Boltzmann statistics due to its early decoupling and non-thermal production mechanisms. However, within collapsed halos, gravitational interactions thermalize particle velocities toward equilibrium distributions. Understanding these velocity distributions is crucial for interpreting direct detection experiment results, which depend sensitively on the assumed velocity profiles of dark matter particles in the solar neighborhood. The effective equation of state of dark matter in cosmological models is essentially pressureless, meaning it neither resists nor supports gravitational collapse through internal pressure. This property contrasts with radiation or baryonic gases, where pressure counteracts gravitational contraction. The pressureless nature facilitates the growth of density fluctuations across a broad range of scales, shaping galaxy formation timelines and the characteristics of the cosmic web. Dark matter halos not only dominate the enclosed mass, but also influence the structural stability of galaxies. Through their gravitational potential, they stabilize rotating galactic disks against disruptive instabilities such as bar formation or excessive spiral arm growth. This stabilizing effect evidences dark matter's role in maintaining long-term galaxy morphologies and dynamics observed in spiral galaxies. Studies of ultra-faint dwarf galaxies reveal that these objects possess extremely high mass-to-light ratios, implying they contain an overwhelming majority of mass in dark matter. Such systems serve as testbeds to understand dark matter properties on the smallest galactic scales, as their shallow gravitational wells are highly sensitive to dark matter particle behavior. The persistence of such dwarfs with minimal star formation strengthens the consensus on dark matter's dominant mass role at these scales. Dark matter's gravitational influence extends to gravitational microlensing events, where compact massive objects can cause temporary brightness variations in background stars. While such microlensing studies have ruled out significant populations of massive compact halo objects, MACHOs, as dark matter candidates, they provide constraints on the possible granularity and composition of dark matter, indirectly supporting particle-based models over macroscopic alternatives. The fine-scale structure and phase space properties of dark matter are constrained by Liouville's theorem, which sets fundamental limits on the maximum phase space density achievable by collisionless particles. Observations of dwarf galaxy cores align with phase space densities anticipated for cold dark matter, constraining models requiring warm or self-interacting particles to avoid excessive smoothing or heating of small-scale structures. Dark matter influences not only the mass distribution, but also the gravitational potential wells affecting gas cooling and star formation efficiencies in galaxies. This indirect effect shapes the history of luminous matter by modulating the depth and concentration of potential wells into which baryonic matter can fall, setting initial conditions for galaxy evolution. The coupling between dark matter halo properties and baryonic processes remains a key aspect of galaxy formation theories. The hierarchy of dark matter halo formation, characterized by continual mergers and accretions, leads to highly dynamical environments where halo properties evolve over cosmic time. Investigations show that mergers can alter the shape, concentration, and spin of halos, impacting subsequent baryonic formation processes. This dynamic evolution helps explain the diversity of galactic morphologies and the observed scatter in scaling relations like the Tully-Fisher relation. Dark matter's lack of electromagnetic coupling means that it does not respond to magnetic fields, unlike ordinary plasma and gas. This property ensures that dark matter remains unaffected by astrophysical processes like magnetohydrodynamic turbulence, which heavily influence the baryonic interstellar medium. Consequently, dark matter provides a relatively steady gravitational background, uninfluenced by complex electromagnetic forces widespread in galaxies. Cosmological observations indicate that dark matter density perturbs the expansion history of the universe by modifying the growth rate of large-scale structure. This growth rate can be measured using redshift space distortions and weak lensing surveys, which in turn constrain the clustering properties and possible interactions of dark matter. Current measurements align well with the lambdictum model, although minor tensions in growth parameters invite ongoing investigation into possible variants. Dark matter halos exhibit a broad range of concentration parameters, indicating differences in the density contrast between the core and outskirts. These concentrations correlate with halo mass and formation epoch. Lower mass halos tend to have higher concentrations due to earlier formation times in hierarchical structure formation. Understanding these correlations assists in interpreting both the internal dynamics of galaxies and the statistical properties of halo populations. Simulations including baryonic feedback, such as supernova-driven winds and active galactic nuclei activity, show that baryonic processes can redistribute dark matter in halos. These feedback effects can flatten central cusps into cores by transferring energy to dark matter particles, potentially resolving small-scale discrepancies like the core cusp problem. Thus, while dark matter itself is collisionless, its distribution can be indirectly shaped through gravitational coupling to baryonic physics. The intrinsic spin or angular momentum of dark matter halos arises from tidal torques during the early phases of structure formation. This angular momentum plays a critical role in shaping the rotational properties of galaxies embedded within the halos. Observations and simulations indicate a broad distribution of spin parameters, reflecting the complex assembly histories of halos and their environments. Dark matter's role in gravitational potentials affects the lensing of cosmic microwave background photons on arc-minute scales, a process known as CMB lensing. This effect provides a direct probe of dark matter distribution integrated over the entire line of sight to the last scattering surface. Precision measurements of CMB lensing by experiments like the South Pole Telescope and Planck place tight constraints on dark matter clustering and cosmic shear. The warm dark matter scenario, involving particles with masses in the keV range, predicts suppression of small-scale structure due to free-streaming effects. Observational studies of the abundance and internal structure of dwarf galaxies, as well as Lyman alpha forest data, place strong constraints on these models by requiring minimal damping to match observed substructure. Current data favor colder dark matter candidates, but allow narrow windows for warm components. Dark matter's presence influences the dynamics within galaxy groups, which consist of a few to several tens of galaxies tightly bound by gravity. The total mass inferred from galaxy motions and X-ray emitting intragroup gas consistently exceeds visible matter, requiring dark matter to account for the discrepancy. These intermediate scale systems provide vital environments to study dark matter's role bridging individual galaxies and massive clusters. Velocity-dependent self-interaction cross-sections have been proposed to reconcile certain halo structural properties with observations. Such models suggest that dark matter interactions vary with relative particle velocity, allowing for stronger self-interactions in low-velocity environments like dwarf galaxies and weaker interactions in high-velocity groups or clusters. Observational data from halo shapes and cluster collisions set upper limits on these velocity-dependent effects, refining theoretical possibilities. Dark matter is generally modeled as collisionless in simulations, but some models invoke dissipative dark matter components that could form structures analogous to baryonic disks. However, observational constraints such as the lack of dark matter emissions or absorption and stability of halo shapes strongly limit such possibilities. The currently favored picture is that dark matter is essentially non-dissipative, maintaining diffuse, extended halo distributions. Dark matter's potential interaction with neutrinos during the early universe would leave subtle signatures in the cosmic microwave background and large-scale structure. Precision cosmological data have been analyzed for evidence of such coupling, but have found no significant interaction, constraining models where dark matter couples to neutrinos or other light particles beyond gravity. Galaxy cluster mass reconstructions using combined gravitational lensing and X-ray data rely on assumptions about dark matter's pressureless and collisionless characteristics. The close agreement between lensing-based total mass distributions and X-ray-derived gas pressure profiles supports the consistency of dark matter properties with collisionless cold dark matter predictions on cluster scales. The thermal relic abundance calculations for dark matter particles predict a strong relationship between particle mass and interaction, rates responsible for freeze-out in the early universe. This relationship constrains the mass and cross-section parameter space where WIMPs could constitute the observed dark matter density. Experimental searches focus on this WIMP miracle region, though no detection has yet been confirmed. Observations of fast radio bursts, FRBs, provide a new avenue to probe dark matter properties, as the dispersion and lensing of these signals by intervening mass distributions reveal small-scale dark matter structures. Early studies indicate that FRBs can be used to detect microlensing by compact dark matter objects, or to constrain the granularity of dark matter on subgalactic scales. The tidal stripping of dark matter from subhalos orbiting within larger host halos impacts the survival and mass distribution of satellite galaxies. Simulations tracking the evolution of subhalos show that tidal forces can remove significant amounts of dark matter, altering satellite dynamics and contributing to the diffuse dark matter halo. These effects influence the observed satellite luminosity function and spatial distribution around host galaxies. Dark matter's lack of electromagnetic coupling implies that it does not suffer from radiative losses, which allows it to maintain non-thermal velocity dispersion, crucial for supporting the extended nature of halos. In contrast, gas loses thermal energy through radiation and collapses into concentrated structures. This difference explains the persistence of large, diffuse dark matter halos coexisting with compact baryonic matter distributions. The morphology and formation cascades of dark matter halos have been extensively studied through large-volume cosmological N-body simulations, such as the Millennium and Illustris projects. These simulations reveal the intricate web-like structure of dark matter, punctuated by voids, sheets, filaments, and nodes. Such multi-scale structure is a direct result of hierarchical clustering driven by primordial dark matter density fluctuations. Finally, constraints from global cosmic evolution implicate that dark matter remains stable over billions of years, with no signals of decay products altering the balance of dark matter density or contributing significantly to cosmic backgrounds. The absence of such signatures, over a wide range of time and distance scales, provides strong evidence that dark matter particles are either stable or possess lifetimes vastly exceeding the current age of the universe. The distribution of dark matter halos exhibits a wide variety of shapes, ranging from nearly spherical to significantly triaxial, as determined through both gravitational lensing observations and cosmological simulations. The triaxiality arises because dark matter collapse and accretion is anisotropic, influenced by surrounding large-scale structures such as filaments and walls. This anisotropic distribution affects the orbits of baryonic matter within galaxies, leading to observable effects in stellar streams and satellite galaxy trajectories, providing indirect probes of the three-dimensional dark matter geometry. Dark matter halos possess characteristic concentration parameters that describe how mass is distributed within them, typically defined as the ratio of a halo's virial radius to a scale radius, where the density profile slopes steeply. Studies reveal that halo concentrations correlate inversely with halo mass. Lower mass halos tend to be more concentrated, reflecting earlier formation epochs in the universe. This relation helps refine models of galaxy formation by linking halo structural properties to the timing of dark matter assembly in different environments. One property of dark matter emerging from simulations is an approximately universal velocity dispersion profile within halos, where particle velocities increase toward the center and decline at larger radii. This velocity structure influences the shape of dark matter, phase space, density, a quantity that encodes the number of particles per unit volume and velocity range. Phase space analyses facilitate constraints on dark matter particle characteristics, since collisionless dark matter preserves fine-grained phase space density, unlike collisional or dissipative dark matter models. The relative lack of small-scale substructure in dark matter halos inferred from observations known as the missing satellites problem has prompted refined understandings of dark matter's clustering properties. While cold dark matter predicts numerous small subhalos within galactic halos, many predicted satellites remain undetected in visible light. This discrepancy can be partially attributed to baryonic physics suppressing star formation in small halos, but it also informs limits on the minimal mass scale for dark matter clumping, placing constraints that are essential for particle physics interpretations. Dark matter's fundamental non-relativistic property means that its free-streaming length, the average distance a particle traveled before becoming gravitationally bound, is very small. This limited free-streaming length allows for the survival of fine structures in the cosmic matter distribution, enabling the presence of galaxies as small as dwarf spheroidals. The exact size of the free-streaming scale depends on the particle mass and velocity distribution, and thus informs cosmological bounds on dark matter particle models. Certain observations suggest that dark matter halos can exhibit a phenomenon known as halo assembly bias, where halos of similar mass differ in clustering strength based on their formation history. Halos that formed earlier tend to cluster more strongly than those formed later, even at fixed mass. This subtle dependence on halo age reveals complexities in dark matter clustering beyond simple mass-based models and affects the interpretation of galaxy halo connection studies crucial for understanding structure formation. Dark matter halos may contain a population of subhalos that survive tidal interactions within host halos. These subhalos are believed to be the remnants of accreted smaller halos and are important for understanding the fine-scale distribution of dark matter. The abundance and spatial distribution of these subhalos influence possible signatures of dark matter annihilation or decay, as denser substructures can act as hotspots for such processes, raising the stakes for indirect detection strategies. The concept of effective pressure in dark matter arises when modeling it with fluid-like equations for large-scale cosmology, even though individual dark matter particles are collisionless. This effective pressure is negligible compared to gravitational forces, but it can manifest through velocity dispersion or collective streaming motions, potentially smoothing density contrasts on very small scales. Such subtle effects can influence the shape of small-scale power spectra and are of interest for distinguishing cold from warm dark matter scenarios with precision cosmological observations. Dark matter's characteristic lack of absorption or emission bands in electromagnetic spectra sets it apart from baryonic matter and any form of gas or dust. Detailed spectral surveys across multiple wavelengths have found no signatures of dark matter interacting electromagnetically. This empirical fact not only excludes the possibility of dark matter composed of standard baryonic objects, but also restricts models proposing exotic dark sectors coupled electromagnetically or through photon mixing. In the cores of galaxy clusters, dark matter dominates the gravitational potential despite the presence of dense baryonic gas emitting X-rays. Studies have shown that the dark matter density profiles in these regions tend to be flatter than the steep cusps predicted by pure cold dark matter simulations, a phenomenon known as the core problem. This flattening may relate to complex interactions between dark matter and baryons, or to possible modifications in dark matter microphysics. Although no consensus has been reached and precise measurements continue to refine this important property. Observations utilizing dynamical modeling of stars in galactic bulges and elliptical galaxies suggest that dark matter contributes significantly to total mass at scales within several kiloparsecs from the galactic center. These mass profiles generally indicate dark matter density distributions more shallow or cored than predicted by pure n-body simulations. This discrepancy points to the possible influence of baryonic feedback processes reshaping dark matter distributions, or to nuanced particle interactions under extreme gravitational conditions. The thermal velocity distribution of dark matter particles in halos plays a crucial role in understanding structure formation and direct detection experiments. Though particles are broadly non-relativistic, small differences in their velocity dispersion affect the predictions of scattering rates in detectors on Earth. Models often assume a Maxwell-Boltzmann distribution truncated at the local escape velocity, but detailed halo simulations suggest departures from this assumption due to the presence of velocity substructure, such as streams and tidal debris. Gravitational interactions among dark matter particles are purely attractive, consistent with general relativity, and there is no evidence for dark matter particles exerting repulsive forces or negative pressure on each other. This behavior ensures that dark matter gravitational potentials contribute positively to the overall matter density, and do not induce exotic gravitational effects such as cosmic acceleration by themselves. The responsible role for cosmic acceleration is instead attributed to dark energy in modern cosmological models. Dark matter particles are expected to be non-relativistic today, but may have had higher velocities in the very early universe, post-decoupling. The relic velocity distribution influences dark matter clustering and the cutoff scale for halo formation. Precise cosmological measurements, such as those using Lyman alpha forest absorption spectra and CMB lensing, place stringent bounds on the permissible velocity dispersion of dark matter at early times, constraining scenarios involving warm or decaying dark matter. The minimum mass of the smallest dark matter halos, or the cutoff scale, is directly linked to the microphysical properties of dark matter, such as particle mass and interaction strength. Simulations indicate that this mass scale can range from as small as Earth mass for standard cold dark matter WIMPs to much larger masses for warm or fuzzy dark matter candidates. Observations targeting the faintest dwarf galaxies and stellar streams increasingly constrain this cutoff, offering valuable insight into dark matter particle physics. Dark matter halos generally show a universal density profile shape across a wide range of masses, often described by the Inasto or Navarro-Franquite (NFW) profiles. Such profiles reflect the equilibrium state achieved through hierarchical merging and gravitational relaxation, and are supported by simulations across cosmological scales. Deviations from these universal profiles in observed halos provide critical information about baryonic influences or possible self-interacting dark matter properties. The lack of significant intrinsic angular momentum in individual dark matter particles does not preclude dark matter halos from possessing net spin. This halo spin arises from tidal torques imparted during cosmic structure formation, much like baryonic angular momentum. The angular momentum affects halo shape, galaxy disk alignment, and may influence the efficiency of star formation by setting initial conditions for baryonic collapse within halos. Detailed studies of the phase space distribution function of dark matter around galaxies show that dark matter particles follow non-trivial anisotropic orbits rather than purely isotropic distributions. This velocity anisotropy varies with radius, typically becoming more radial at large distances from the galactic center. Such anisotropies impact both gravitational lensing analyses and interpretations of stellar kinematics data, enhancing our understanding of dark matter halo dynamics. Dark matter appears to have no intrinsic magnetic moment or electric dipole moment, as any such properties would couple it to electromagnetic fields and increase detectability, in conflict with extensive null results from astrophysical and laboratory searches. Constraints on these electromagnetic moments are extremely stringent, excluding even extremely small values, which supports the assumption that dark matter interactions are dominated by gravity alone. In regions of intense gravitational potential, such as galactic centers, dark matter density may rise but remains finite, avoiding singularities. This behavior contrasts with predictions of some simulations without baryonic physics that produce steep cuspy profiles. Observational evidence suggests that processes like dynamical heating by stars and gas feedback flatten the central dark matter distribution, indicating interplay between dark and ordinary matter in shaping density profiles. The total mass of dark matter within galaxy clusters is typically a few times greater than all the visible matter combined, including stars and hot gas. This dominant mass fraction underpins the gravitational binding of clusters and governs their dynamical evolution. Observational measurements from X-ray, gas temperature profiles, and gravitational lensing independently confirm this mass discrepancy and reinforce the role of dark matter as the principal matter component on cluster scales. While dark matter itself is pressureless, the gravitational binding energy of its halos contributes indirectly to the thermal energy of baryonic gas trapped within the halo's potential wells. This interaction influences baryonic gas temperature distributions, star formation rates, and the evolution of galaxies embedded within dark matter halos. Thus, dark matter's properties impact observable phenomena via gravitational coupling rather than direct interaction. Constraints on the self-interaction cross-section of dark matter come from a variety of astrophysical observations, including the shapes of galaxy clusters and galaxy halo mergers. Limits currently place the cross-section per unit mass below roughly 0.1 to 1 cm2/g, to avoid significant deviations from collisionless behavior. This narrow window guides theoretical models, balancing the need to explain small-scale structure problems while maintaining large-scale structure consistency. Dark matter particles are believed to have decoupled kinetically from the primordial plasma relatively early, meaning collisions with ordinary matter ceased, allowing dark matter to evolve independently under gravity. This decoupling epoch sets initial conditions for the formation of gravitational potential wells, thereby influencing the later assembly of galaxies and cosmic structures. The timing and physics of kinetic decoupling strongly impacts predictions of small-scale dark matter clumps and substructure. The dark matter power spectrum, which describes the amplitude of density fluctuations as a function of spatial scale, has a characteristic shape shaped by the interplay of primordial fluctuations and dark matter properties. High-precision cosmological measurements using the CMB and galaxy surveys reconstruct this spectrum and favor predictions consistent with cold dark matter. Deviations at small scales would signal alternative dark matter physics, making the power spectrum a fundamental tool in constraining dark matter's nature. The gravitational influence of dark matter halos induces characteristic cold flows of baryonic gas that feed galaxy growth in the cosmic web. These flows occur along filaments defined by dark matter distributions, funneling gas into galaxies and fueling star formation. The presence and properties of these streams are indirectly tied to dark matter halo characteristics and affect galaxy morphology and evolution. Dark matter does not cluster at scales below a certain limit set by quantum mechanical principles and cosmological initial conditions. For instance, ultralight fuzzy dark matter models invoke a de Broglie wavelength that sets a minimum halo size, smoothing out structures below galaxies of dwarf scale. Observations of the abundance and internal properties of small galaxies test these quantum limits, constraining alternative dark matter scenarios with wave-like properties. The dark matter halo mass function, which describes the number density of halos per unit mass at different epochs, is a key property revealing hierarchical structure growth. This function evolves predictably with cosmic time, reflecting how smaller halos merge and accrete to form larger structures. Comparing mass functions from simulations with observations across redshift offers insights into dark matter cosmology and the evolution of cosmic structures. The absence of direct electromagnetic interactions in dark matter means that it does not emit or scatter photons during cosmic recombination, preserving the detailed anisotropy patterns observed in the cosmic microwave background. This is in contrast to baryons, which tightly coupled to photons before recombination and left a distinctive imprint known as baryon acoustic oscillations. The silent behavior of dark matter during this epoch shapes the overall cosmic matter, power spectrum, and structure formation. Dark matter's gravitational field influences the tidal disruption of satellite galaxies, contributing to the formation of stellar streams and tidal tails observable in the halos of larger galaxies. These stellar streams provide dynamical tracers of the dark matter potential, allowing astronomers to reconstruct halo mass distribution and substructure with ever-increasing precision. Through this, astronomers probe dark matter's smoothness and granularity at scales unreachable by other means. Finally, the distribution of dark matter affects the rate and pattern of cosmic reionization by influencing the formation sites and timing of the first stars and galaxies. These luminous objects, which reionize the intergalactic medium, formed in dark matter halos of sufficient mass. Thus, the properties and abundance of these halos set the initial conditions for the universe's first luminous structures. Understanding this relationship illuminates the deep connection between dark matter's properties and observable cosmic dawn phenomena. Dark matter's distribution in galactic halos often exhibits subtle substructures that persist over cosmic time despite the collisionless nature of the particles. These subhalos can range from the size of dwarf galaxies down to much smaller mass scales, and their abundance and distribution are key predictions of cold dark matter models. Observational efforts utilizing stellar streams and gravitational lensing aim to detect these substructures, as their presence helps confirm dark matter's granular composition rather than a perfectly smooth halo. The velocity anisotropy of dark matter particles within halos significantly impacts the density and shape of these structures. Particles on predominantly radial orbits tend to create density enhancements along specific directions, while tangentially biased orbits promote more spherical mass distributions. Numerical simulations show that the anisotropy profile generally transitions from isotropic near the halo center to more radially biased in the outskirts, a behavior consistent with the hierarchical assembly of halos through mergers and accretion. Dark matter's weak gravitational clustering at the smallest scales sets fundamental limits on the formation of structures below a certain mass threshold, often called the free-streaming cutoff. This cutoff arises because primordial dark matter particle velocities prevent clustering below a particular scale, which depends on the particle's mass and kinetic decoupling epoch. Studies combining observations of ultra-faint dwarf galaxies and Lyman alpha forests precisely constrain this minimum scale, thus narrowing viable dark matter candidate masses. While dark matter is considered effectively pressureless in large-scale cosmology, on smaller galactic scales, it exhibits effective pressure-like effects due to velocity dispersion and anisotropic motions. This velocity dispersion pressure counters gravitational collapse and can influence the internal structure and stability of halos. Incorporating these effects in semi-analytic models helps reproduce observed density cores in some galaxies, shedding light on the non-trivial dynamics within dark matter halos beyond simple collisionless approximations. In regions of galaxy clusters where dark matter density peaks, the gravitational potential wells can influence the spatial distribution of hot, X-ray emitting intracluster gas. The alignment between these gas distributions and underlying dark matter halos is often imperfect, reflecting the collisional nature of baryons compared to collisionless dark matter. These discrepancies provide independent ways to map dark matter density profiles, as well as to understand the physics of gas dynamics in extreme gravitational environments. The lack of self-annihilation signals in gamma rays from dark matter-dense environments like the galactic center or dwarf galaxies places stringent upper limits on the annihilation cross-section of many hypothesized particle candidates. These limits, often derived from Fermi-Lat and HESS data, challenge simple WIMP models with thermal relic cross-sections near 3 × 10⁻26 cm3/s, pushing theorists toward more complex frameworks or less interactive particles. This absence refines the parameter space for viable dark matter models and drives the development of alternative detection strategies. The mass-to-light ratios in galaxy clusters highlight dark matter's dominant role in their total mass budget. Typical ratios can reach several hundred solar mass units per solar luminosity. This extreme difference shows that ordinary stars and hot gas compose only a small fraction of the cluster's mass. Observations combining strong and weak lensing with spectroscopic data of member galaxies confirm the dark matter dominance over wide spatial scales, influencing cluster evolution and cosmological mass calibration. Dark matter's smoothness on large cosmological scales contrasts sharply with its clumpiness on galactic or smaller scales. This scale-dependent structure reflects the balance between gravitational collapse and the initial velocity dispersion of dark matter particles, which suppresses growth below certain scales but leaves large-scale fluctuations intact. Cosmological measurements of matter power spectra, especially from surveys like BOSS and DAISY, confirm this distinctive pattern, lending support to cold dark matter paradigms. The elliptical shapes of some massive dark matter halos, inferred from gravitational lensing and satellite kinematics, result from anisotropic accretion flows and mergers along cosmic filaments. These non-spherical shapes influence the distributions of satellite galaxies and stellar streams, often causing preferred directions or asymmetric phase space features. Modeling these triaxial structures improves understanding of galaxy dynamics and the relationship between dark matter morphology and baryonic components. Dark matter velocity distributions in galactic halos can be perturbed by the presence of substructure, such as tidal debris from disrupted satellites or dark matter streams. These localized velocity features introduce departures from the canonical Maxwellian distributions commonly assumed in detection experiments. Accounting for such features is important when interpreting direct detection data, as they can enhance or suppress expected event rates depending on the Earth's position within these dark matter flows. The absence of dark matter interactions with electromagnetic fields also implies that it does not contribute to gas cooling processes or ionization fronts during epochs of galaxy formation and evolution. This lack of direct coupling means that dark matter's role in cosmic reionization is purely gravitational, shaping the timing and location of star-forming regions by providing gravitational wells where gas collects and cools. Consequently, dark matter indirectly influences the intergalactic medium's ionization history through gravitational structure formation. Self-interacting dark matter models, which posit weak but non-negligible dark matter particle collisions, predict observable consequences such as the formation of flat-density cores in dwarf galaxies and modification of halo shapes. Observations of cluster collisions and halo ellipticities constrain these interaction cross-sections, but do not exclude small levels of interaction, opening the possibility that dark matter behaves as a nearly collisionless fluid with subtle internal scattering. These models continue to be tested through detailed astrophysical observations and high-resolution simulations. The resilience of dark matter subhalos within larger host halos depends strongly on their mass, concentration, and orbit. Tidal forces strip mass preferentially from the outer regions of subhalos, yet their dense inner cores can survive numerous orbits, potentially hosting faint satellite galaxies. Understanding these survival mechanisms helps bridge the gap between the large numbers of predicted subhalos in simulations and the observed satellite galaxies, shedding light on both dark matter and baryonic feedback processes. Dark matter particles with very low masses, such as ultralight axions, exhibit wave-like properties on astrophysical scales, leading to interference patterns known as quantum granules. These granules impart characteristic fluctuations in the dark matter density, which could be observed through detailed measurements of stellar motions in dwarf galaxies or gravitational lensing effects. This wave behavior modifies the classical collisionless nature, potentially resolving some small-scale structure issues while remaining consistent with large-scale observations. Thermal relic calculations of dark matter particle properties depend sensitively on their annihilation cross-section and the freeze-out temperature in the early universe. Particles with smaller cross-sections remain overabundant unless compensated by heavier masses or non-standard cosmological histories. These considerations delineate a target parameter space for both direct and indirect detection experiments, providing a theoretical framework that constrains particle physics models consistent with cosmological observations. The hierarchical growth of dark matter halos implies that larger halos form through the successive merging of smaller ones, a process that leaves dynamical signatures in velocity dispersion profiles and shape distributions. Observed galaxy groups and clusters frequently contain substructures tracing recent mergers, which affect the dark matter potential and the subsequent motion of baryonic matter. Studies utilizing multi-wavelength observations enable reconstruction of these merger histories, providing constraints on dark matter clustering and interaction properties. Dark matter halos are not perfectly isolated, but can overlap and interact gravitationally in dense environments such as clusters, leading to tidal deformation and stripping of outer layers. These hollow-hollow interactions contribute to the redistribution of dark matter and can influence cluster dynamics, as well as the growth and survival of satellite galaxies. Observations of cluster outskirts and their dark matter profiles provide clues about the extent and impact of these interactions. The faintest known satellite galaxies, often called ultrafaint dwarfs, have extraordinarily high dark matter fractions, often exceeding several hundred times their stellar mass. These systems serve as vital probes into the nature of dark matter at the smallest galactic scales. Their survival and properties impose constraints on the free-streaming length and possible interactions of dark matter particles, limiting warm dark matter models and informing theories about the earliest stages of structure formation. Dark matter lacks radiative mechanisms that would redistribute its kinetic energy internally, causing its velocity distributions to remain nearly collisionless and preserving fine-grained phase-space features over cosmic time. This property means that phase-space mixing arises chiefly from gravitational interactions rather than collisional thermalization, distinguishing dark matter behavior from ordinary gases. This dynamic leads to persistent features such as caustics and streams, which are targets for future observational probes. In the cosmological context, dark matter drives the growth of gravitational potentials that determine the growth rate of large-scale structure. Measurement of the growth rate via redshift space distortions in galaxy surveys provides constraints on dark matter properties and possible deviations from general relativity. Current data are consistent with cold, collisionless dark matter, but remain sensitive to subtle alternative scenarios involving modified gravity or dark matter interactions. The smoothness of dark matter on large scales is quantified by its power spectrum amplitude and shape, with precisely measured parameters known as sigma-8 and ns, which relate to matter clustering and primordial fluctuations. Observations of the cosmic microwave background by Planck and other observatories tightly constrain these parameters, providing robust support for the cold dark matter paradigm. Any significant deviations would imply alternative dark matter dynamics or production mechanisms. Dark matter's presence influences the formation and evolution of central supermassive black holes in galaxies by contributing mass and depth to potential wells. Deeper, more massive halos promote enhanced gas inflow rates that feed black hole growth. Observational correlations between black hole masses and dark matter halo properties suggest a linked evolution shaped by gravitational dynamics in the cosmological context. The inviscid nature of dark matter, a consequence of its collisionless behavior, prevents it from undergoing dissipative processes like viscosity-induced angular momentum loss or shock formation. As a result, dark matter maintains orbital coherence and angular momentum distribution over long timescales, impacting the stability and shape of halos and embedded galaxies. This contrasts with ordinary baryons, where viscous and dissipative processes drive disk formation and star formation. The distribution of dark matter around galaxies is commonly described using empirical models such as the Navarro-Frankwhite profile, but some observations suggest deviations at small radii that may demand core-like profiles. These cores potentially arise from baryonic feedback processes or self-interactions within dark matter itself. Determining which mechanisms dominate remains an active area, with implications for the underlying particle nature of dark matter. Detailed measurements of dark matter halo concentration as a function of redshift reveal evolution consistent with hierarchical clustering. Halos at earlier cosmic times tend to be less concentrated due to their more recent formation. These evolutionary trends are vital for interpreting observations of galaxy populations at different epochs, and for testing cosmological models with time-dependent dark matter properties. Dark matter's non-interacting nature ensures it does not participate in electromagnetic processes that produce cosmic magnetic fields. Consequently, dark matter does not contribute directly to the magnetization of intergalactic or interstellar media. The origin and amplification of cosmic magnetic fields thus rely solely on baryonic and plasma processes, within the gravitational potential shaped by dark matter. The mass distribution of dark matter halos influences the velocity dispersion of stars in galaxies, providing a critical tracer for inferring dark matter profiles. In particular, Jeans modeling and Schwarzschild orbit superposition techniques applied to stellar kinematics allow astronomers to reconstruct gravitational potentials and hence map dark matter distributions. These methods have revealed variations in dark matter density profiles across galaxy types and environments. Dark matter halos play a crucial role in gravitational lensing time delays by affecting the geometry and potential wells along the line of sight to lensed images. Precise measurements of these delays in systems with multiple images provide constraints on the mass distribution of lensing galaxies and their dark matter content. Combined with cosmological models, such studies contribute to independent estimations of the Hubble constant and dark matter properties. Gravitational microlensing surveys aim to detect macroscopic compact halo objects, MACHOs, as dark matter candidates have instead largely ruled them out over wide mass ranges. These microlensing null results strengthen the case for particle dark matter by limiting the fraction of dark matter composed of such compact bodies. Remaining microlensing signals come primarily from known stellar populations, underscoring the absence of dark matter candidates with significant electromagnetic interactions or mass concentrations. The presence of dark matter affects the dynamics of barred spiral galaxies, where it can absorb angular momentum from rotating bars, influencing their longevity and strength. Simulations including dark matter halos demonstrate that dynamical friction between the bar and halo can slow bar pattern speeds, affecting observable galaxy morphology. This interaction provides indirect evidence for halo properties such as density and velocity distribution around galactic centers. The dark matter velocity distribution near Earth influences the recoil energy spectrum expected in direct detection experiments. Variations owing to the Earth's motion within the Milky Way and potential transient structures like dark matter streams modulate the expected detection rates and their annual modulation signatures. Understanding these velocity features is critical to designing experiments and interpreting results in the search for dark matter particles. Dark matter particle candidates such as sterile neutrinos possess decay channels leading to X-ray photons, motivating searches for unexplained X-ray emission lines in astrophysical systems. Observations of galaxy clusters and the Milky Way center have reported tentative spectral lines near 3.5 keV, though their origin remains debated. Future high-resolution X-ray spectroscopy missions will clarify these signals' nature and their implications for dark matter properties. The interplay between dark matter and baryonic matter during galaxy formation involves complex feedback mechanisms where energy output from stars and active nuclei alters the dark matter density distribution via gravitational coupling. Processes like supernova-driven gas outflows can cause temporary fluctuations in gravitational potential wells, transferring energy to dark matter particles and flattening density cusps into cores. This coupling shows that while dark matter is collisionless, it is not isolated from baryonic effects. Dark matter's role in providing gravitational potential wells also establishes the environment in which chemically enriched gas accumulates and cools. This framework enables the formation of successive generations of stars and the buildup of complex elements necessary for planetary systems. The persistence of dark matter halos over cosmic timescales thus underpins the conditions favorable for chemical evolution and cosmic structure. Precision measurements of the Milky Way's rotation curve and the local escape velocity help constrain dark matter density and velocity distribution in the solar neighborhood. Recent data from the Gaia mission and spectroscopic surveys refine these parameters, improving models for direct detection rates and galactic dynamics. These local constraints are essential for translating cosmological dark matter properties into testable particle physics predictions. The gravitational lensing effect known as Einstein rings depends sensitively on the dark matter distribution in lens galaxies. High-resolution imaging of these rings provides detailed mass maps that separate baryonic and dark matter contributions. Such analyses improve understandings of dark matter halo shapes, concentrations, and substructure, complementary to other probes like stellar kinematics. Dark matter's sustained presence through cosmic time, implied by the persistence of large-scale structures and stable galaxy populations, implies extremely long lifetimes or fundamental stability of its constituent particles. Models involving decaying dark matter are constrained tightly by observations of the cosmic microwave background and extragalactic background light, limiting decay rates to values that exceed the current age of the universe by many orders of magnitude. The fine-scale anisotropies in the cosmic microwave background place constraints on dark matter properties such as mass and interaction cross-section by affecting the growth of density perturbations. Variations in dark matter characteristics alter the timing and amplitude of acoustic peaks, offering indirect but robust means to exclude certain warm or interacting dark matter scenarios that would contradict precise CMB observations. Dark matter's effect on the gravitational potential within galaxies influences the stability and lifetime of molecular clouds where stars form. By modulating tidal forces and overall mass distribution, dark matter indirectly impacts star formation efficiency and the initial mass function of stars. This gravitational regulation links large-scale cosmological features with the small-scale physics of stellar birth. Simulations show that the angular momentum of dark matter halos correlates with the spin of their embedded galaxies, indicating coevolution shaped by cosmic tidal torques. This relationship affects disk formation and alignment within halos, impacting observable galaxy morphology, especially in spiral galaxies. Understanding this connection is pivotal in unraveling how dark matter shapes the visible universe. Dark matter halos exhibit mass accretion histories that vary depending on environment and redshift, influencing halo concentration and substructure content. Halos in denser regions typically experience earlier formation and increased merging, resulting in higher concentrations and richer satellite populations. These histories are traced using cosmological simulations and compared to observations to test dark matter models and understand galaxy environment dependencies. The gravitational potentials shaped by dark matter are essential in setting escape velocities, which determine the retention or loss of gas in galaxies. Galaxies with shallow dark matter potentials are more susceptible to gas loss via feedback-driven winds, influencing chemical enrichment and star formation histories. This link between dark matter halo mass and baryonic feedback underscores the intertwined evolution of dark and ordinary matter components. Finally, the distribution and clustering of dark matter influence gravitational wave signals through their impact on galaxy mergers and black hole formation rates. The frequency and intensity of these events depend on the dark matter-driven growth histories of galaxies. Future gravitational wave observations can thus provide complementary insights into dark matter properties by tracing the cosmic assembly of massive objects. Dark matter halos exhibit a range of shapes influenced by their formation history and environment, with simulations revealing that halos in denser regions tend to be more oblate, while those in less crowded environments show more prolate or triaxial shapes. This morphological diversity affects how dark matter aggregates and subsequently how baryonic matter settles within these halos, influencing galaxy shapes and rotation patterns. Observationally, gravitational lensing and stellar stream studies confirm these complex halo geometries, indicating that dark matter does not form perfectly spherical distributions. The internal velocity structure of dark matter within halos reveals a transition from nearly isotropic motions in central regions to more radial anisotropy at larger radii. This anisotropy arises naturally from infalling particles during hierarchical accretion and mergers. contributing to the formation of density cusps and the overall halo stability. Precise modeling of this velocity behavior is crucial when interpreting dynamical data from stellar tracers and predicting the expected signals in direct detection experiments that depend on particle velocities. Dark matter particle candidates must exhibit extremely weak interactions with the standard model to remain consistent with cosmological and astrophysical constraints. Experiments searching for spin-dependent interactions have placed stringent upper limits, excluding many particle models where dark matter would interact via axial vector couplings. Such constraints help refine theoretical models, focusing attention on particles that interact predominantly through gravity or via new, hidden sector forces with negligible scattering with normal matter. Galactic tidal streams, which form when smaller satellite galaxies are gravitationally disrupted, provide indirect yet sensitive probes of the dark matter halo's granularity and substructure. Subhalos induce gaps and perturbations in these streams, and detailed observations allow astronomers to reconstruct the mass and location of otherwise invisible dark clumps. This technique has confirmed predictions from cold dark matter simulations regarding the existence and abundance of subhalos down to very low mass scales, currently inaccessible by other observational means. The dark matter density at the location of the Earth within the Milky Way is critical for interpreting the likelihood of detecting dark matter particles on Earth. Current estimates based on multiple independent methods, including stellar kinematics and microlensing, converge on a value around 0.3 to 0.4 GeV/cm3. This density, combined with local velocity distributions, determines the flux of dark matter particles through detectors and informs the design and sensitivity requirements for direct detection experiments. Dark matter's collisionless nature implies that individual particles move along geodesics determined primarily by the gravitational potential, without undergoing collisions that would redistribute energy or momentum. This results in long-lived features in phase space, such as caustics and streams formed by tidal disruption events. The persistence of these structures provides unique fingerprints of the dark matter particle properties and the assembly history of galactic halos. In interplay with baryonic physics, dark matter halos exhibit adiabatic contraction, where the infall and cooling of ordinary matter lead to a densification of the central dark matter distribution. This process steepens the inner density profile, increasing gravitational potential and affecting galaxy evolution. Conversely, feedback processes from star formation and active galactic nuclei can counteract this effect, redistributing dark matter and potentially flattening central cusps into cores. Gravitational lensing time delays between multiple images of background sources provide constraints not only on halo mass, but also on fine-scale dark matter substructure. Variations in arrival times caused by subhalos offer a way to detect or limit the abundance of dark matter clumps below direct imaging thresholds. These time delay measurements complement flux ratio anomalies in lensing and enhance our capability to test dark matter clustering on subgalactic scales. Dark matter halos show a strong correlation between mass and concentration, yet there exists significant scatter caused by variations in halo formation times and merging histories. Early forming halos tend to be more concentrated due to longer periods of gravitational relaxation, influencing galaxy properties such as stellar density and rotation curves. This scatter challenges simplified models, emphasizing the importance of detailed simulations in interpreting observed dark matter distributions. The particle mass of dark matter candidates affects the smallest scale at which structures can form, commonly referred to as the matter power spectrum cutoff. For example, heavier weakly interacting massive particles allow formation of halos down to Earth mass scales, while lighter warm dark matter particles suppress small-scale structures below dwarf galaxy sizes. Observations of faint galaxies, combined with Lyman alpha forest data, impose strict lower bounds on the particle mass by requiring consistency with observed small-scale clustering. Dark matter's gravitational impact on the cosmic microwave background, CMB, extends beyond density perturbations to lensing distortions of the primary CMB anisotropies. This lensing smooths and modifies the angular power spectrum, measurable by experiments like Planck and the Atacama Cosmology Telescope. The degree of CMB lensing directly informs the integrated mass distribution of dark matter along the line of sight, refining constraints on its total abundance and distribution. The absence of dark matter detection in direct search experiments, despite increasing sensitivity, suggests that if dark matter interacts with ordinary matter, it does so with cross-sections far below current detection thresholds or via channels not yet explored. This drives the development of complementary detection strategies targeting alternative interaction signatures, including electron recoils, inelastic scatterings, or interactions with sub-GeV dark matter candidates requiring novel technologies. Substructures within dark matter halos, known as subhalos, evolve dynamically due to tidal stripping and heating when orbiting a larger host halo. These effects reduce their mass and alter their density profiles over time, potentially making many subhalos too diffuse to host visible satellite galaxies. Understanding subhalo survival and evolution is crucial in reconciling the missing satellites problem and interpreting indirect detection signals dependent on dense clumps. The phase space distribution of dark matter particles is constrained by Liouville's theorem, ensuring that fine-grained phase space density cannot increase through collisionless evolution. This principle implies limits on how dense dark matter cores can become without collisions or dissipative processes. Observational data supporting chord profiles in dwarf galaxies suggest that these phase space limits provide meaningful constraints on candidate particle properties, favoring cold, collisionless models. Dark matter halos exhibit spin characterized by a dimensionless parameter arising from tidal torques during gravitational collapse, with typical values around 0.03. This spin influences the angular momentum of embedded baryonic matter, impacting galaxy disk sizes and rotational characteristics. The correlation between halo spin and galaxy morphology is a key outcome of hierarchical structure formation models. Strong limits on dark matter's self-interaction cross-section have been established through observations of the morphology of galaxy clusters and colliding clusters like Abell 3827. These limits, typically less than 1 cm2/g, require dark matter to behave largely collisionlessly on cluster scales, ruling out models with frequent or strong self-interactions that would produce observable offsets or distortions in the distribution. Dark matter does not contribute to cosmic reionization through ionizing photons, but influences the timing and efficiency of reionization via its gravitational role in assembling halo masses that host early star formation. The abundance and mass function of these halos set the initial conditions for ultraviolet photon production needed to ionize the intergalactic medium, linking dark matter properties to one of the universe's major phase transitions. Numerical simulations demonstrate that the process of violent relaxation during halo formation establishes near-universal dark matter density profiles. This relaxation, occurring via rapid gravitational potential fluctuations, redistributes particle energies without collisions, leading to equilibrium configurations best described by NFW or INASTO profiles. Understanding the mechanisms behind this equilibration is critical to connecting particle-scale physics to large-scale structure observations. The intrinsic velocity dispersion of dark matter particles within halos prevents infinite gravitational collapse, acting as an effective pressure that supports halos against singularity formation. This dispersion, determined by the initial conditions and the hierarchical history, stabilizes halos and contributes to the formation of flat density cores observed in some galaxies, especially when combined with baryonic feedback effects. Dark matter particle candidates with masses in the sub-eV range, such as fuzzy dark matter, exhibit macroscopic quantum mechanical behavior on kiloparsec scales due to their large de Broglie wavelengths. This wave-like nature suppresses structure formation below certain scales, differs markedly from cold dark matter predictions, and can be tested by observations of galaxy density profiles and the Lyman alpha forest. The distribution of dark matter in the Milky Way is not perfectly smooth, but expected to contain clumps and streams from past mergers with smaller galaxies. These features produce local variations in dark matter density and velocity distributions, which may impact direct detection signals on Earth by altering expected event rates and modulations. Current and upcoming surveys targeting stellar streams contribute vital data to map this substructure. The non-relativistic nature of dark matter in the epoch of structure formation allows it to serve as an effective gravitational seed for baryonic matter collapse. Its dominance over relativistic species at late times removes pressure support, enabling small-scale perturbations to grow and eventually form galaxies. Observational evidence from galaxy clustering and Lyman alpha systems supports this cold behavior as fundamental to cosmic structure formation. An important parameter in dark matter studies is the escape velocity from a given halo, which determines the maximal dark matter particle speeds within it. The escape velocity profile affects the shape of the local velocity distribution and the flux of high-speed particles interacting with Earth-bound detectors. Measurements in the solar neighborhood indicate escape velocities around 500-600 km/s, consistent with models of the Milky Way's dark matter halo. Dark matter particles are hypothesized to have originated thermally in the early universe, freezing out when interaction rates dropped below expansion rates, yielding a relic abundance. This thermal freeze-out scenario predicts characteristic relationships between particle mass and annihilation cross-section, guiding experimental searches. The absence of discovery to date constrains these parameters and motivates theories of non-thermal or feebly interacting scenarios. Dark matter's gravitational effect modifies the redshift space distortions observed in large galaxy surveys, influencing the inference of peculiar velocities and matter clustering. Accurate modeling of these distortions enables measurements of the growth rate of cosmic structures and tests of gravity on cosmological scales, thereby providing indirect constraints on dark matter properties and possible interactions. The gravitational potential wells generated by dark matter halos create tidal forces that can distort and strip gaseous and stellar components of satellite galaxies. These tidal interactions shape the morphology and star formation history of satellites and contribute to the diffuse stellar halos observed around large galaxies. Studying these effects helps infer dark matter distributions and the dynamical history of galaxies. The velocity bias refers to potential differences between the velocities of dark matter particles and baryonic tracers, such as stars or gas within halos. Though small, this difference can affect precision measurements in galaxy clusters and pose challenges in mass modeling. Numerical simulations suggest velocity bias is minimal but non-zero, reflecting complex interactions between components during halo assembly. Dark matter density fluctuations imprint signatures in the large-scale distribution of galaxies, traced through the two-point correlation function and higher-order clustering statistics. These spatial patterns, measured by surveys like Euclid and DAISY, constrain dark matter properties and its role in galaxy bias, affecting interpretations of cosmological parameters and models of structure evolution. Certain dark matter candidates could possess tiny but non-zero electric or magnetic dipole moments, which would induce faint electromagnetic couplings. Laboratory and astrophysical searches have placed severe limits on such moments, pushing allowed values to negligible levels and reinforcing the assumption that dark matter's primary interaction channel remains gravitational. Dark matter's role in setting angular momentum distribution in galaxies is intertwined with cosmic tidal torque theory, where growing perturbations induce torques that spin halos. This process explains correlations observed between halo spins and large-scale structure, affecting galaxy alignments and morphology. Observations indicate that spiral galaxies preferentially align their disks with the angular momentum axes of their host halos. The density of dark matter particles in galaxy centers may be reduced by dynamical processes such as supermassive black hole growth and stellar feedback, which heat and redistribute dark matter orbits. These heating mechanisms contrast with purely gravitational collapse predictions, leading to central cores rather than cusps in some galaxies. Observational studies of dwarf galaxies and low-surface brightness galaxies support this scenario. Indirect searches for dark matter annihilation employ observations of the gamma ray flux from regions of expected high dark matter density, such as dwarf spheroidal galaxies. The non-detection of excess gamma rays in these environments provides strong constraints on the annihilation cross-section and the particle mass of many dark matter candidates. These results complement direct detection and collider experiments by probing a different interaction channel. Statistical studies of galaxy clusters show a consistent baryon fraction across a variety of environments, with total mass dominated by dark matter. This near-universal baryon fraction provides a cosmological test that dark matter constitutes the majority of matter, as variation would otherwise arise from baryonic physics alone. Measurements combining weak lensing and X-ray observations confirm this balance on cluster scales. Dark matter's presence indirectly shapes the initial mass function, IMF, of stars by regulating the potential wells within which gas collapses and fragments. By deepening gravitational wells, dark matter halos enhance gas retention and temperature profiles, influencing fragmentation scales. Understanding this coupling remains an active area of astrophysical research, linking cosmological and local physics. The gravitational interaction between satellite galaxies and dark matter substructure can induce resonant phenomena, causing transient features in stellar kinematics and spatial distributions. Such interactions act as diagnostics of the underlying dark matter halo, granularity, and density. Observations of the Milky Way's stellar halo and globular clusters provide laboratories to study these effects. Dark matter annihilation or decay could produce high-energy neutrinos, attracting the attention of neutrino observatories like IceCube. No conclusive evidence of dark matter origin neutrinos has yet been found, placing limits on annihilation rates and particle properties in certain mass ranges. These neutrino-based searches complement gamma ray and direct detection efforts by probing different messengers. Halo occupation distribution models, which describe the statistical relation between galaxies and dark matter halos, incorporate dark matter properties to explain galaxy clustering and luminosity functions. These models help disentangle the complex interplay of baryonic and dark matter processes shaping the observed universe, refining our understanding of galaxy formation and evolution in a dark matter-dominated cosmos. Dark matter's gravitational potential impacts the escape fraction of ultraviolet photons from galaxies, influencing cosmic reionization. By fostering denser gas configurations, the presence of dark matter halos indirectly controls the ionizing photon budget available to ionize intergalactic hydrogen, tying dark matter properties to the early ionization history of the universe. The study of dark matter-rich ultra-diffuse galaxies reveals that some galaxies with very low stellar content possess extensive dark matter halos. These systems challenge simple relations between stellar mass and halo mass and provide unique environments to probe dark matter dynamics and interplay with baryons. Observations suggest that dark matter can dominate galactic dynamics even in the near absence of ordinary matter. Finally, kinematic studies of globular cluster populations orbiting galaxies allow tests of dark matter halo potentials in regimes and spatial scales complementary to stellar and gas tracers. Such clusters respond primarily to the total gravitational potential and thus serve as independent probes of dark matter density, distribution, and anisotropy, enhancing our holistic view of dark matter's galactic-scale properties. Dark matter exhibits remarkably high stability over cosmological timescales, as indicated by the persistence of large-scale structures across billions of years. If dark matter particles were unstable and decayed appreciably within the universe's age, the gravitational potentials shaping galaxy and cluster formation would be altered, leading to observable discrepancies in the cosmic microwave background, CMB, and matter distribution. Observational constraints from gamma-ray backgrounds and CMB anisotropies limit dark matter decay lifetimes to well beyond the current age of the universe, strongly suggesting that dark matter consists of particles that are either absolutely stable or possess lifetimes exceeding tens of billions of years. Investigations into the possibility of dark matter self-interactions have led to upper bounds on the dark matter scattering cross-section per unit mass, often expressed in cm2/g. Analysis of galaxy clusters such as Able 3827 and the detailed structure of colliding systems impose cross-section limits roughly below 0.1 to 1 cm2/g, maintaining dark matter's predominantly collisionless character. These limits are crucial for refining models that allow mild self-interactions, which can help resolve small-scale structure tensions without contradicting observations on larger cluster scales. The velocity distribution of dark matter particles in the local group, especially near the solar neighborhood, is an essential property for interpreting direct detection experiment results. Models typically assume a Maxwellian distribution with a peak speed around 220 km/s and a high-velocity cutoff at the local escape speed near 550 km/s. However, recent data from Gaia and numerical simulations suggest the presence of velocity substructures, streams, and anisotropies that could cause deviations from these simple models, thereby affecting the expected scattering rates and directional signals in terrestrial detectors. Dark matter halos manifest a concentration parameter, which quantifies the steepness of their density profiles toward the center. Empirical and simulation-based studies show that halo concentration inversely correlates with halo mass. Smaller halos form earlier when the universe was denser and thus have higher concentrations, whereas massive halos forming later are less concentrated. This mass concentration relation has implications for understanding the assembly history of halos and their baryonic content, affecting galaxy rotation curves and lensing signatures. In regions where dark matter density reaches extremely high values, such as the centers of galaxies or clusters, the density profiles tend to flatten or develop cores rather than maintain steep cusps predicted by pure cold dark matter simulations. This core formation is evidenced by stellar kinematics and strong lensing observations, and is often attributed to processes such as baryonic feedback, redistributing dark matter, or potential self-interactions causing heat transfer within the halo. The precise origin of these cores remains an active area of research, as it offers clues to the microphysical properties of dark matter. The gravitational lensing effect induced by dark matter can also be used to measure its clumpiness on small scales through phenomena such as flux ratio anomalies in quadruply lensed quasars. These anomalies occur when tiny dark matter subhalos perturb the magnification of individual images, providing indirect evidence for the predicted abundance and mass function of subhalos in cold dark matter models. Such measurements complement direct and indirect detection efforts by probing dark matter's distribution on otherwise inaccessible scales. Dark matter particles have negligible thermal pressure relative to their mass density, rendering dark matter effectively pressureless on cosmological scales. This absence of pressure enables dark matter to collapse under gravity efficiently, facilitating the hierarchical growth of cosmic structures. Unlike baryonic gases, which resist collapse via thermal pressure and radiative cooling, dark matter's pressureless nature is essential to matching the observed galaxy population and large-scale distribution. The spatial distribution of dark matter exhibits a remarkable degree of smoothness on scales larger than several megaparsecs, following predictions of the lambdictum model. Statistical analysis of galaxy surveys and the CMB show that at these large scales, inhomogeneities in dark matter density are small, reflecting the near uniformity of the early universe. This smoothness provides the initial conditions for structure formation, with small-scale clumping arising from gravitational amplification of primordial density perturbations seeded during inflation. Dark matter's inability to interact electromagnetically implies that it does not cool by radiative emission, unlike ordinary baryonic matter. This lack of cooling prevents dark matter from dissipating energy and condensing into thin, disk-like structures commonly observed in stars and gas. Consequently, dark matter halos maintain extended, roughly spherical distributions, which shape the gravitational potentials hosting galaxies and impede direct dark matter collapse into highly concentrated objects. In collisionless cold dark matter scenarios, the distribution function of dark matter particles in phase space preserves the fine-grained phase space density due to Liouville's theorem. This conservation constrains how dense and cold dark matter structures can become over time. Observations of dwarf spheroidal galaxies support this, indicating dark matter with high phase space density values that effectively rule out overly warm or strongly self-interacting dark matter candidates that would smooth out these densities. The early kinetic decoupling epoch of dark matter marks the time when dark matter particles ceased interacting frequently with the thermal plasma of ordinary matter and radiation. This decoupling affects the damping of density perturbations on small scales and the minimum mass of dark matter halos that can form. The precise timing of this event depends on the particle physics properties of dark matter and constrains theories related to the small-scale cutoff in the halo mass function. Dark matter halos display triaxial shapes with axis ratios deviating from perfect spherical symmetry, as inferred from gravitational lensing and stellar dynamics. The degree of triaxiality varies with halo mass and environment, resulting from anisotropic accretion and mergers along cosmic filaments. Such non-spherical geometries influence the distribution of satellite galaxies and the orbits of stars within galaxies, serving as observable signatures of dark matter assembly histories. The interplay of dark matter with baryonic processes can indirectly reshape dark matter distribution through gravitational coupling. Energetic events like supernova explosions and active galactic nuclei activity expel gas, altering the gravitational potential and causing a phenomenon known as gravitational heating of dark matter particles. This process can flatten central dark matter cusps into cores, reconciling some observational discrepancies with pure dark matter simulations. Dark matter's clustering properties affect the universe's matter-power spectrum by setting a characteristic cutoff scale below which density fluctuations are suppressed due to particle free-streaming velocities. Observations from Lyman alpha forest absorption lines and galaxy surveys restrict this cutoff to correspond to very small scales, consistent with cold dark matter particles having masses above a few keV. These constraints disfavor warmer dark matter candidates that would erase structures at dwarf galaxy scales and above. The formation of the cosmic web, the vast network of filaments and voids composed of dark matter and galaxies, reflects dark matter's dominant role in large-scale structure. Numerical simulations incorporating cold dark matter replicate these structures with remarkable accuracy, showing that dark matter provides the gravitational scaffolding within which galaxies form and evolve. The geometry and connectivity of this web trace the initial conditions of the early universe and constrain dark matter's clustering behavior. Direct detection searches for dark matter on Earth depend critically on assumptions about the local dark matter density and velocity distribution. Current estimates place the local dark matter density near 0.3 GeV/cm3, but uncertainties remain due to the potential presence of streams or substructure. These variations can alter expected event rates and are a focus of ongoing astrophysical and laboratory studies to improve detection sensitivity. In galaxy clusters, the ratio of dark matter mass to baryonic mass can reach factors of 5 to 10, reflecting that dark matter dominates the gravitational potential at nearly all radii. This dominance influences observable properties such as galaxy velocity dispersions, X-ray gas temperature distributions, and gravitational lensing patterns. Such correlations offer robust constraints on both the amount and spatial distribution of dark matter within massive halos. Dark matter's role in modifying gravitational potentials governs gas cooling and star formation efficiencies in galaxies. Deeper dark matter halos allow gas to reach higher densities, promoting cooling and subsequent star formation, while shallow halos hinder these processes. This regulation links the properties of dark matter halos to observable galactic features such as stellar mass, gas content, and star formation rates across cosmic time. Observations of dwarf galaxies with diverse internal kinematics reveal varying central dark matter densities, challenging simple universal halo profiles. Some dwarfs show chord dark matter distributions, while others appear cuspy, suggesting variations in dark matter physics or baryonic feedback effects. These differences provide critical testing grounds for dark matter models, especially those exploring self-interactions or alternative particle properties. The continuous hierarchical buildup of dark matter halos implies that halos grow by accreting smaller halos and matter, with mergers influencing their internal structure and subhalo populations. This assembly history determines halo properties such as concentration, spin, and shape. Simulations tracking these hierarchical mergers connect dark matter microphysics with macroscopic properties of galaxies and clusters. The gravitational influence of dark matter impacts peculiar velocities and large-scale flows of galaxies, observable through redshift space distortions in surveys. Measuring these distortions allows inference of the growth rate of cosmic structure and tests modifications to dark matter clustering or gravity. Current data remain consistent with cold, collisionless dark matter, but provide targets for future precision cosmology measurements. Dark matter candidates, such as sterile neutrinos with masses in the keV range, could decay radiatively, emitting X-ray photons that manifest as weak emission lines in astrophysical spectra. Searches for such lines, like the debated 3.5 keV signal reported in galaxy clusters and the Milky Way, continue to refine the parameter space of these warm dark matter models. Definitive confirmation or exclusion of these signatures awaits higher-resolution X-ray observations. The scale dependence of dark matter clustering impacts the mass function and spatial distribution of subhalos, which in turn affect gravitational lensing, satellite galaxy populations, and direct detection signals. Current observations increasingly discriminate between models by constraining subhalo abundance and their density profiles. These constraints provide valuable feedback to particle physicists seeking viable dark matter candidates consistent with structure formation. The absence of dark matter emissions or absorptions in the electromagnetic spectrum across all frequencies strongly supports the lack of electromagnetically charged components in dark matter. Detailed astrophysical observations, including X-ray, optical, radio, and gamma-ray surveys, have found no signals attributable to standard matter interactions. This empirical fact severely limits exotic models involving charged or electromagnetically interacting dark sectors. Dark matter's contribution to lensing-induced time delays in strongly lensed quasars and galaxies allows precise mass measurements on galaxy scales. By modeling these delays alongside image configurations, astronomers can probe dark matter halo densities and substructures with sub-kiloparsec resolution. Such measurements enhance constraints on dark matter distribution beyond the reach of other methods, providing complementary tests of the cold dark matter paradigm. In the solar neighborhood, the velocity anisotropy of dark matter particles affects their flux and angle of incidence on Earth. This anisotropy arises from the global structure of the Milky Way's halo and the presence of local streams or debris flows stemming from past mergers. Understanding these features is critical for interpreting annual modulation signals and recoil spectra in direct detection experiments. Dark matter's lack of interaction with photons implies that it remains dynamically decoupled from the radiation field across cosmic history. This decoupling allows dark matter density fluctuations to grow unimpeded after kinetic decoupling, unlike baryons whose density perturbations were suppressed until recombination. The early growth of dark matter structure leads to the gravitational potential, wells necessary for subsequent galaxy and structure formation. Cosmological simulations show that the intrinsic spin of dark matter halos arises through tidal torques during gravitational collapse and growth. Typical halo spin values are low, with dimensionless spin parameters around 0.03. Yet this spin strongly influences the angular momentum acquired by baryons and the resultant morphology of galaxies embedded within halos. This connection is fundamental to understanding disk formation and kinematic alignment in galaxies. Gravitational tidal stripping of subhalos orbiting within clusters and galaxies alters their mass and structure, leading to observable consequences such as the suppression of visible satellite populations. Simulations indicate that stripping can remove a large fraction of a subhalo's outer mass while preserving dense cores. Observationally, this process explains discrepancies in satellite number counts and contributes to the diffuse dark matter component within halos. The universal dark matter halo profiles replicate well across a vast range of masses and redshifts, supporting the idea that dark matter density profiles emerge from fundamental gravitational dynamics independent of baryonic physics. These profiles provide essential inputs for modeling gravitational lensing, galaxy rotation curves, and cluster mass distributions. Deviations from these universal profiles can signal important astrophysical feedback or alternative dark matter properties. Dark matter's phase space structure retains memory of its initial conditions and assembly history through preservation of phase space density in the absence of collisional relaxation. This leads to the formation of caustics and stream-like features in halos, which can influence the local density and velocity distribution of dark matter particles. Efforts to detect signals originating from such fine-grained structures are ongoing in the context of dark matter detection experiments. Finally, dark matter's mass contribution to galaxies and clusters significantly alters the baryonic angular momentum distribution through gravitational torques. This interaction shapes galaxy morphologies, the formation of bars and spiral arms, and the kinematics of stars and gas. Understanding how dark matter structures influence baryonic angular momentum remains a key challenge connecting cosmology and galaxy formation. The inclusivity of dark matter in cosmic structure enhances gravitational potentials without contributing to electromagnetic forces, implying that dark matter's influence on baryonic matter is purely through gravity. This distinction is affirmed by the absence of radiation pressure effects or photon scattering signals linked to dark matter, as revealed by multi-wavelength astronomical observations. The gravitational-only interaction aspect underlines why dark matter has survived as a distinct component throughout the universe's evolution, without being assimilated into luminous matter or altered by radiative processes. Detailed analyses of galaxy cluster mass distributions through weak lensing tomography have revealed that dark matter halos extend well beyond the virial radius, sometimes by factors of 2 or more. These extended halos modify the gravitational environment in cluster outskirts and affect the infall rates of galaxies and gas, influencing cluster assembly. The persistence of such extended mass profiles illustrates dark matter's ability to dominate the gravitational landscape far beyond the concentrations of baryonic matter. Advances in numerical simulations incorporating realistic cosmic expansion and dark matter dynamics have enabled precise predictions of halo merger rates, concentration evolution, and subhalo survivability. These simulations indicate that the internal kinematics of dark matter halos evolve gradually, with subhalos experiencing tidal heating and stripping that reshape their density and velocity profiles. Such dynamic evolution underscores the non-static nature of dark matter halos and their continual impact on galactic and cluster evolution. The self-gravity of dark matter particles, while solely attractive, can lead to nonlinear clustering and the formation of gravitational caustics, regions of enhanced density caused by the focused trajectories of particles in phase space. Although difficult to observe directly, these caustics affect the fine-scale dark matter density and velocity distributions, potentially influencing the local flux of dark matter particles. Modeling these features provides insight into the collisionless behavior of dark matter over cosmic time. Dark matter is expected to contribute negligibly to the total angular momentum budget of the universe due to its weak coupling with baryons and radiation during early cosmic epochs. While halos individually possess spin arising from tidal torques, dark matter as a whole does not significantly exchange angular momentum on cosmic scales. This property affects the transfer of angular momentum to baryonic matter, which is critical for the formation of galactic disks and large-scale angular momentum alignment. The hierarchical nature of dark matter halo formation implies a diversity of subhalo mass functions dependent on environment and redshift. Denser regions foster earlier formation and more abundant substructure, whereas void regions host fewer and less massive halos. These environmental dependencies facilitate distinguishing dark matter models by comparing simulation-based predictions with observations of satellite galaxy populations across different cosmic neighborhoods. Precise measurements of star cluster and molecular cloud dynamics in the vicinity of the galactic center help delineate dark matter contributions versus baryonic mass. These data suggest that while the central kiloparsec is dominated by baryonic matter, dark matter remains an important component at intermediate radii, influencing the stability and evolution of galactic components. Understanding this interplay is essential for constructing comprehensive mass models of galaxies. The lack of detected monochromatic signals from dark matter decays or annihilations in gamma-ray spectra imposes robust constraints on possible dark matter lifetimes and annihilation cross-sections. Limits derived from observations by the Fermi Gamma-ray Space Telescope and others show that if such processes occur, they must be rare or involve particles with interactions far weaker than initially expected. These constraints guide the development of dark matter particle theories and influence the design of future indirect detection experiments. Certain models of dark matter predict that particles may cluster into gravitationally bound states or boson stars under specific conditions, altering local density and velocity distributions. While such objects remain hypothetical, their potential existence would produce distinctive gravitational signatures in lensing or dynamical measurements. Present astronomical surveys set upper limits on the abundance of such exotic configurations, preventing significant contributions to overall dark matter profiles, but their study continues to extend the range of dark matter phenomenology. In galaxy groups, dark matter dominates the mass budget similarly to clusters but at smaller scales, and its influence shapes group dynamics, merging histories, and the distribution of hot gas. Measurements of the virial masses of galaxy groups via member galaxy velocity dispersions and X-ray emission consistently demonstrate large dark matter fractions. These systems act as an intermediary scale for studying how dark matter transitions from galactic to large cluster environments, providing critical data for calibrating cosmological models. The velocity distribution of dark matter may exhibit features imprinted by past accretion events, such as streams or debris flows derived from disrupted satellites. Such structures can create localized enhancements or deficits in the dark matter particle flux at Earth's position. Accounting for these non-uniformities is crucial for interpreting results from directional dark matter detectors, which seek to distinguish potential signals from background noise through angular correlations. Dark matter's gravitational influence shapes the morphological transformation of galaxies, affecting processes such as bar formation, disk thickening, and mergers. Simulations illustrate that dark matter halos absorb angular momentum from baryonic structures during dynamical interactions, influencing the persistence and strength of galactic features. Observational correlations between halo concentration and galaxy morphology further elucidate how dark matter properties translate into visible galactic characteristics. Recent constraints on dark matter interactions with photons or neutrinos find no evidence of coupling beyond gravity, reinforcing the standard collisionless cold dark matter paradigm. Precision cosmological probes, such as CMB polarization measurements and large-scale structure observations, exclude scenarios where dark matter significantly alters photon or neutrino behavior. These results narrow options for dark matter particle models and focus searches on gravitational and weakly interacting candidates. The role of dark matter in galaxy cluster lensing extends to producing multiple images and arcs of background galaxies, whose shapes and arrangements encode detailed information about the inner halo structure. Strong lensing analyses reveal both the smooth dark matter component and small-scale subhalos, allowing mass mapping with unprecedented spatial resolution. These observations validate simulation predictions and help refine models of dark matter halo composition. Dark matter particles are expected to have extremely low cross-sections for scattering with nucleons, as demonstrated by the lack of signals in a variety of underground detectors. The resultant experimental upper bounds have pushed theoretical models toward lower interaction strengths and non-standard coupling scenarios, such as inelastic or isospin-violating interactions. These evolving limits steadily narrow the parameter space where viable dark matter candidates may exist. The distribution of dark matter also influences the trapping and retention of baryonic gas within potential wells, governing the efficiency of gas cooling and subsequent star formation. Halo mass and concentration directly impact whether gas can remain bound or escape via feedback processes, influencing galaxy luminosities and colors observed today. This regulatory role forms the backbone of galaxy evolution theories, linking dark matter halos to observable properties. Dark matter's effective equation of state, characterized by negligible pressure and viscosity, allows modeling as an ideal, collisionless fluid on large scales. This simplification is central to cosmological simulations, enabling efficient computation of cosmic structure formation while capturing the essence of dark matter's gravitational dynamics. Deviations from this idealization would signal new physics, but have not been observed to date. The central densities of dark matter halos exhibit a significant variation in observations, ranging from cuspy profiles in some galaxy clusters to core densities in dwarf galaxies. This diversity has motivated studies on whether astrophysical feedback or inherent particle properties, such as self-interactions, produce these differences. Understanding these variations is pivotal to constraining dark matter models and elucidating the interplay between dark and baryonic matter. The local velocity distribution of dark matter potentially includes contributions from a dark disk, component co-rotating with the Milky Way's stellar disk, formed from late accretion of satellite galaxies. Such a component would alter predictions for dark matter direct detection by changing particle velocities relative to Earth. Current dynamical and stellar population studies provide constraints on the existence and mass fraction of any such dark disk. Dark matter's gravitational role extends to influencing galaxy merger rates by determining the relative velocities and trajectories of galaxies within shared halos. The dynamical friction experienced within dark matter halos slows merging galaxies, dictating timescales for coalescence and eventual morphological transformation. Observational signatures of merger histories correlate with halo properties inferred from large cosmological simulations. Some theoretical models posit the existence of dark matter, with negligible but non-zero dissipative interactions, allowing formation of dark substructures analogous to baryonic disks. However, observations have yet to find evidence of such dissipative dark matter through gravitational lensing, stellar dynamics, or cosmic microwave background measurements. Current constraints effectively limit the fraction of dark matter that could exhibit such behavior, favoring collisionless models. The precise measurement of the local dark matter density impacts the expected event rates in direct detection experiments and informs the design of next-generation detectors. Estimates using Gaia data and halo modeling converge near 0.3 GeV/cm3, but with systematic uncertainties related to the modeling of baryonic components and halo shape. Refining this parameter remains a high priority for both astrophysical and particle physics communities. The neglect of dark matter dissipation channels explains why it exhibits high-velocity dispersion and cannot collapse into compact astrophysical bodies such as stars. This dynamical heating helps maintain the observed extended halo structures, differentiating dark matter from baryonic gas, which cools and fragments. Understanding this property clarifies the role of dark matter as a gravitational scaffold without directly participating in luminous matter formation. Observations of fast radio burst gravitational lensing events have been proposed as a novel probe of dark matter substructure. Minute differences in arrival times and magnifications caused by dark subhalos could detect or constrain the abundance of small-scale structure, complementing traditional lensing and dynamical studies. While still in early stages, this emerging technique holds promise for adding to the arsenal of dark matter observational tools. The universality of dark matter halo profiles across different cosmic epochs suggests that gravitational relaxation mechanisms operate similarly throughout the universe's history. This behavior facilitates the use of simulations to predict halo structure at high redshifts and informs models of early galaxy formation. Confirming this universality with observations at various redshifts remains an active goal of multi-wavelength astronomical surveys. The orbital anisotropy of dark matter particles, reflecting preferential directions in their motion, has measurable effects on the density and velocity dispersion profiles of halos. Increasing radial anisotropy toward outer halo regions influences the stability and shape of dark matter distributions, shaping the orbits of satellite galaxies and affecting gravitational lensing signals. Incorporating anisotropy into halo models improves the fidelity of mass reconstructions and predictions of dark matter behavior. Dark matter's lack of interaction with electromagnetic radiation ensures it remains gravitationally dominant even in the presence of intense radiation fields, such as those found in starburst or active galactic nuclei environments. This resilience implies that dark matter halos provide steady gravitational potentials over varied astrophysical conditions, influencing gas dynamics and feedback processes that shape galaxies. High-precision measurements of gravitational lensing time delays in strong lensing systems are sensitive to sub-kiloparsec scale dark matter structures, providing constraints on the mass and spatial distribution of subhalos. These measurements enable tests of cold dark matter predictions at scales not accessible through other methods, helping to distinguish between competing dark matter models, such as warm or self-interacting dark matter. The conservation of the fine-grained phase-space density of dark matter during gravitational evolution limits the maximum density achievable in collapsed halos, setting fundamental constraints on particle mass and velocity dispersion. This principle helps explain the observed density floors in dwarf galaxies and the structure of dark matter cores, connecting macroscopic astrophysical observations to microphysical particle properties. Variations in dark matter halo spin parameters arise from differences in large-scale tidal torque fields and merging histories, with typical halo spin parameters clustered around 0.03, but exhibiting a broad distribution. These variations impact galaxy disk sizes and orientations, influencing observable galaxy morphology and alignment with cosmic structures, underpinning galaxy halo coevolution models. Despite no direct detection of dark matter, precision cosmological measurements tightly constrain its total abundance and clustering properties. Observations of the cosmic microwave background, large-scale structure, and weak lensing consistently indicate that dark matter constitutes approximately 27% of the universe's total mass energy content, providing robust empirical support for its fundamental role in cosmic evolution. Dark matter's impact on the angular momentum transfer within interacting galaxies shapes the formation and longevity of tidal tails, bridges, and other transient structures. These features serve as observational tracers of dark matter halo properties and interactions, advancing our understanding of the dynamical assembly history of galaxies. Indirect detection efforts searching for dark matter annihilation products in neutrino observatories have so far placed upper limits on neutrino fluxes arising from dense dark matter environments, such as the Sun and galactic center. These null results constrain models of dark matter capture and annihilation, further shaping our understanding of particle properties and interaction strengths. Recent discoveries of ultra-diffuse galaxies with seemingly large dark matter halos and low stellar content provoke questions about galaxy formation efficiency and dark matter halo occupancy. These objects offer unique laboratories to disentangle baryonic physics from dark matter properties, as their dynamics are heavily influenced by dark matter distributions with minimal baryonic complication. The longevity of dark matter halos and their persistence through repeated mergers is a consequence of the collisionless nature of dark matter. Unlike baryonic gas, dark matter halos do not dissipate energy through radiative processes and thus maintain their structure over cosmological timescales, merging gradually to form ever larger cosmic structures. Dark matter does not interact with cosmic magnetic fields, which ensures that it remains unaffected by magneto-hydrodynamic turbulence and related instabilities occurring in baryonic plasma. This distinction supports treating dark matter dynamics separately from magnetized gas physics in galaxy formation and evolution modeling. Concluding measurements of the cosmological parameters such as the total matter density, omega, baryon density, omega, and dark matter density are consistent across independent observational methods including CMB, baryon acoustic oscillations, and supernovae surveys. This convergence strengthens the interpretation that dark matter is a non-baryonic, invisible mass component governing gravitational structure formation. The presence of dark matter alters gravitational potentials involved in local group dynamics, affecting the trajectories and orbital parameters of satellite galaxies and dwarf companions. Studies of these orbital motions not only constrict dark matter halo mass distributions, but also provide direct evidence of dark matter's role in shaping galactic neighborhood evolution. Dark matter's influence extends to the cosmic velocity field, where it governs peculiar velocities alongside large-scale bulk flows. Measurements of these velocities through redshift surveys serve as cosmological tests of dark matter, clustering strength and distribution consistency with lambdictum predictions. Observations of gravitational lensing-induced time delays in multiply imaged fast radio bursts, FRBS, offer new opportunities to probe dark matter substructure on unprecedented timescales. These fast transient phenomena enable precise measurement of lensing signatures, potentially caused by small-scale halo clumps, opening a promising frontier for dark matter studies. Dark matter halos contribute fundamentally to the dark energy-matter interplay by setting the gravitational wells within which accelerated expansion acts. While dark energy governs universal acceleration, dark matter determines the rate and scale of structure formation, a dynamic balance verifiable through cosmological observations. Finally, the growing catalog of resolved stellar streams around nearby galaxies provides an increasingly detailed mapping of dark matter halo structures. By examining the perturbations and coherence of these streams, astronomers trace the underlying dark matter potential, directly probing its shape, substructure, and evolution. These stellar streams thus constitute precise and nuanced tracers of dark matter properties in the local universe. One of the primary methods scientists use to hunt for dark matter is through direct detection experiments, which aim to observe rare interactions between dark matter particles and normal matter. These experiments typically involve ultrasensitive detectors placed deep underground to shield them from cosmic rays and background radiation. For instance, the Xenon 1T experiment, located in the Gran Sasso National Laboratory in Italy, uses a tank filled with liquid xenon to detect potential collisions between dark matter particles and xenon atoms, producing tiny flashes of light that sensors can capture. Such interactions are expected to be exceedingly rare because dark matter interacts very weakly with regular matter, making the detection process extremely challenging. In parallel to direct detection, indirect detection searches look for the byproducts of dark matter annihilations or decays occurring in space. Instruments like the Fermi Gamma Ray Space Telescope monitor regions of high dark matter density, such as the center of our galaxy, for excess gamma rays that could signal these events. Similarly, experiments such as the Alpha Magnetic Spectrometer, AMS, on the International Space Station measure cosmic rays for unusual signatures like excess positrons or antiprotons, which some theories suggest might be produced by dark matter interactions. By analyzing these energetic particles, scientists hope to identify patterns that cannot be explained by known astrophysical processes alone. Gravitational lensing provides a powerful observational tool to infer the presence and distribution of dark matter in the universe. When light from distant galaxies passes near massive clusters containing substantial amounts of dark matter, the gravitational field bends the light, causing distortions or multiple images of the background source. By carefully mapping these lensing effects, astronomers can reconstruct the amount and arrangement of mass, including dark matter, in these clusters. The bullet cluster observation serves as a striking example, where the separation between visible matter and gravitational mass provided compelling evidence for dark matter's existence. Galactic rotation curves present foundational evidence supporting dark matter's presence, and they continue to guide searches for its properties. Measurements of star velocities within spiral galaxies show that orbital speeds remain roughly constant far beyond regions containing most of the visible matter, contradicting expectations based solely on stars and gas. This suggests a substantial unseen mass component, assumed to be a dark matter halo, influencing gravitational dynamics. Contemporary surveys using radio telescopes to track hydrogen gas rotation complement optical observations, refining our understanding of how dark matter shapes galaxy structure. The cosmic microwave background, CMB, radiation offers a snapshot of the early universe, revealing subtle fluctuations in temperature that are influenced by the density and composition of matter, including dark matter. Satellite missions like the Wilkinson Microwave Anisotropy Probe, WMAP, and Planck have measured these anisotropies with extraordinary precision, enabling cosmologists to tightly constrain dark matter's abundance and distribution on the largest scales. These observations have reinforced the standard cosmological model, which estimates that about 27% of the universe's mass-energy budget consists of dark matter. Experiments searching for dark matter have also exploited the unique properties of cryogenic detectors that operate at temperatures near absolute zero. These devices measure both ionization and heat produced when a dark matter particle potentially knocks into atoms in their target material. The Super Cryogenic Dark Matter Search, SuperCDMS, experiment uses germanium and silicon crystals cooled to millikelvin temperatures to attain the sensitivity required for such rare event detection. By combining multiple signal channels, researchers can discriminate between potential dark matter events and background noise, enhancing the reliability of their results. Neutrino observatories offer an indirect approach to dark matter detection by searching for neutrinos emanating from the Sun or Earth's core that might originate from dark matter particles accumulating and annihilating within these bodies. Facilities such as IceCube in Antarctica detect Cherenkov radiation produced when neutrinos interact with the ice, allowing them to track neutrino fluxes with high precision. Any excess neutrinos from such regions relative to expected backgrounds could hint at dark matter interactions, providing new clues about its nature and mass. Recent innovation in quantum sensors has started to extend the dark matter search to extremely low mass candidates, which might otherwise evade detection in traditional setups. For example, atomic clock experiments monitor minute shifts in fundamental constants, potentially induced by interactions with ultralight dark matter fields. Similarly, resonant mass detectors and superconducting circuits probe hypothetical dark matter candidates like axions or axion-like particles through their effects on electromagnetic fields. These novel techniques broaden the experimental landscape beyond standard weakly interacting massive particles, WIMPs, reflecting the dynamic evolution of the search. Large-scale sky surveys, such as the Dark Energy Survey, DES, and the upcoming Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, contribute valuable data for dark matter research by mapping millions of galaxies with high precision. These surveys analyze the spatial distribution and clustering of galaxies, which trace the underlying dark matter structure due to gravity's dominant influence. By comparing observations with simulations based on different dark matter models, astrophysicists refine theoretical predictions and test alternative scenarios about its nature. Particle accelerators like the Large Hadron Collider, LHC, also play a significant role in searching for dark matter by attempting to produce dark matter particles in high-energy collisions. Physicists look for events displaying missing transverse energy, where momentum appears to vanish from the detectors, which could indicate invisible particles escaping detection. Coupled with precise measurements and background subtraction, these experiments help constrain possible dark matter candidates and their interactions with known particles, cross-linking cosmological and laboratory approaches. The use of directional detection in dark matter experiments offers a promising means to distinguish potential dark matter signals from background events by capitalizing on the expected directionality of dark matter particles in our galaxy. Since Earth moves through the Milky Way's dark matter halo, there should be a wind of particles coming mainly from the direction of the constellation Cygnus. Detectors capable of measuring recoil directions of nuclei struck by dark matter could thus provide a powerful signature, strengthening candidate event identification and reducing false positives caused by terrestrial sources. Astrophysical observations of dwarf spheroidal galaxies around the Milky Way provide attractive targets for indirect detection due to their high dark matter content and low background emission from ordinary astrophysical sources. Instruments such as the Fermi Telescope and the Cherenkov Telescope Array, CTA, scan these small satellite galaxies for gamma-ray excesses indicative of dark matter annihilation. The relatively clean environment of these galaxies allows for stringent constraints on annihilation cross-sections and particle mass, complementing searches in more complex regions like the galactic center. Underground laboratories afford a uniquely low background environment for direct detection experiments, protecting sensitive detectors from cosmic rays and environmental radioactivity. Locations like the Sanford Underground Research Facility in South Dakota and Italy's Gran Sasso National Laboratory provide depths exceeding a kilometer, significantly attenuating cosmic ray muons. Additional shielding with materials like lead and polyethylene further reduces background noise, enabling detectors like LuxZ PLIN, LZ, and PandaX to push detection sensitivities to unprecedented levels. Time projection chambers, TPCS, have become indispensable components of many direct detection experiments due to their ability to reconstruct three-dimensional particle interaction tracks with high precision. Liquid noble gas TPCS, such as those using xenon or argon, detect scintillation light and ionization electrons caused by particle collisions, providing both energy measurements and spatial resolution. This dual readout enhances capability to distinguish between electronic recoils from background radiation and nuclear recoils expected from dark matter interactions, improving candidate event selection. The study of structure formation in the universe also informs and constrains dark matter properties through numerical simulations comparing theoretical models with observed large-scale galaxy distributions. Cold dark matter (CDM) simulations successfully reproduce the cosmic web's filamentary patterns and cluster formation, but face challenges at small scales where discrepancies like the cusp core problem arise. Observations using high-resolution instruments help test different dark matter theories, influencing experimental priorities and detector designs to target particles consistent with cosmological data. In the radio wavelength regime, scientists investigate the 21-centimeter hydrogen line signals originating from the early universe as an indirect probe of dark matter effects on cosmic dawn and reionization. Instruments like the Hydrogen Epoch of Reionization Array (HERA) and the Square Kilometer Array (SKA) plan to detect fluctuations in this signal that might reveal how dark matter influenced the thermal and ionization history of the intergalactic medium. By comparing data with astrophysical models, researchers aim to glean additional insights into the properties of dark matter beyond local or galactic scales. Detection strategies also include searching for potential dark matter particles decaying into photons of specific energies, which could produce narrow spectral lines in X-ray or gamma-ray observations. For example, unexplained features around 3.5 keV detected in X-ray spectra of galaxy clusters, and the Milky Way have spurred investigations into sterile neutrino dark matter candidates. While the evidence remains inconclusive, ongoing observations by instruments such as XMM Newton and Chandra continue to test these hypotheses and refine decay lifetime limits, shaping experimental directions. The synergy between different detection methods strengthens the overall pursuit of dark matter identification, as positive signals in one approach can be cross-verified or constrained by others. For instance, a direct detection claim might be supported by corresponding excesses in indirect gamma-ray measurements or collider experiments. This multi-pronged approach mitigates the possibility of false positives and guides the refinement of theoretical models, emphasizing the importance of collaborative efforts across experimental physics, astrophysics, and cosmology. Advances in machine learning and data analysis techniques have become essential in processing the vast amounts of data generated by dark matter searches. Algorithms trained to recognize subtle patterns and discriminate signal from background noise enhance sensitivity and reduce false detection rates in experiments like LuxZ-PLIN and IceCube. Similarly, applying these methods to astrophysical survey data helps identify weak lensing signals and classify large numbers of galaxies, accelerating progress in mapping dark matter's cosmic distribution. Finally, international collaborations remain crucial to the success and sustainability of dark matter research. Projects such as the Cherenkov Telescope Array involve scientists from dozens of countries working together to build and operate the next generation of gamma-ray observatories. Likewise, initiatives like the Global Argon Dark Matter Collaboration pool resources and expertise to develop state-of-the-art detectors. This global effort exemplifies the scale and complexity of the challenge, ensuring a comprehensive and coordinated approach to unveiling one of the universe's fundamental mysteries. Another vital technique in the search for dark matter involves the study of galaxy cluster mergers beyond the bullet cluster, where multiple systems exhibit similar separations between visible baryonic matter and gravitational mass. By analyzing systems such as the Train-Wreck cluster Abel 520, and the musket ball cluster, scientists can observe how dark matter behaves independently from hot gas during collisions, offering insights into its self-interaction properties. These merging clusters act as cosmic laboratories, helping researchers place limits on how strongly dark matter particles can interact with each other, which guides theoretical model development. The annual modulation signal is a distinctive signature sought in direct detection experiments, arising from Earth's motion around the Sun as it orbits through the galactic dark matter halo. This movement causes slight seasonal variations in the detected dark matter interaction, rate as the relative speed between Earth and the dark matter wind changes. The DAMA/Libra experiment in Italy has reported observation of such an annual modulation over multiple cycles. But these results remain controversial due to the lack of independent confirmation by other experiments, emphasizing the importance of verification through diverse detection methods. In addition to high-energy particle detectors, atomic and molecular spectroscopy serve as tools to search for dark matter by monitoring fundamental constants over time. Certain dark matter candidates, particularly ultralight scalar fields, could induce small, periodic variations in quantities like the fine structure constant or electron mass. Experiments comparing atomic clocks with extreme precision over extended periods look for such possible shifts, providing constraints on these dark matter forms complementary to direct detection techniques that target heavier particles. Cosmic rays generated by standard astrophysical processes pose a significant background challenge in indirect searches, but also present opportunities. Sophisticated models of pulsars, supernova remnants, and other cosmic accelerator sources allow scientists to subtract expected backgrounds from observed cosmic ray spectra. Any excesses in energy ranges difficult to explain by known sources can then be scrutinized for potential dark matter origins, as demonstrated by the positron excess observed by the AMS and PAMELA instruments. The development of liquid argon detectors complements the extensive use of liquid xenon in direct detection by offering different nuclear recoil responses and background discrimination capabilities. Experiments like DarkSide use argon extracted from underground sources, which reduces radioisotope contamination such as 39R, thereby lowering intrinsic backgrounds. The distinct ionization and scintillation characteristics of argon allow researchers to cross-check potential signals observed in xenon detectors, enhancing the robustness of claims. In the context of accelerator-based dark matter searches, missing energy events at the LHC are often scrutinized alongside monojet or monophoton signatures, where a single high-energy particle recoils against undetected invisible particles. These analyses depend heavily on precise modeling of standard model backgrounds to identify potential new physics. By combining results from different channels and collision energies, the LHC experiments have set stringent upper bounds on dark matter-nucleon interaction cross-sections, complementing limits from underground detectors. Weak gravitational lensing not only maps dark matter in galaxy clusters, but also serves to characterize dark matter on cosmological scales through measurements of cosmic shear, the subtle distortion of distant galaxies due to intervening matter. Surveys like Euclid and the Hyper-SubPrime strategically measure these minute distortions across vast sky areas, producing data sets critical for understanding dark matter's large-scale distribution and its role in cosmic expansion history. These measurements help refine models of dark matter clustering and the growth of cosmic structure over time. The advent of time-domain astronomy adds a dynamic dimension to dark matter searches, where transient phenomena such as supernova explosions or fast radio bursts are analyzed for potential dark matter involvement. Some theories suggest that dark matter could influence or modulate transient signals, or that certain transient events might produce dark matter particles. Although no confirmed associations have been found, time domain observations expand the palette of cosmic phenomena available for dark matter investigation. Strong gravitational lensing in quasar systems provides a further means to probe dark matter small-scale structure. When quasars are multiply-imaged by intervening galaxies, flux anomalies and time delays between images can reveal the presence of dark matter subhalos too small to contain stars. These subhalos are predicted by cold dark matter models, but challenging to detect otherwise. Detailed modeling of lens systems allows researchers to test these predictions, constraining alternative dark matter theories that deviate from the cold, collisionless paradigm. Searches for primordial black holes, PBHS, as a fraction of dark matter integrate astronomical observations with gravitational wave detections. The LIGO/Virgo collaborations have detected black hole mergers with masses in ranges compatible with some PBH formation scenarios, sparking interest in their contribution as dark matter candidates. However, microlensing surveys like OGLE and EROS have placed strong limits on the abundance of PBHS in certain mass windows, narrowing the parameter space available to this hypothesis and guiding future search strategies. In neutrino experiments, creating low-threshold detectors sensitive to sub-GeV dark matter opens new experimental domains. Xenon-based detectors tuned to detect light dark matter recoils are being developed, focusing on improving sensitivity to electron recoils induced by dark matter interactions. This approach leverages technological advances to investigate possible dark matter candidates with masses below the traditional WIMP scale, expanding our understanding of the possible dark matter spectrum. Developments in cryogenic calorimeters aim to detect dark matter-induced phonon signals in ultrapure crystals, with energy resolutions reaching below the electronvolt scale. These detectors monitor the tiny vibrations produced when dark matter particles collide with crystal lattices, offering sensitivity to very light dark matter particles or those interacting via less conventional mechanisms. The ability to operate at millikelvin temperatures reduces thermal noise, enabling detection of exceedingly rare and faint signals that could otherwise remain hidden. Exploring the impact of dark matter on the epoch of recombination through precision measurements of the CMB polarization provides indirect constraints on dark matter properties. Energy injection from dark matter annihilations or decays during this epoch would alter ionization levels and the CMB's temperature and polarization anisotropies. Data from satellites like Planck have been used to place upper limits on annihilation cross-sections, helping to exclude certain particle models that would otherwise modify early universe conditions beyond observed limits. The synergy between gamma-ray observatories and radio telescopes enables multi-wavelength investigations of dark matter annihilation or decay signals. For example, synchrotron radiation produced when relativistic electrons and positrons from dark matter interactions spiral in magnetic fields can be detected at radio frequencies. Joint analysis combining radio data with gamma-ray observations narrows uncertainties in astrophysical backgrounds and tests dark matter models in different regimes. Efforts to detect axions or axion-like particles, ALPES, which may constitute dark matter, use resonant cavities known as haloscopes. The Axion Dark Matter experiment, ADMX, employs microwave cavities in strong magnetic fields to convert axions into detectable photons. By tuning cavity resonant frequencies and scanning across plausible axion mass ranges, these searches incrementally cover possible parameter space, yielding some of the most stringent bounds on axion-photon coupling strengths to date. The geological record offers an unconventional platform to test certain dark matter models, particularly those invoking ultra-heavy or composite candidates. Accumulated damage tracks in ancient minerals or isotopic anomalies could be signatures of dark matter particles interacting over geological timescales. Although this approach is in early stages, it provides long-term integration complementary to event-based detectors and expands the scope of dark matter searches to terrestrial archives. Quantum information science contributes to dark matter detection through the development of sensors with sensitivity to extremely weak forces or subtle quantum state changes. Spin-based sensors, nitrogen vacancy centers in diamond, and atomic interferometers are being adapted to monitor tiny variations induced by interactions with dark matter fields. These devices promise to open new frontiers by probing parameter spaces inaccessible to classical detectors, especially for ultralight or wave-like dark matter candidates. Collider searches have also explored the possibility of dark matter production associated with Higgs boson decays or electroweak boson interactions. Since the discovery of the Higgs in 2012, experiments have sought exotic decay channels where the Higgs might decay invisibly into dark matter particles, altering expected branching ratios. Although no deviations from standard model predictions have been observed thus far, these analyses place valuable constraints on the coupling strength between the Higgs and dark matter. Space-based detectors such as the Alpha Magnetic Spectrometer, AM-SMINUS-2, continue operating with unprecedented exposure times, improving statistics for rare cosmic ray components potentially linked to dark matter. By accumulating data over years or decades, these instruments refine spectra of positrons, antiprotons, and nuclei at high energies. Continuous operation allows researchers to monitor temporal variations that could distinguish steady dark matter signals from transient astrophysical sources. Microwave kinetic inductance detectors, MKIDS, are emerging as sensitive tools for dark matter experiments, particularly in applications involving axion searches or photon detection in resonators. Operating at cryogenic temperatures, MKIDs can count single photons and measure their energy with fine resolution, enabling searches for weak dark matter-induced electromagnetic signatures. Their scalability and frequency multiplexing capability make them attractive components for future large-scale detector arrays. The increasing precision of stellar kinematic surveys from missions like Gaia enables detailed mapping of the Milky Way's dark matter halo through stellar motion measurements. By analyzing the velocities and spatial distributions of millions of stars, astrophysicists can infer the underlying gravitational potential attributed to dark matter. This data improves constraints on the shape, density, and substructure of our galactic dark matter halo, informing models of dark matter distribution and dynamics. The potential interaction of dark matter with ordinary matter via the so-called dark photon mediator is being investigated through fixed target and beam dump experiments. These laboratory setups produce intense particle beams aimed at dense targets, searching for signals of dark sector particles escaping detection. Constraints from such experiments provide important complementary limits on dark matter models featuring vector portal interactions that may evade traditional detection schemes. In globular clusters, which are tightly bound collections of old stars, searches focus on the potential accumulation and detection of dark matter effects on stellar dynamics or evolution. Although globular clusters are generally thought to be dark matter poor due to tidal stripping, precise observations of their gravitational potentials and internal velocities offer indirect probes of rare dark matter concentrations. Understanding the dark matter content in these environments tests formation history scenarios and helps refine the influence of dark matter on small-scale astrophysical objects. Cross-correlation studies combining different cosmological observables, such as lensing maps with galaxy clustering or CMB temperature maps, provide powerful statistical tools for probing dark matter and dark energy. These methods increase sensitivity to subtle signals by leveraging complementary dataset features, enabling tighter constraints on the growth of cosmic structures influenced by dark matter. Such analyses rely on extensive survey data and sophisticated statistical techniques, and are central to current efforts in precision cosmology. Laboratory experiments using ultra-cold neutrons, investigate neutron oscillations into hypothesized mirror neutron states as a candidate for dark matter interactions. By monitoring neutron disappearance and reappearance rates in highly controlled environments, these studies aim to detect rare transitions that would imply the existence of a parallel dark sector. Though still speculative, the experimental limits set by these investigations help to exclude or support certain mirror matter models. Advancements in detector material purity and radio purity measures are critical for reducing backgrounds that obscure rare dark matter signals. Techniques such as electroforming copper underground for detector components or using ultrapure crystals minimize contamination from radioactive isotopes that produce spurious events. Continuous improvements in material science directly translate into increased sensitivity and reliability of dark matter experimental results. Detailed simulations of the Milky Way's dark matter halo, incorporating baryonic feedback effects from star formation and supernovae, offer refined predictions for dark matter velocity distributions at Earth's location. These velocity profiles are essential inputs for interpreting direct detection data, as they affect expected recoil spectra and rates. Comparisons of simulated distributions with experimental results ensure that searches remain grounded in realistic astrophysical contexts rather than idealized assumptions. Dedicated underground experiments like COSIN Eminus 100 and ANAIS AIM to independently test the DAMA/Libra annual modulation claim by using similar target materials but different detector configurations and shielding techniques. These experiments seek to reproduce or refute the modulation signal under different environmental conditions, reinforcing confidence in or challenging the robustness of claimed detections. The resolution of this controversy is vital for understanding systematic effects and advancing direct detection technology. Precision measurement of isotope abundances in ancient meteorites and lunar samples provides constraints on decaying dark matter particles that would have injected energetic radiation into the early solar system. By comparing isotopic ratios with expected cosmic ray and solar radiation backgrounds, scientists identify potential anomalies attributable to dark matter decay products. These studies complement astrophysical observations by exploring dark matter influences on a local and historical scale. Supernova neutrino detectors such as SuperCamioCand also contribute to dark matter searches by monitoring for neutrino flux enhancements or spectral distortions caused by dark matter annihilation in dense astrophysical environments. Since core-collapse supernovae produce intense neutrino bursts, any modification in the neutrino signal attributable to exotic processes could hint at dark matter interactions. Continuous monitoring of neutrino event rates enhances the capability to detect these subtle effects. Investigations into seasonal and diurnal modulation effects extend beyond annual signals, incorporating Earth's rotation and orbital parameters influencing dark matter flux and detection rates. These finer time scales arise from the planet's orientation relative to the galactic dark matter halo and gravitational focusing effects caused by the Sun. Such modulations offer additional discrimination power to separate genuine dark matter interactions from stationary background noise. Tracking the deflection of fast radio bursts, FRBs, by dark matter substructures poses a novel observational frontier. These brief, intense bursts of radio waves traveling cosmological distances can be gravitationally lensed or scattered by intervening dark matter clumps, leading to characteristic delays or distortions. Observatories like CHIME and ASKAP, collecting large FRB samples, increasingly enable statistical studies of such phenomena, which may provide indirect evidence for dark matter structures on small scales. Superfluid helium detectors are being developed to detect dark matter through excitations analogous to phonons and rotons generated when particles deposit energy. The unique quantum properties of superfluid helium allow for extremely low thresholds and high sensitivity to light dark matter candidates. This approach complements traditional targets, broadening the experimental scope using diverse detection media and physical mechanisms. Gravitational microlensing surveys, such as those conducted by the Optical Gravitational Lensing Experiment (OGLE, continuously monitor millions of stars to identify lensing events caused by compact dark matter objects passing in front of background sources. Statistical analysis over many years has set upper limits on the abundance of MACHOs, massive compact halo objects, as dark matter components, especially in certain mass ranges. These constraints help refine the role of astrophysical compact objects in the overall dark matter budget. Tests of Lorentz invariance using high-precision experiments examine whether dark matter interactions could induce violations detectable through delicate symmetry measurements. Since many dark matter models potentially break or alter fundamental symmetries, sensitive searches for tiny deviations in particle behavior are employed. Results thus far have placed stringent constraints on such effects, guiding theorists toward models compatible with observed fundamental symmetries. Heliosismology, the study of sound waves traveling through the sun, offers indirect means to detect dark matter accumulating in the solar core. Dark matter particles gravitationally captured by the sun could alter energy transport and core temperature, subtly affecting oscillation frequencies measurable by heliosismic observations. Comparing measured solar oscillation patterns with theoretical models constrains the impact and properties of dark matter within our closest star. Exotic dark matter models propose interactions with gravitational waves, prompting searches for transient or persistent perturbations in gravitational wave detectors like LIGO and Virgo. While standard gravitational waves arise from astrophysical events, additional signals might indicate couplings to dark matter fields or particle backgrounds. Though no direct evidence has emerged, this approach leverages emerging multi-messenger astrophysics avenues and detector sensitivities. Data obtained from cosmic voids, large underdense regions in the universe, inform dark matter properties by analyzing how matter evacuates these spaces over cosmic time. The growth rates and shapes of voids are influenced by dark matter clustering and interaction properties. Surveys mapping void distribution and evolution provide constraints complementary to those derived from clusters and filaments, enriching the overall cosmological picture. Advanced computational techniques, including graph neural networks and Bayesian inference methods, have been integrated into dark matter research for data analysis and theoretical modeling. These tools enhance the capacity to handle complex, high-dimensional datasets, common in astrophysical surveys and laboratory experiments, facilitating the extraction of subtle dark matter signals from noisy environments. Their adoption reflects the increasing interdisciplinary nature of dark matter science. Laboratory searches for millicharged dark matter probe hypothetical particles carrying tiny electric charges through beam dump and fixed target experiments. The existence of dark matter particles with small electric charges would modify electromagnetic interactions and could produce detectable signatures in dedicated setups. Null results to date have placed tight constraints on this property, guiding the theoretical landscape. Tracking variations in pulsar timing arrays offers another strategy to probe dark matter structures. Deviations in the clock-like signals from millisecond pulsars caused by gravitational potential fluctuations due to dark matter subhalos or waves may be observed. Collaborations like Grav continuously analyze long-term pulsar timing data to detect such subtle perturbations, contributing to dark matter studies at galactic scales. Finally, developments in phonon-mediated detection methods aim to exploit the crystalline anisotropy of target materials to enhance the directional sensitivity of dark matter interactions. By measuring recoil angles through phonon signals in anisotropic crystals, experiments seek to confirm directional signatures expected from dark matter wind modulation. These innovative approaches have the potential to provide unambiguous identification of dark matter signals while reducing backgrounds. One of the emerging frontiers in dark matter detection involves the use of noble gas-time projection chambers with dual-phase technology, which combine liquid and gas phases of noble elements like xenon or argon. This setup enhances signal fidelity by allowing the extraction and amplification of ionization electrons into the gas phase, producing secondary scintillation light that is easier to detect. Such detectors benefit from improved background discrimination and precise three-dimensional event reconstruction, enabling experiments like LZ and dark side to push sensitivity limits ever lower. High-resolution spectroscopy of cosmic gamma ray sources, utilizing instruments like the Fermi Large Area Telescope, permits searches for monochromatic spectral lines indicative of dark matter annihilation or decay. While continuous spectra often arise from astrophysical processes, narrow lines, signaling photons with a fixed energy, would stand out as telltale signatures of dark matter interactions. Despite rigorous analyses, no definitive gamma ray lines associated with dark matter have been confirmed, setting strong constraints on particle properties and decay channels. The study of ultra-faint dwarf galaxies discovered through deep sky surveys has expanded potential indirect detection targets. These small galaxies exhibit exceptionally high mass-to-light ratios, implying a dominance of dark matter relative to their stellar content. Because their astrophysical gamma ray background is minimal, they provide clean laboratories for testing signals of dark matter annihilation, where even subtle excesses can translate into meaningful constraints on interaction cross-sections. Precision experiments measuring the neutron electric dipole moment, NEDM, offer complementary insights by limiting CP-violating interactions that could relate to dark matter particle models. Certain classes of dark matter, such as axions invoked to solve the strong CP problem, would influence the NEDM at measurable levels. Current NEDM measurements, therefore, add indirect limits to the parameter space of dark matter candidates related to underlying symmetries of the standard model. Innovations in drag-free satellite technologies enable highly sensitive measurements of gravitational forces in the Earth's vicinity, which can indirectly test dark matter distributions. Missions like the planned LISA Pathfinder have demonstrated the ability to monitor non-gravitational forces to unprecedented precision, laying groundwork for future space-based detectors that could identify minute gravitational perturbations, potentially caused by nearby dark matter clumps or subhalos. The analysis of tidal streams from disrupted dwarf galaxies around the Milky Way provides constraints on dark matter clumpiness at subgalactic scales. As these stellar streams traverse the galactic halo, interactions with dark matter subhalos lead to observable gaps and perturbations in their distribution. Detailed mapping of these features using data from Gaia and future surveys informs the abundance and mass function of dark matter substructures, refining theoretical models of structure formation. Searches for dark matter-induced ionization signals in molecular hydrogen and helium during the cosmic dark ages offer potential early universe probes. Such interactions could influence the formation rate of the first stars and galaxies by altering gas chemistry and cooling processes. Planned 21-centimeter cosmology experiments aim to detect these subtle effects, providing complementary avenues for understanding dark matter's role in shaping cosmic evolution. Beyond WIMPs and axions, attention has turned toward searching for dark matter made of primordial black holes, PBHS, through gravitational wave observations of compact object mergers. Advanced LIGO and Virgo detect black hole collisions, whose mass and spin distributions can hint at primordial origins. While current data place strong constraints on the fraction of dark matter composed of PBHS, continued gravitational wave observations improve sensitivity to this possibility. The directional dependence of solar neutrino fluxes provides an indirect probe for certain dark matter models proposing interactions within the Sun's core. Variations in neutrino production or energy spectra could signal dark matter particle capture and annihilation rates changing with solar activity or orbital parameters. Experiments like Borexino continue refining neutrino measurements, offering potential windows into dark matter accumulation in stellar environments. Superfluid helium-3 detectors exploit the unique fermionic properties of helium-3 atoms to achieve outstanding sensitivity to low-energy recoil events. Their operation at millikelvin temperatures allows precise detection of quasi-particle excitations caused by dark matter interactions. The isotropic superfluid phase provides a noise-reduced environment conducive to probing dark matter candidates with masses well below traditional detection thresholds. Measurement of the annual modulation in underground neutron background rates has been explored as a possible source of systematic bias in dark matter modulation claims. Neutrons produced by cosmic ray spallation or local radioactivity can mimic nuclear recoil signals, and their seasonal variation must be carefully accounted for. Laboratory studies of neutron production and propagation enhance background modeling, essential for accurate interpretation of direct detection data. The use of graphene and other two-dimensional materials in sensor technology is a novel development in dark matter detection efforts. Owing to their exceptional electrical, thermal, and mechanical properties, these materials offer pathways to build ultrasensitive detectors capable of registering minuscule energy depositions from low-mass dark matter particles. Prototypes investigating phonon and electron excitations in such materials promise enhanced resolution and lower energy thresholds. Dark matter interactions with ordinary matter could induce nuclear transitions or excitations detectable through precise gamma spectroscopy. Some experiments focus on rare nuclear processes, such as the excitation of metastable nuclear isomers or unusual gamma-ray emissions, which would arise if dark matter particles deposit energy in particular nuclear states. Although challenging, this approach provides a unique probe orthogonal to elastic nuclear recoils. The fine structure of the cosmic web, revealed by large spectroscopic galaxy surveys like SDSS and DAISY, enables indirect assessments of dark matter clustering on scales down to individual galaxy groups. By examining spatial correlations and redshift space distortions, researchers constrain the growth rate of structure and distinguish models with varying dark matter interaction strengths or particle properties. These statistical approaches blend astronomy and data science to refine cosmological parameters linked to dark matter. Cryogenic detectors utilizing superconducting transition-edge sensors, TES, are employed to detect minute temperature rises caused by dark matter particle interactions. TES devices operate at temperatures near their superconducting transition, where slight energy inputs change their resistance dramatically, allowing for sensitive detection of low-energy events. Their integration into dark matter experiments enhances the detection of rare interactions by providing excellent energy resolution and low noise floors. Studies of interstellar gas clouds and their thermal properties have also been proposed as probes of dark matter interactions, especially with ultralight candidates that might induce heating effects. Observations of cold, dense clouds that remain stable over long timescales place limits on possible exotic heating or cooling mechanisms attributable to dark matter particle interactions with baryons. These astrophysical constraints complement terrestrial experiments by exploring large volume, low-density environments. The spin-dependent interaction channel remains a focus of direct detection efforts, as certain dark matter candidates interact preferentially with the spin of atomic nuclei rather than their mass. Specialized detectors often incorporate target materials rich in isotopes like fluorine, sodium, or xenon isotopes with non-zero nuclear spin to enhance sensitivity to spin-dependent scattering. Constraints derived from spin-dependent searches provide essential complementary information to spin-independent cross-section limits. Exploring the potential seasonal variations in directional detection signals from dark matter requires advanced detector capabilities to track nuclear recoil trajectories in 3 dimensions. Gas-based time projection chambers with pixelated readouts are being developed to precisely measure recoil directions and energies. Such measurements could provide a powerful confirmatory signature of dark matter by correlating with the expected direction of the galactic dark matter wind. Luminous red galaxies and quasars, studied in spectroscopic surveys, serve as tracers of massive dark matter halos due to their preferential residence in dense environments. By linking galaxy properties to halo masses through halo occupation distribution models, cosmologists derive insights into the relationship between visible matter and dark matter structures over cosmic timescales. These studies refine theories of galaxy formation influenced by the underlying dark matter scaffolding. Ultra-high energy cosmic rays, detected by observatories like the Pier Auger Observatory, present a unique environment to search for dark matter decay products at energies unattainable in terrestrial accelerators. Some models suggest that decaying super-heavy dark matter could contribute to the highest energy cosmic rays, producing distinctive particle spectra. Current data have not confirmed such signals, but provide important exclusion limits on these exotic scenarios. Explorations of dark matter self-interactions in the context of small-scale structure have prompted hydrodynamical simulations incorporating nonlinear baryonic physics. Results demonstrate that self-interacting dark matter can alleviate some tensions between observations and cold dark matter predictions, such as core density profiles in dwarf galaxies. These high-resolution simulations guide both astrophysical observations and laboratory experiments seeking evidence for particle interactions beyond gravity. Deep underground sodium iodide detector arrays serve as a complementary platform to test claims of annual modulation signals, leveraging a material similar to DAMA/Libra, but with improved background rejection and newer technologies. Projects like COSIN Eminus 100 and SABRE aim to provide independent assessments by replicating key experimental parameters while employing rigorous shielding and timing analysis. This multi-experimental verification approach strengthens the scientific robustness of modulation studies. The cosmological lithium problem, involving the discrepancy between observed and predicted lithium abundances in old stars, has been examined for potential links to dark matter interactions during Big Bang nucleosynthesis. The presence of exotic particles or energy injections could modify elemental production, and precise measurements of lithium isotopes provide a benchmark for testing these hypotheses. While no definitive connections have been found, such nucleosynthesis probes remain part of the wider dark matter search spectrum. Satellite-based gamma-ray burst detectors offer transient event catalogs to investigate possible prompt or delayed signals resulting from dark matter annihilation in distant galaxies. Cross-correlating gamma-ray bursts with known dark matter-rich environments constrains models proposing dark matter decay triggered by astrophysical phenomena. Although challenging due to the transient nature and background complexity, these studies expand the temporal domain of indirect searches. Neutron star observations provide indirect constraints on dark matter properties via their potential capture and accumulation inside these compact objects. Dark matter particles gravitationally bound within neutron stars may influence their thermal evolution, rotation, or lead to collapse scenarios detectable through pulsar timing or X-ray emissions. These astrophysical laboratories probe dark matter candidates that interact weakly with baryons, but could deposit energy in dense nuclear matter. The application of quantum noise reduction techniques, such as squeezed light states, has been explored to improve the sensitivity of optical detection methods in dark matter experiments. By reducing quantum shot noise, these methods enhance signal-to-noise ratios for photon counting in searches like axion haloscopes. Progress in quantum optics thus promises to elevate experimental capabilities, pushing detection thresholds beyond classical limits. The implementation of multi-messenger astrophysics, combining gravitational waves, neutrinos, and electromagnetic observations, enriches dark matter studies by providing diverse probes of energetic phenomena influenced by or producing dark matter particles. For instance, joint detections can constrain dark matter particle lifetimes or interactions during cataclysmic events like neutron star mergers. This holistic approach integrates data from disparate observatories to deepen understanding of dark matter's cosmic role. The potential for detecting dark matter-induced changes in atomic parity violation experiments offers a precision laboratory test linked to electroweak-scale physics. Such experiments measure asymmetries in electron-nucleus interactions sensitive to new forces or particles mediating dark matter interactions. Null results tighten constraints on dark matter models, incorporating new vector bosons or scalar particles coupling to ordinary matter. Studies of the intergalactic medium via Lyman alpha forest observations help probe dark matter free-streaming lengths, thereby constraining its particle mass and interaction characteristics. The suppression or enhancement of small-scale absorption features informed theories regarding warm dark matter or alternative scenarios deviating from the cold dark matter paradigm. These observations provide some of the tightest cosmological constraints on low-mass dark matter candidates. The advancement of large-scale silicon-based solid-state detectors permits enhanced sensitivity to electron recoil events potentially induced by light dark matter particles. Experiments such as SENSEI utilize Skipper CCD technology to count individual electron hole pairs generated by sub-GeV dark matter interactions, pushing detection capabilities into previously unexplored mass ranges. These technological breakthroughs open new experimental avenues complementary to traditional nuclear recoil searches. Investigations into the effects of dark matter on the Sunyaev-Zeldovich effect, an alteration of the cosmic microwave background spectrum caused by hot electrons in galaxy clusters, have considered whether dark matter annihilation contributes to cluster pressure profiles. Accurate modeling of thermal and kinetic components of the effect aids in disentangling potential dark matter signals from standard astrophysical contributions. This method extends the indirect detection toolkit to cluster-scale observations. Studies of star formation rates in low metallicity dwarf galaxies may indirectly reflect dark matter properties, as the gravitational potential well shapes gas cooling and collapse. Comparing observational data with simulations incorporating various dark matter interaction strengths reveals subtle effects on galaxy evolution, constraining particle models influencing baryon-dark matter coupling. These astrophysical tests complement direct detection by linking dark matter physics to observable galaxy characteristics. Baseline stability and calibration methodologies in dark matter detectors are critical for reliable signal extraction over extended timescales. Techniques such as periodic injections of calibration signals or fiducial volume monitoring ensure detector response uniformity and facilitate the identification of subtle time-dependent signals, including annual modulation effects. Robust calibration protocols underpin the credibility of claim validations in dark matter search experiments. Dark matter searches in the subatomic scale continue, with experiments exploring rare nuclear decay processes such as neutrinoless double beta decay, which could signal Majorana particles related to the dark matter sector. While primarily aimed at neutrino physics, these experiments constrain parameters that overlap with some dark matter candidate models, bridging two frontier areas of fundamental physics. The multi-purpose nature of such detectors enhances the scientific return of investments. Sophisticated Monte Carlo simulations of detector response and background interactions are integral to dark matter search analysis, enabling researchers to model expected signal and noise distributions under diverse hypotheses. By benchmarking simulations against calibration data and environmental measurements, experimenters develop discriminants for potential dark matter signals. The evolution of these computational tools continues to improve detection confidence and sensitivity. Finally, the integration of citizen science platforms in analyzing astronomical data contributes to dark matter research by facilitating the identification of lensing events, variable sources, and galaxy morphologies. Public participation enhances data processing throughput and introduces novel pattern recognition capabilities, supplementing machine learning methods. Such collaborative efforts expand the human resource pool, tackling the complex datasets inherent in dark matter studies. One significant limitation in our understanding of dark matter arises from the precision of cosmological parameters derived from the cosmic microwave background, CMB. While the Planck satellite has measured these parameters with extraordinary accuracy, reconciling CMB-based dark matter density with observations of the large-scale structure sometimes reveals subtle tensions. For example, the sigma-8 parameter, which quantifies the clustering amplitude of matter fluctuations, exhibits mild discrepancies between CMB predictions and galaxy surveys, indicating possible unknown aspects of dark matter's interaction or behavior at low redshifts. Another challenge lies in the difficulty of distinguishing dark matter effects from baryonic feedback processes in galaxy formation. Stellar winds, supernova explosions, and active galactic nuclei can redistribute ordinary matter and alter the gravitational potential wells where dark matter resides. Accurately modeling these baryonic effects in simulations is complex, making it hard to isolate dark matter's intrinsic properties based solely on observed galactic structures. This entanglement limits the precision with which we can infer dark matter's microphysical nature. Despite the robustness of lambda-cold dark matter lambdictum as the leading cosmological model, it struggles to explain the observed diversity in rotation curves of dwarf galaxies, a puzzle called the Corcus problem. Simulations predict a steep, dense central concentration, cusp, of dark matter within galaxies, but observations often find flattened density profiles, cores. This discrepancy challenges assumptions about dark matter's cold, collisionless nature, and could hint at self-interactions or unknown particle physics effects, yet to be conclusively detected. The issue of small-scale structure, commonly referred to as the missing satellites problem, highlights another limit to our understanding. Cold dark matter simulations forecast many more small dark matter halos than observed dwarf galaxies in the Milky Way's neighborhood. This gap could originate from observational biases or complex baryonic processes, suppressing star formation in small halos. But it also signals uncertainties about dark matter clustering on subgalactic scales and its possible particle interactions affecting halo formation. From an experimental standpoint, many dark matter detection efforts focus on a narrow range of particle masses and interaction strengths, constrained by current instrumentation capabilities. This focus creates blind spots in parameter space where lighter or more weakly interacting candidates could elude detection. For instance, sub-eV mass axions or ultralight scalar fields require detection techniques fundamentally different from those used for weakly interacting massive particles, WIMPs, demonstrating how technical limitations restrict the scope of current searches. Additionally, astronomical observations have yet to uncover definitive signals of dark matter annihilation or decay, expected in some theoretical scenarios. Instruments like the Fermi Gamma Ray Space Telescope have mapped high-energy emissions from regions rich in dark matter, such as the galactic center or dwarf spheroidal galaxies. Yet identified signals remain ambiguous or attributable to astrophysical sources. This lack of a smoking gun indirect detection constrains models and emphasizes the limits of interpreting background cosmic signals amid complex environments. Gravitational microlensing surveys, such as those conducted by the Optical Gravitational Lensing Experiment (OGLE) and the MACHO collaboration, have placed strong limits on compact dark matter candidates like primordial black holes within certain mass windows. However, these observations cannot completely exclude all mass ranges or clustering scenarios, leaving open the possibility of dark matter composed of exotic compact objects that evade detection due to rarity or distribution. This illustrates the challenge of ruling out exhaustive classes of candidates using current methods. On the particle physics front, collider experiments like those at the Large Hadron Collider, LHC, seek signs of dark matter production via missing energy signatures in high-energy collisions. Despite stringent searches, no excess events have been conclusively linked to dark matter particles, restricting many supersymmetric or extra-dimensional models. The null results highlight experimental limitations in energy reach, luminosity, or detection sensitivity, underscoring the possibility that dark matter particles may interact even more feebly or have masses beyond current collider capabilities. A less explored frontier involves understanding whether dark matter possesses self-interactions, which could alter its behavior in galaxy clusters and smaller-scale structures. Studies of merging galaxy clusters, such as the Bullet cluster, indicate that dark matter behaves largely as a collisionless fluid, but subtle self-interaction cross-section limits remain imprecise. Refining these constraints requires high-resolution mapping of cluster mass distributions and velocities, a task complicated by the complex astrophysical environments and data analysis challenges, limiting definitive conclusions. Another intrinsic limitation is how cosmic variance affects large-scale measurements of dark matter distribution. Since we observe only one universe from a single vantage point, statistical fluctuations in matter density and structure growth can skew estimates derived from observational surveys. This fundamental uncertainty imposes a ceiling on the accuracy with which we can probe dark matter's properties from large-scale structure alone, and necessitates combining multiple observational techniques to reduce biases. Furthermore, the potential existence of dark radiation or additional relativistic species in the early universe complicates constraints on dark matter. Measurements from the CMB and Big Bang nucleosynthesis set bounds on the effective number of neutrino species, NEF, yet small deviations remain possible, potentially indicating unknown particles that interact or coexist with dark matter. Identifying and disentangling these contributions is challenging, limiting how precisely we can characterize dark matter's cosmological impact and its connection to the particle content of the universe. An often overlooked limitation is the impact of systematic uncertainties in astronomical measurements on dark matter inferences. For example, estimating the total mass or density profile of galaxy clusters depends on assumptions about hydrostatic equilibrium of hot gas observed in X-rays or Sunyaev-Zeldovich effect measurements. Any departures from equilibrium or instrumental calibration errors can skew mass determinations, affecting constraints on dark matter distribution and properties derived from these systems, thereby reflecting limitations inherent in observational astrophysics. In theoretical modeling, the adoption of simplified assumptions such as cold, collisionless, and non-interacting particles restricts our ability to capture more complex dark matter physics that could explain inconsistent observations. Extensions involving warm dark matter or interacting dark matter require significantly more computational resources and introduce degeneracies with baryonic physics, making model testing difficult. Such theoretical uncertainties place bounds on how completely numerical simulations can mimic the real universe and hinder the extraction of dark matter's intrinsic features. In addition, identifying the scale or mass threshold below which dark matter halos cease to form is still uncertain. This cutoff scale is sensitive to dark matter's particle nature, velocity dispersion, and possible interactions. Observations and simulations have not yet converged on precise values, especially for lower mass halos, limiting our ability to use small-scale structures as probes of particle dark matter properties, and reflecting gaps in understanding how microscopic properties translate into cosmic structures. The role of neutrinos as a hot dark matter component further complicates the landscape. Though neutrinos constitute only a small fraction of total matter, their free streaming suppresses the formation of structures on small scales. Pinning down neutrino masses and their cosmological impact requires disentangling their subtle effects from those of cold dark matter and baryons, imposing limits on measuring both neutrino and dark matter characteristics simultaneously from large-scale observations. It is also noteworthy that the nature of dark matter influences the timing and efficiency of cosmic reionization, the epoch when the first stars and galaxies ionized intergalactic hydrogen. Different dark matter models predict varying rates of early structure formation, thereby affecting reionization signature in the CMB and future 21 cm line observations. Presently, the scarcity of direct measurements for this epoch limits the constraints on dark matter properties that reionization studies can provide, illustrating a gap between theory and data. Another fundamental limit arises from our inability to replicate dark matter properties in terrestrial laboratories due to the vast difference in scale between cosmological phenomena and lab conditions. This scale discrepancy restricts direct experimental control or manipulation of dark matter candidates and constrains tests primarily to indirect methods or observed astrophysical effects, meaning insights depend heavily on interpretations rather than direct measurement. The intrinsic weakness of gravitational interactions with standard matter also severely constrains potential detection channels. Since gravity is the only confirmed force coupling dark matter to observable matter, signals in detectors are rare and faint, often lost in backgrounds or instrumental noise. This realization informs the design of experiments, but also highlights a fundamental sensitivity limit in any method relying on gravitational effects or weak interaction cross-sections. Observations of galaxy cluster collisions besides the bullet cluster, like the train wreck cluster and Abel clusters, further illustrate complexities when interpreting dark matter properties. Although such systems provide natural laboratories to probe dark matter interactions, their dynamics are intricate, and modeling errors or assumptions about initial conditions introduce uncertainties. Consequently, establishing precise limits on dark matter interactions from these events remains challenging and subject to ongoing refinement. The global dark matter mass function, describing the number of halos as a function of mass, is inferred primarily from simulations combined with limited observational data. Yet inherent uncertainties about the mass-to-light ratios of galaxies and the influence of feedback effects impede precise empirical determinations. Without accurate mass function measurements, devising tight constraints on dark matter's clustering behavior or formation history remains limited. Interdisciplinary gaps between astrophysics, cosmology, and particle physics also constrain our ability to fully understand dark matter. While each field offers insights, the integration of data and theoretical frameworks is non-trivial due to differing methodologies, assumptions, and scales. This fragmentation slows progress in developing comprehensive models and interpreting complex datasets, setting a procedural limit on the speed of breakthrough discoveries. Finally, as new dark matter candidates emerge, potentially involving hidden sectors, non-thermal production mechanisms, or exotic quantum properties, the lack of corresponding experimental or observational probes curtails testing these theories. Many proposed models remain speculative partly because existing instruments lack the sensitivity to detect their predicted signals. This deficiency feeds back into the broader limitation. The current generation of technologies and data analysis methods restrict our capacity to explore the full parameter space of conceivable dark matter properties and interactions. A central difficulty in advancing dark matter research lies in the disentanglement of dark matter, effects from those of ordinary matter, across multiple cosmic environments. The gravitational influence of stars, gas, and dust complicates attempts to isolate dark matter signatures, especially in dense regions like galactic centers, where baryonic components dominate the gravitational potential. This interplay requires sophisticated modeling and high-precision data. Yet degeneracies between dark and luminous matter distributions often leave room for uncertainty, limiting our ability to refine dark matter profiles accurately. The diversity in galactic morphologies and compositions further complicates efforts to generalize dark matter properties. For example, low surface brightness (LSB) galaxies, characterized by their diffuse stellar content, often exhibit rotation curves that differ markedly from those of high surface brightness galaxies. These differences challenge universal dark matter halo models and suggest potential environmental or evolutionary effects influencing dark matter distributions, underscoring uncertainties in applying a one-size-fits-all paradigm for dark matter halos. Weak gravitational lensing surveys, key to mapping dark matter over vast cosmological scales, face systematic challenges such as intrinsic alignments of galaxies, atmospheric distortions, and instrument calibration errors. These effects can bias the inferred dark matter density fields, creating limits on the precision of dark matter mapping and the derived cosmological parameters. Although statistical methods mitigate some biases, residual systematics persist, defining an observational floor that restricts the extraction of subtle dark matter features. The alignment, or lack thereof, between dark matter halos and their host galaxies constitutes another puzzle. Observations indicate that in some cases, dark matter distributions appear misaligned with the luminous matter, suggesting complex formation histories or interactions that are not fully captured in simulations. Such misalignments limit the reliability of using galaxy light as a tracer for dark matter, and indicate that halo galaxy connections embody intricate physics still to be fully unraveled. Limits on understanding dark matter also arise from the incomplete knowledge of cosmic baryon cycles, including gas accretion, feedback, and outflows, which shape the environment where dark matter accumulates. These baryonic processes influence the gravitational potential and can modify dark matter distribution indirectly, but uncertainties in modeling their timing, scale, and efficiency constrain our ability to isolate pure dark matter effects. As a result, interpretations of structure formation hinge on assumptions that may hide or mimic dark matter properties. Cosmic voids, the vast underdense regions of the universe, provide a complementary regime to test dark matter theories. However, their low matter content and complex dynamical evolution make it challenging to extract precise constraints on dark matter using void statistics. The limited signal-to-noise in void observations and complex environmental effects restrict the utility of voids for testing alternative dark matter models, highlighting another domain where observational limitations affect theoretical interpretation. Astrophysical backgrounds pose significant challenges in indirect dark matter searches. For instance, high-energy cosmic rays, pulsars, and supernova remnants emit gamma rays and other particles that can mask or imitate signals expected from dark matter annihilation or decay. Accurately modeling these backgrounds demands detailed astrophysical knowledge, and any mismodeling can lead to false positive or negative detections, limiting the reliability of current indirect detection efforts. The rarity and vast parameter space of dark matter candidates require experimental designs that balance breadth and depth. Many experiments optimize sensitivity for specific mass ranges or interaction types, inherently limiting their ability to discover particles lying outside these niches. Consequently, the sheer diversity of candidate properties combined with resource constraints results in unavoidable gaps or blind spots in search strategies, which in turn curtail the completeness of dark matter surveys. In cosmological simulations, accurately capturing the interplay between dark matter and baryons demands high spatial and temporal resolution, yet computational limitations often force trade-offs. For example, large volumes are simulated at moderate resolution to capture cosmological context, while small-scale physics requires zoom-in simulations on individual halos. This separation complicates constructing fully consistent models across all relevant scales, posing limits on the fidelity of simulated dark matter structures. Further limits on understanding arise from the intrinsic dependence of dark matter characterization on the assumed cosmological model. The lambdictum framework serves as the backdrop for most analyses. However, any departures from this model, such as evolving dark energy or alternative gravity theories, could affect inferred dark matter properties. This dependence implies that uncertainties in cosmological parameters propagate into uncertainties about dark matter, making the complete characterization contingent on progress in broader cosmology. The dynamic nature of the early universe, involving complex phase transitions and particle production mechanisms, remains only partially understood, constraining interpretations of dark matter origins. Processes such as thermal freeze-out or freeze-in set relic abundances in standard scenarios, but alternative non-thermal production channels are harder to constrain observationally. The incomplete grasp of these early conditions limits the ability to connect present-day dark matter properties directly to specific formation mechanisms. In the realm of neutrino physics, the interplay between neutrino mass hierarchy and dark matter clustering introduces subtle but non-negligible uncertainties. The exact neutrino mass ordering affects free-streaming lengths and thereby influences small-scale structure formation, which in turn overlaps with scales sensitive to dark matter properties. This degeneracy complicates efforts to use cosmological data to disentangle neutrino and dark matter effects, highlighting a key astrophysical particle physics interface still fraught with unknowns. Attempts to detect axion dark matter via haloscopes or helioscopes are constrained by the narrow sensitivity bandwidth and require assumptions about axion mass and coupling constants. The absence of a positive detection so far impels expanding search ranges, but experimental techniques face practical limits in tuning frequencies and background suppression. These instrumental and methodological limitations illustrate how knowledge gaps hinge not only on theory, but also on experimental implementation. The question of whether dark matter clusters gravitationally at all scales remains partially unresolved. Cold dark matter models predict hierarchical clustering down to very small mass scales, but observationally, these smallest halos are difficult or impossible to detect with current means. Without direct evidence for these microhalos, confirming detailed theoretical predictions remains elusive, limiting our understanding of dark matter's clustering behavior at the microscopic end of the halo mass spectrum. Tensions between local measurements of the Hubble constant and those extrapolated from CMB data demonstrate a fundamental cosmic parameter uncertainty that indirectly affects dark matter studies. Any mismatch in cosmic expansion history impacts the inferred growth of structure, dark matter distribution constraints, and particle property limits. Resolving such discrepancies is crucial before some aspects of dark matter phenomenology can be firmly established, indicating intertwined challenges across cosmological investigations. The isotropy assumption underlying many cosmological analyses implies that dark matter distribution and behavior are uniform on large scales, yet observations sometimes reveal anisotropic features or large-scale structure anomalies. These irregularities may originate from primordial fluctuations, astrophysical processes, or unknown physics, but their presence complicates the interpretation of dark matter's fundamental properties and its role in universal evolution. This introduces limits in assuming spatial homogeneity for dark matter characterization. Current constraints on dark matter self-interaction cross-sections rely heavily on observations of galaxy cluster mergers, but inherent uncertainties in the timing, geometry, and mass distribution of these events restrict precision. In addition, dynamical evolution can mask or mimic signatures of dark matter collisions, leading to model degeneracies. Such observational and interpretational challenges limit our ability to conclusively establish or rule out self-interacting dark matter scenarios. The phenomenon of dark matter core formation, the flattening of central density profiles in some galaxies, presents interpretational difficulties because it can arise from either dark matter physics or baryonic feedback. Distinguishing between these causes requires high-resolution data and comprehensive simulations, yet existing data resolution or sample size constrains the strength of conclusions. This ambiguity limits our capacity to identify exotic dark matter properties solely based on core-cusp observations. Similarly, the process of galaxy merging can redistribute dark matter and baryons in ways that complicate the reconstruction of original dark matter halos. Post-merger systems exhibit complex kinematics and mass distributions that challenge current analytical and simulation tools. Such complexity hampers backward inference of dark matter properties from observed mergers, essentially imposing limits on how well we can reconstruct dark matter evolution pathways. The non-observation of signals from dark matter annihilation or decay in the cosmic neutrino background similarly restricts constraints on particle lifetime and interaction strength. Current neutrino detectors lack the sensitivity to isolate diffuse dark matter contributions from astrophysical neutrino backgrounds with high confidence. This limitation lowers the efficacy of neutrino telescopic methods in narrowing dark matter parameter space compared to photon-based indirect detection approaches. Spatial and temporal variability in astrophysical conditions can mimic or obscure signals attributed to dark matter. For instance, fluctuations in magnetic fields, cosmic ray densities, or interstellar medium properties influence emission profiles used to constrain dark matter models. Such environmental noise increases the complexity of extracting robust dark matter information from astrophysical data, placing practical limits on signal identification. Some dark matter models predict subtle effects on gravitational wave propagation or formation mechanisms, but current gravitational wave detectors lack the sensitivity or frequency range to detect such signatures. Although gravitational wave astronomy is an emerging field with promising potential, its present limitations restrict its contribution to resolving dark matter's nature. Ongoing development in this area may eventually provide new constraints, but presently it remains a frontier with untapped potential. The lack of laboratory-based dark matter production, despite extensive collider searches, points to potential limitations in model coverage or energy reach. Existing accelerators might not produce dark matter particles if their mass scale lies beyond current energies, or if interactions differ fundamentally from weak or strong interactions. This practical limitation delays experimental validation of particle physics models and confines dark matter studies largely to indirect and astrophysical techniques. Dark matter's role in influencing the dynamics and morphology of large-scale cosmic filaments remains poorly constrained observationally. These filaments, which connect clusters and superclusters, are challenging to study due to low densities and limited luminous tracers. Without precise measurements of dark matter in these structures, understanding its influence on cosmic web formation and evolution remains incomplete. The determination of the exact mass-to-light ratio in galaxies, critical for inferring dark matter presence, suffers from uncertainties linked to stellar population models and dust extinction. Variations in these factors affect estimates of luminous matter, thereby impacting dark matter mass estimates indirectly. The consequent propagation of uncertainties into dark matter distribution modeling illustrates observational limitations rooted in the complexity of astrophysical data. Environmental dependence of dark matter halo properties, such as mass accretion history or tidal stripping effects, introduces diversity that is difficult to capture fully in population-level studies. Observational biases due to selection effects or limited sampling further obscure this diversity, restricting understanding of how environment shapes dark matter structures. Such variability imposes an inherent limitation on universal or simplified models of dark matter halos. In studies of strong gravitational lensing, subhalo detection within lensing galaxies offers a route to probe dark matter granularity, but limited spatial resolution and complex lens models constrain sensitivity and accuracy. These technical challenges cap the precision with which small-scale substructure can be mapped, limiting tests of dark matter, clustering predictions, and particle properties that influence subhalo abundance. The statistical methods employed in cosmological parameter estimation carry inherent uncertainties related to sample sizes, model priors, and data completeness. Bayesian inference or likelihood analyses are sensitive to input assumptions and can produce varying dark matter parameter estimates depending on methodology. Such statistical limitations highlight the importance of robust analysis frameworks and diverse datasets to minimize uncertainties. Direct detection experiments rely on assumptions about dark matter velocity distributions in the Milky Way halo. Yet measurements of local dark matter kinematics are indirect and model-dependent. Variability in these assumptions influences sensitivity projections and interpretation of experimental results, introducing a key unknown that impacts the robustness of exclusion limits or potential signals. Existing constraints on the presence of dark matter substructure in the solar neighborhood remain weak due to the difficulty of detecting and characterizing such small-scale features. The presence or absence of local subhalos influences direct and indirect detection prospects, but current limits remain coarse, representing a gap in the interface between galactic astronomy and particle searches. The complexity of dark matter-baryon interactions during the epoch of recombination can affect the detailed anisotropy patterns seen in the cosmic microwave background. Although data from Planck and WMAP have constrained these interactions tightly, residual model uncertainties persist, limiting the precision of dark matter property extraction from CMB measurements. Finally, the sheer scale and scope of dark matter research extend beyond a single experimental or observational domain, requiring coordinated efforts that span multiple disciplines and technologies. Coordination challenges, funding limits, and the long development times of major facilities represent practical restrictions that slow progress. These systemic limitations highlight that our understanding of dark matter is not solely bound by physics or technology, but also by the broader context of scientific enterprise. Together, these factors combine to illustrate the substantial and multifaceted limits inherent in current efforts to understand dark matter. While each limitation points to areas for future improvement, their cumulative effect underscores the persistent and challenging nature of the dark matter problem within modern science.